Welcome to Academic Avengers. Today we begin a journey into Brian Greene's groundbreaking book, The Elegant Universe, Superstrings, Hidden Dimensions, and the Quest for the Ultimate Theory. In this masterpiece, Greene invites us to explore the mysteries of space, time, and the hidden fabric of reality. From Einstein's relativity to the strange world of quantum mechanics, and finally to the daring vision of string theory, this book opens the door to one of the most ambitious scientific quests of our time, the search for a unified theory of the universe. Preface. During the last 30 years of his life, Albert Einstein sought relentlessly for a so-called unified field theory, a theory capable of describing nature's forces within a single, all-encompassing coherent framework. Einstein was not motivated by the things we often associate with scientific undertakings, such as trying to explain this or that piece of experimental data. Instead, he was driven by a passionate belief that the deepest understanding of the universe would reveal its truest wonder, the simplicity and power of the principles on which it is based. Einstein wanted to illuminate the workings of the universe with a clarity never before achieved, allowing us all to stand in awe of its sheer beauty and elegance. Einstein never realized this dream, in large part because the deck was stacked against him. In his day, a number of essential features of matter and the forces of nature were either unknown or, at best, poorly understood. But during the past half-century, physicists of each new generation, through fits and starts and diversions down blind alleys, have been building steadily on the discoveries of their predecessors to piece together an ever fuller understanding of how the universe works. And now, long after Einstein articulated his quest for a unified theory but came up empty-handed, physicists believe they have finally found a framework for stitching these insights together into a seamless whole. A single theory that, in principle, is capable of describing all physical phenomena. The theory, superstring theory, is the subject of this book. I wrote The Elegant Universe in an attempt to make the remarkable insights emerging from the forefront of physics research accessible to a broad spectrum of readers, especially those with no training in mathematics or physics. Through public lectures on superstring theory I have given over the past few years, I have witnessed a widespread yearning to understand what current research says about the fundamental laws of the universe, how these laws require a monumental restructuring of our conception of the cosmos, and what challenges lie ahead in the ongoing quest for the ultimate theory. I hope that by explaining the major achievements of physics going back to Einstein and Heisenberg, and describing how their discoveries have grandly flowered through the breakthroughs of our age, this book will both enrich and satisfy this curiosity. I also hope that The Elegant Universe will be of interest to readers who do have some scientific background. For science students and teachers, I hope this book will crystallize some of the foundational material of modern physics, such as special relativity, general relativity, and quantum mechanics, while conveying the contagious excitement of researchers closing in on the long-sought unified theory. For the avid reader of popular science, I have tried to explain many of the exhilarating advances in our understanding of the cosmos that have come to light during the last decade. And for my colleagues in other scientific disciplines, I hope this book will give an honest and balanced sense of why string theorists are so enthusiastic about the progress being made in the search for the ultimate theory of nature. Superstring theory casts a wide net. It is a broad and deep subject that draws on many of the central discoveries in physics. Since the theory unifies the laws of the large and of the small, laws that govern physics out to the farthest reaches of the cosmos and down to the smallest speck of matter, there are many avenues by which one can approach the subject. I have chosen to focus on our evolving understanding of space and time. I find this to be an especially gripping developmental path, one that cuts a rich and fascinating swath through the essential new insights. Einstein showed the world that space and time behave in astoundingly unfamiliar ways. Now, cutting-edge research has integrated his discoveries into a quantum universe with numerous hidden dimensions coiled into the fabric of the cosmos. Dimensions whose lavishly entwined geometry may well hold the key to some of the most profound questions ever posed. Although some of these concepts are subtle, we will see that they can be grasped through down-to-earth analogies. And when these ideas are understood, they provide a startling and revolutionary perspective on the universe. Throughout this book, I have tried to stay close to the science while giving the reader an intuitive understanding, often through analogy and metaphor, of how scientists have reached the current conception of the cosmos. Although I avoid technical language and equations because of the radically new concepts involved, the reader may need to pause now and then, to mull over a section here or ponder an explanation there in order to follow the progression of ideas fully. A few sections of Part 4, focusing on the most recent developments, are a bit more abstract than the rest. I have taken care to forewarn the reader about these sections and to structure the text so that they can be skimmed or skipped with minimal impact on the book's logical flow. I have included a glossary of scientific terms for an easy and accessible reminder of ideas introduced in the main text. Although the more casual reader may wish to skip the endnotes completely, the more diligent reader will find in the notes amplifications of points made in the text, clarifications of ideas that have been simplified in the text, as well as a few technical excursions for those with mathematical training. I owe thanks to many people for their help during the writing of this book. David Steinhardt read the manuscript with great care and generously provided sharp editorial insights and invaluable encouragement. David Morrison, Ken Weinberg, Raphael Kasper, Nicholas Bowles, Stephen Carlip, Arthur Greenspoon, David Merman, Michael Popowitz, and Shani Offen read the manuscript closely and offered detailed reactions and suggestions that greatly enhanced the presentation. Others who read all or part of the manuscript and offered advice and encouragement are Paul Aspinwall, Persis Drell, Michael Duff, Kurt Gottfried, Joshua Greene, Teddy Jefferson, Mark Kamionkowsko, Yakov Cantor, Andras Kovac, David Lee, Megan McEwen, Nari Mistry, Hassan Padamzi, Ronan Plesser, Massimo Parati, Fred Sherry, Lars Strader, Stephen Strogatz, Andrew Strominger, Henry Ty, Kamrun Vafa, and Gabriele Veneziano. I owe special thanks to Raphael Gunner for, among many other things, his insightful criticisms at an early stage of writing that helped to shape the overall form of the book, and to Robert Malley for his gentle but persistent encouragement to go beyond thinking about the book and to put pen to paper. Stephen Weinberg and Sidney Coleman offered valuable advice and assistance, and it is a pleasure to acknowledge many helpful interactions with Carol Archer, Vicky Karstens, David Castle, Ann Coyle, Michael Duncan, Jane Foreman, Eric Gendrison, Gary Cass, Shiva Kumar, Robert Mawani, Pam Morehouse, Pierre Ramond, Amanda Sals, and Eero Simoncelli. I am indebted to Kostas Eftimiou for his help in fact-checking and reference finding, and for turning my initial sketches into line drawings from which Tom Rockwell created, with the patience of a saint and a masterful artistic eye, the figures that illustrate the text. I also thank Andrew Hansen and Jim Sethna for their help in preparing a few of the specialized figures, for agreeing to be interviewed and to lend their personal perspectives on various topics covered. I thank Howard Georgi, Sheldon Glashow, Michael Greene, John Schwartz, John Wheeler, Edward Witten, and again, Andrew Strominger, Kamrun Vafa, and Gabriele Veneziano. I am happy to acknowledge the penetrating insights and invaluable suggestions of Angela von der Lippe and the sharp sensitivity to detail of Tracy Nagel, my editors at W.W. Norton, both of whom significantly enhance the clarity of the presentation. I also thank my literary agents John Brockman and Katinka Matson for their expert guidance in shepherding the book from inception to publication, for generously supporting my research in theoretical physics for more than a decade and a half. I gratefully acknowledge the National Science Foundation, the Alfred P. Sloan Foundation, and the U.S. Department of Energy. It is perhaps not surprising that my own research has focused on the impact superstring theory has on our conception of space and time, and in a couple of the later chapters I describe some of the discoveries in which I had the fortune to take part. Although I hope the reader will enjoy reading these inside accounts, I realize that they may leave an exaggerated impression of the role I have played in the development of superstring theory. So let me take this opportunity to acknowledge the more than 1,000 physicists around the world who are crucial and dedicated participants in the effort to fashion the ultimate theory of the universe. I apologize to all whose work is not included in this account. This merely reflects the thematic perspective I have chosen and the length limitations of a general presentation. Finally, I owe heartfelt thanks to Ellen Archer for her unwavering love and support, without which this book would not have been written. Part 1. The Edge of Knowledge. Chapter 1. Tied Up with String. Calling it a cover-up would be far too dramatic. But for more than half a century, even in the midst of some of the greatest scientific achievements in history, physicists have been quietly aware of a dark cloud looming on a distant horizon. The problem is this: there are two foundational pillars upon which modern physics rests. One is Albert Einstein's general relativity, which provides a theoretical framework for understanding the universe on the largest of scales: stars, galaxies, clusters of galaxies, and beyond to the immense expanse of the universe itself. The other is quantum mechanics, which provides a theoretical framework for understanding the universe on the smallest of scales: molecules, atoms, and all the way down to subatomic particles like electrons and quarks. Through years of research, physicists have experimentally confirmed to almost unimaginable accuracy virtually all predictions made by each of these theories. But these same theoretical tools inexorably lead to another disturbing conclusion. As they are currently formulated, general relativity and quantum mechanics cannot both be right. The two theories underlying the tremendous progress of physics during the last 100 years, progress that has explained the expansion of the heavens and the fundamental structure of matter, are mutually incompatible. If you have not heard previously about this ferocious antagonism, you may be wondering why. The answer is not hard to come by. In all but the most extreme situations, physicists study things that are either small and light, like atoms and their constituents, or things that are huge and heavy, like stars and galaxies, but not both. This means that they need use only quantum mechanics or only general relativity, and can, with a furtive glance, shrug off the barking admonition of the other. For 50 years, this approach has not been quite as blissful as ignorance, but it has been pretty close. But the universe can be extreme. In the central depths of a black hole, an enormous mass is crushed to a minuscule size. At the moment of the Big Bang, the whole of the universe erupted from a microscopic nugget whose size makes a grain of sand look colossal. These are realms that are tiny and yet incredibly massive, therefore requiring that both quantum mechanics and general relativity simultaneously be brought to bear. For reasons that will become increasingly clear as we proceed, the equations of general relativity and quantum mechanics, when combined, begin to shake, rattle, and gush with steam like a red-lined automobile. Put less figuratively, well-posed physical questions elicit nonsensical answers from the unhappy amalgam of these two theories. Even if you are willing to keep the deep interior of a black hole and the beginning of the universe shrouded in mystery, you can't help feeling that the hostility between quantum mechanics and general relativity cries out for a deeper level of understanding. Can it really be that the universe at its most fundamental level is divided, requiring one set of laws when things are large and a different incompatible set when things are small? Superstring theory, a young upstart compared with the venerable edifices of quantum mechanics and general relativity, answers with a resounding no. Intense research over the past decade by physicists and mathematicians around the world has revealed that this new approach to describing matter at its most fundamental level resolves the tension between general relativity and quantum mechanics. In fact, superstring theory shows more. Within this new framework, general relativity and quantum mechanics require one another for the theory to make sense. According to superstring theory, the marriage of the laws of the large and the small is not only happy, but inevitable. That's part of the good news, but superstring theory, string theory for short, takes this union one giant step further. For 3 decades, Einstein sought a unified theory of physics, one that would interweave all of nature's forces and material constituents within a single theoretical tapestry. He failed. Now, at the dawn of the new millennium, proponents of string theory claim that the threads of this elusive unified tapestry finally have been revealed. String theory has the potential to show that all of the wondrous happenings in the universe, from the frantic dance of subatomic quarks to the stately waltz of orbiting binary stars, from the primordial fireball of the Big Bang to the majestic swirl of heavenly galaxies, are reflections of one grand physical principle, one master equation. Because these features of string theory require that we drastically change our understanding of space, time, and matter, they will take some time to get used to sink in at a comfortable level. But as shall become clear, when seen in its proper context, string theory emerges as a dramatic yet natural outgrowth of the revolutionary discoveries of physics during the past 100 years. In fact, we shall see that the conflict between general relativity and quantum mechanics is actually not the first, but the third in a sequence of pivotal conflicts encountered during the past century, each of whose resolution has resulted in a stunning revision of our understanding of the universe. The three conflicts. The first conflict, recognized as far back as the late 1800s, concerns puzzling properties of the motion of light. Briefly put, according to Isaac Newton's laws of motion, if you run fast enough, you can catch up with a departing beam of light, whereas according to James Clerk Maxwell's laws of electromagnetism, you can't. As we will discuss in Chapter 2, Einstein resolved this conflict through his theory of special relativity, and in so doing completely overturned our understanding of space and time. According to special relativity, no longer can space and time be thought of as universal concepts set in stone, experienced identically by everyone. Rather, space and time emerged from Einstein's reworking as malleable constructs whose form and appearance depend on one's state of motion. The development of special relativity immediately set the stage for the second conflict. One conclusion of Einstein's work is that no object, in fact, no influence or disturbance of any sort, can travel faster than the speed of light. But, as we shall discuss in Chapter 3, Newton's experimentally successful and intuitively pleasing universal theory of gravitation involves influences that are transmitted over vast distances of space instantaneously. It was Einstein, again, who stepped in and resolved the conflict by offering a new conception of gravity with his 1915 general theory of relativity. Just as special relativity overturned previous conceptions of space and time, so too did general relativity. Not only are space and time influenced by one's state of motion, but they can warp and curve in response to the presence of matter or energy. Such distortions to the fabric of space and time, as we shall see, transmit the force of gravity from one place to another. Space and time, therefore, can no longer to be thought of as an inert backdrop on which the events of the universe play themselves out. Rather, through special and then general relativity, they are intimate players in the events themselves. Once again, the pattern repeated itself. The discovery of general relativity, while resolving one conflict, led to another. Over the course of the 3 decades beginning in 1900, physicists developed quantum mechanics, discussed in Chapter 4 in response to a number of glaring problems that arose when 19th century conceptions of physics were applied to the microscopic world. And as mentioned above, the third and deepest conflict arises from the incompatibility between quantum mechanics and general relativity. As we will see in Chapter 5, the gently curving geometrical form of space emerging from general relativity is at loggerheads with the frantic, roiling microscopic behavior of the universe implied by quantum mechanics. As it was not until the mid-1980s that string theory offered a resolution, this conflict is rightly called the central problem of modern physics. Moreover, building on special and general relativity, string theory requires its own severe revamping of our conceptions of space and time. For example, most of us take for granted that our universe has 3 spatial dimensions, but this is not so according to string theory, which claims that our universe has many more dimensions than meet the eye, dimensions that are tightly curled into the folded fabric of the cosmos. So central are these remarkable insights into the nature of space and time that we shall use them as a guiding theme in all that follows. String theory, in a real sense, is the story of space and time since Einstein. To appreciate what string theory actually is, we need to take a step back and briefly describe what we have learned during the last century about the microscopic structure of the universe. The universe at its smallest, what we know about matter. The ancient Greeks surmised that the stuff of the universe was made up of tiny, uncuttable ingredients that they called atoms. Just as the enormous number of words in an alphabetic language is built up from the wealth of combinations of a small number of letters, they guessed that the vast range of material objects might also result from combinations of a small number of distinct elementary building blocks. It was a prescient guess. More than 2,000 years later, we still believe it to be true, although the identity of the most fundamental units has gone through numerous revisions. In the 19th century, scientists showed that many familiar substances such as oxygen and carbon had a smallest recognizable constituent. Following in the tradition laid down by the Greeks, they called them atoms. The name stuck, but history has shown it to be a misnomer, since atoms surely are cuttable. By the early 1930s, the collective works of J.J. Thomson, Ernest Rutherford, Niels Bohr, and James Chadwick had established the solar system-like atomic model with which most of us are familiar. Far from being the most elementary material constituent, atoms consist of a nucleus, containing protons and neutrons, that is surrounded by a swarm of orbiting electrons. For a while, many physicists thought that protons, neutrons, and electrons were the Greeks' atoms. But in 1968, experimenters at the Stanford Linear Accelerator Center, making use of the increased capacity of technology to probe the microscopic depths of matter, found that protons and neutrons are not fundamental either. Instead, they showed that each consists of three smaller particles called quarks, a whimsical name taken from a passage in James Joyce's Finnegan's Wake by the theoretical physicist Murray Gell-Mann, who previously had surmised their existence. The experimenters confirmed that quarks themselves come in two varieties, which were named a bit less creatively up and down. A proton consists of two up quarks and a down quark. A neutron consists of two down quarks and an up quark. Everything you see in the terrestrial world and the heavens above appears to be made from combinations of electrons, up quarks, and down quarks. No experimental evidence indicates that any of these three particles is built up from something smaller. But a great deal of evidence indicates that the universe itself has additional particulate ingredients. In the mid-1950s, Frederick Rines and Clyde Cowan found conclusive experimental evidence for a fourth kind of fundamental particle called a neutrino, a particle whose existence was predicted in the early 1930s by Wolfgang Pauli. Neutrinos proved very difficult to find because they are ghostly particles that only rarely interact with other matter. An average energy neutrino can easily pass right through many trillion miles of lead without the slightest effect on its motion. This should give you significant relief because right now, as you read this, billions of neutrinos ejected into space by the sun are passing through your body and the Earth as well, as part of their lonely journey through the cosmos. In the late 1930s, another particle called a muon, identical to an electron except that a muon is about 200 times heavier, was discovered by physicists studying cosmic rays, showers of particles that bombard Earth from outer space. Because there was nothing in the cosmic order, no unsolved puzzle, no tailor-made niche that necessitated the muon's existence, the Nobel Prize-winning particle physicist Isidore Isaac Rabi greeted the discovery of the muon with a less than enthusiastic, "Who ordered that?" Nevertheless, there it was. And more was to follow. Using ever more powerful technology, physicists have continued to slam bits of matter together with ever-increasing energy, momentarily recreating conditions unseen since the Big Bang. In the debris, they have searched for new fundamental ingredients to add to the growing list of particles. Here is what they have found. 4 more quarks: charm, strange, bottom, and top, and another even heavier cousin of the electron called a tau, as well as 2 other particles with properties similar to the neutrino, called the muon neutrino and tau neutrino, to distinguish them from the original neutrino now called the electron neutrino. These particles are produced through high-energy collisions and exist only ephemerally. They are not constituents of anything we typically encounter. But even this is not quite the end of the story. Each of these particles has an antiparticle partner, a particle of identical mass but opposite in certain other respects such as its electric charge, as well as its charges with respect to other forces discussed below. For instance, the antiparticle of an electron is called a positron. It has exactly the same mass as an electron, but its electric charge is +1, whereas the electric charge of the electron is -1. When in contact, matter and antimatter can annihilate one another to produce pure energy. That's why there is extremely little naturally occurring antimatter in the world around us. Physicists have recognized a pattern among these particles displayed in Table 1.1. The matter particles neatly fall into 3 groups, which are often called families. Each family contains 2 of the quarks, an electron or one of its cousins, and one of the neutrino species. The corresponding particle types across the 3 families have identical properties except for their mass, which grows larger in each successive family. The upshot is that physicists have now probed the structure of matter to scales of about 1/1000th of a billionth of a meter, and shown that everything encountered to date, whether it occurs naturally or is produced artificially with giant atom smashers, consists of some combination of particles from these 3 families and their antimatter partners. A glance at Table 1.1 will no doubt leave you with an even stronger sense of Robbie's bewilderment at the discovery of the muon. The arrangement into families at least gives some semblance of order, but innumerable whys leap to the fore. Why are there so many fundamental particles, especially when it seems that the great majority of things in the world around us need only electrons, up quarks, and down quarks? Why are there 3 families? Why not 1 family or 4 families or any other number? Why do the particles have a seemingly random spread of masses? Why, for instance, does the tau weigh about 3,520 times as much as an electron? Why does the top quark weigh about 40,200 times as much an up quark? These are such strange, seemingly random numbers. Did they occur by chance, by some divine choice, or is there a comprehensible scientific explanation for these fundamental features of our universe? Things only become more complicated when we consider the forces of nature. The world around us is replete with means of exerting influence. Balls can be hit with bats. Bungee enthusiasts can throw themselves earthward from high platforms. Magnets can keep superfast trains suspended just above metallic tracks. Geiger counters can tick in response to radioactive material. Nuclear bombs can explode. We can influence objects by vigorously pushing, pulling, or shaking them, by hurling or firing other objects into them, by stretching, twisting, or crushing them, or by freezing, heating, or burning them. During the past 100 years, physicists have accumulated mounting evidence that all of these interactions between various objects and materials, as well as any of the millions upon millions of others encountered daily, can be reduced to combinations of 4 fundamental forces. One of these is the gravitational force. The other 3 are the electromagnetic force, the weak force, and the strong force. Gravity is the most familiar of the forces, being responsible for keeping us in orbit around the Sun, as well as for keeping our feet firmly planted on Earth. The mass of an object measures how much gravitational force it can exert as well as feel. The electromagnetic force is the next most familiar of the 4. It is the force driving all of the conveniences of modern life: lights, computers, TVs, telephones, and underlies the awesome might of lightning storms and the gentle touch of a human hand. Microscopically, the electric charge of a particle plays the same role for the electromagnetic force as mass does for gravity. It determines how strongly the particle can exert as well as respond electromagnetically. The strong and the weak forces are less familiar because their strength rapidly diminishes over all but subatomic distance scales. They are the nuclear forces. This is why these 2 forces were discovered only much more recently. The strong force is responsible for keeping quarks glued together inside of protons and neutrons, and keeping protons and neutrons tightly crammed together inside atomic nuclei. The weak force is best known as the force responsible for the radioactive decay of substances such as uranium and cobalt. During the past century, physicists have found 2 features common to all these forces. First, as we will discuss in Chapter 5, at a microscopic level, all the forces have an associated particle that you can think of as being the smallest packet or bundle of the force. If you fire a laser beam, an electromagnetic ray gun, you are firing a stream of photons, the smallest bundles of the electromagnetic force. Similarly, the smallest constituents of weak and strong force fields are particles called weak-gauge bosons and gluons. The name gluon is particularly descriptive. You can think of gluons as the microscopic ingredient in the strong glue holding atomic nuclei together. By 1984, experimenters had definitively established the existence and the detailed properties of these three kinds of force particles, recorded in Table 1.2. Physicists believe that the gravitational force also has an associated particle, the graviton, but its existence has yet to be confirmed experimentally. The second common feature of the forces is that just as mass determines how gravity affects a particle, and electric charge determines how the electromagnetic force affects it, particles are endowed with certain amounts of strong charge and weak charge that determine how they are affected by the strong and weak forces. These properties are detailed in the table in the endnotes to this chapter. But, as with particle masses, beyond the fact that experimental physicists have carefully measured these properties, no one has any explanation of why our universe is composed of these particular particles with these particular masses and force charges. Notwithstanding their common features, an examination of the fundamental forces themselves serves only to compound the questions. Why, for instance, are there 4 fundamental forces? Why not 5 or 3 or perhaps only 1? Why do the forces have such different properties? Why are the strong and weak forces confined to operate on microscopic scales, while gravity and the electromagnetic force have an unlimited range of influence? And why is there such an enormous spread in the intrinsic strength of these forces? To appreciate this last question, imagine holding an electron in your left hand and another electron in your right hand, and bringing these two identical electrically charged particles close together. Their mutual gravitational attraction will favor their getting closer, while their electromagnetic repulsion will try to drive them apart. Which is stronger? There is no contest. The electromagnetic repulsion is about 1,000,000 billion 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 billion, 10 to the 42 the mod, times stronger. If your right bicep represents the strength of the gravitational force, then your left bicep would have to extend beyond the edge of the known universe to represent the strength of the electromagnetic force. The only reason the electromagnetic force does not completely overwhelm gravity in the world around us is that most things are composed of an equal amount of positive and negative electric charges whose forces cancel each other out. On the other hand, since gravity is always attractive, there are no analogous cancellations. More stuff means greater gravitational force. But fundamentally speaking, gravity is an extremely feeble force. This fact accounts for the difficulty in experimentally confirming the existence of the graviton. Searching for the smallest bundle of the feeblest force is quite a challenge. Experiments also have shown that the strong force is about 100 times as strong as the electromagnetic force and about 100,000 times as strong as the weak force. But where is the rationale, the raison d'etre for our universe having these features? This is not a question born of idle philosophizing about why certain details happen to be one way instead of another. The universe would be a vastly different place if the properties of the matter and force particles were even moderately changed. For example, the existence of the stable nuclei forming the 100 or so elements of the periodic table hinges delicately on the ratio between the strengths of the strong and electromagnetic forces. The protons, crammed together in atomic nuclei, all repel one another electromagnetically. The strong force acting among their constituent quarks, thankfully, overcomes this repulsion and tethers the protons tightly together. But a rather small change in the relative strengths of these two forces would easily disrupt the balance between them, and would cause most atomic nuclei to disintegrate. Furthermore, were the mass of the electron a few times greater than it is, electrons and protons would tend to combine to form neutrons, gobbling up the nuclei of hydrogen, the simplest element in the cosmos with a nucleus containing a single proton, and, again, disrupting the production of more complex elements. Stars rely upon fusion between stable nuclei and would not form with such alterations to fundamental physics. The strength of the gravitational force also plays a formative role. The crushing density of matter in a star's central core powers its nuclear furnace and underlies the resulting blaze of starlight. If the strength of the gravitational force were increased, the stellar clump would bind more strongly, causing a significant increase in the rate of nuclear reactions. But just as a brilliant flare exhausts its fuel much faster than a slow-burning candle, an increase in the nuclear reaction rate would cause stars like the Sun to burn out far more quickly, having a devastating effect on the formation of life as we know it. On the other hand, where the strength of the gravitational force significantly decreased, matter would not clump together at all, thereby preventing the formation of stars and galaxies. We could go on, but the idea is clear. The universe is the way it is because the matter and the force particles have the properties they do. But is there a scientific explanation for why they have these properties? String theory. The basic idea. String theory offers a powerful conceptual paradigm in which, for the first time, a framework for answering these questions has emerged. Let's first get the basic idea. The particles in Table 1.1 are the letters of all matter. Just like their linguistic counterparts, they appear to have no further internal substructure. String theory proclaims otherwise. According to string theory, if we could examine these particles with even greater precision, a precision many orders of magnitude beyond our present technological capacity, we would find that each is not point-like, but instead consists of a tiny one-dimensional loop. Like an infinitely thin rubber band, each particle contains a vibrating, oscillating, dancing filament that physicists, lacking Gell-Mann's literary flair, have named a string. In Figure 1.1, we illustrate this essential idea of string theory by starting with an ordinary piece of matter, an apple, and repeatedly magnifying its structure to reveal its ingredients on ever smaller scales. String theory adds the new microscopic layer of a vibrating loop to the previously known progression from atoms through protons, neutrons, electrons, and quarks. Although it is by no means obvious, we will see in Chapter 6 that this simple replacement of point-particle material constituents with strings resolves the incompatibility between quantum mechanics and general relativity. String theory thereby unravels the central Gordian knot of contemporary theoretical physics. This is a tremendous achievement, but it is only a part of the reason string theory has generated such excitement. String theory as the unified theory of everything. In Einstein's day, the strong and the weak forces had not yet been discovered, but he found the existence of even two distinct forces, gravity and electromagnetism, deeply troubling. Einstein did not accept that nature is founded on such an extravagant design. This launched his 30-year voyage in search of the so-called unified field theory that he hoped would show that these two forces are really manifestations of one grand underlying principle. This quixotic quest isolated Einstein from the mainstream of physics, which, understandably, was far more excited about delving into the newly emerging framework of quantum mechanics. He wrote to a friend in the early 1940s, "I have become a lonely old chap who is mainly known because he doesn't wear socks and who is exhibited as a curiosity on special occasions." Einstein was simply ahead of his time. More than half a century later, his dream of a unified theory has become the holy grail of modern physics, and a sizable part of the physics and mathematics community is becoming increasingly convinced that string theory may provide the answer. From one principle, that everything at its most microscopic level consists of combinations of vibrating strands. String theory provides a single explanatory framework capable of encompassing all forces and all matter. String theory proclaims, for instance, that the observed particle properties, the data summarized in Tables 1.1 and 1.2, are a reflection of the various ways in which a string can vibrate. Just as the strings on a violin or on a piano have resonant frequencies at which they prefer to vibrate, patterns that our ears sense as various musical notes in their higher harmonics, the same holds true for the loops of string theory. But we will see that rather than producing musical notes, each of the preferred patterns of vibration of a string in string theory appears as a particle whose mass and force charges are determined by the string's oscillatory pattern. The electron is a string vibrating one way, the up quark is a string vibrating another way, and so on. Far from being a collection of chaotic experimental facts, particle properties in string theory are the manifestation of one and the same physical feature, the resonant patterns of vibration, the music, so to speak, of fundamental loops of string. The same idea applies to the forces of nature as well. We will see that force particles are also associated with particular patterns of string vibration, and hence everything, all matter and all forces, is unified under the same rubric of microscopic string oscillations, the notes that strings can play. For the first time in the history of physics, we therefore have a framework with the capacity to explain every fundamental feature upon which the universe is constructed. For this reason, string theory is sometimes described as possibly being the theory of everything, TOE, or the ultimate or final theory. These grandiose descriptive terms are meant to signify the deepest possible theory of physics, a theory that underlies all others, one that does not require or even allow for a deeper explanatory base. In practice, many string theorists take a more down-to-earth approach and think of a TOE in the more limited sense of a theory that can explain the properties of the fundamental particles and the properties of the forces by which they interact and influence one another. A staunch reductionist would claim that this is no limitation at all, and that in principle absolutely everything, from the Big Bang to daydreams, can be described in terms of underlying microscopic physical processes involving the fundamental constituents of matter. If you understand everything about the ingredients, the reductionist argues, you understand everything. The reductionist philosophy easily ignites heated debate. Many find it fatuous and downright repugnant to claim that the wonders of life and the universe are mere reflections of microscopic particles engaged in a pointless dance fully choreographed by the laws of physics. Is it really the case that feelings of joy, sorrow, or boredom are nothing but chemical reactions in the brain? Reactions between molecules and atoms that, even more microscopically, are reactions between some of the particles in Table 1.1, which are really just vibrating strings. In response to this line of criticism, Nobel laureate Steven Weinberg cautions, "In dreams of a final theory, at the other end of the spectrum are the opponents of reductionism who are appalled by what they feel to be the bleakness of modern science. To whatever extent they and their world can be reduced to a matter of particles or fields and their interactions, they feel diminished by that knowledge." I would not try to answer these critics with a pep talk about the beauties of modern science. The reductionist worldview is chilling and impersonal. It has to be accepted as it is, not because we like it, but because that is the way the world works. Some agree with this stark view, some don't. Others have tried to argue that developments such as chaos theory tell us that new kinds of laws come into play when the level of complexity of a system increases. Understanding the behavior of an electron or a quark is one thing. Using this knowledge to understand the behavior of a tornado is quite another. On this point, most agree. But opinions diverge on whether the diverse and often unexpected phenomena that can occur in systems more complex than individual particles truly represent new physical principles at work, or whether the principles involved are derivative, relying, albeit in a terribly complicated way, on the physical principles governing the enormously large number of elementary constituents. My own feeling is that they do not represent new and independent laws of physics. Although it would be hard to explain the properties of a tornado in terms of the physics of electrons and quarks, I see this as a matter of calculational impasse, not an indicator of the need for new physical laws. But again, there are some who disagree with this view. What is largely beyond question and is of primary importance to the journey described in this book is that even if one accepts the debatable reasoning of the staunch reductionist, principle is one thing and practice quite another. Almost everyone agrees that finding the TOE would in no way mean that psychology, biology, geology, chemistry, or even physics had been solved or in some sense subsumed. The universe is such a wonderfully rich and complex place that the discovery of the final theory, in the sense we are describing here, would not spell the end of science. Quite the contrary. The discovery of the TOE, the ultimate explanation of the universe at its most microscopic level, a theory that does not rely on any deeper explanation, would provide the firmest foundation on which to build our understanding of the world. Its discovery would mark a beginning, not an end. The ultimate theory would provide an unshakable pillar of coherence, forever assuring us that the universe is a comprehensible place, the state of string theory. The central concern of this book is to explain the workings of the universe according to string theory, with a primary emphasis on the implications that these results have for our understanding of space and time. Unlike many other exposés of scientific developments, the one given here does not address itself to a theory that has been completely worked out, confirmed by vigorous experimental tests and fully accepted by the scientific community. The reason for this, as we will discuss in subsequent chapters, is that string theory is such a deep and sophisticated theoretical structure that even with the impressive progress that has been made over the last 2 decades, we still have far to go before we can claim to have achieved full mastery. And so string theory should be viewed as a work in progress whose partial completion has already revealed astonishing insights into the nature of space, time, and matter. The harmonious union of general relativity and quantum mechanics is a major success. Furthermore, unlike any previous theory, string theory has the capacity to answer primordial questions having to do with nature's most fundamental constituents and forces. Of equal importance, although somewhat harder to convey, is the remarkable elegance of both the answers and the framework for answers that string theory proposes. For instance, in string theory, many aspects of nature that might appear to be arbitrary technical details, such as the number of distinct fundamental particle ingredients and their respective properties, are found to arise from essential and tangible aspects of the geometry of the universe. If string theory is right, the microscopic fabric of our universe is a richly intertwined multidimensional labyrinth within which the strings of the universe endlessly twist and vibrate, rhythmically beating out the laws of the cosmos. Far from being accidental details, the properties of nature's basic building blocks are deeply entwined with the fabric of space and time. In the final analysis, though, nothing is a substitute for definitive, testable predictions that can determine whether string theory has truly lifted the veil of mystery hiding the deepest truths of our universe. It may be some time before our level of comprehension has reached sufficient depth to achieve this aim, although, as we will discuss in Chapter 9, experimental tests could provide strong circumstantial support for string theory within the next 10 years or so. Moreover, in Chapter 13 we will see that string theory has recently solved a central puzzle concerning black holes, associated with the so-called Beakenstein-Hawking entropy, that has stubbornly resisted resolution by more conventional means for more than 25 years. This success has convinced many that string theory is in the process of giving us our deepest understanding of how the universe works. Edward Witten, one of the pioneers and leading experts in string theory, summarizes the situation by saying that string theory is a part of 21st century physics that fell by chance into the 20th century, an assessment first articulated by the celebrated Italian physicist Daniele Amati. In a sense, then, it is as if our forebears in the late 19th century had been presented with a modern-day supercomputer, without the operating instructions. Through inventive trial and error, hints of the supercomputer's power would have become evident, but it would have taken vigorous and prolonged effort to gain true mastery. The hints of the computer's potential, like our glimpses of string theory's explanatory power, would have provided extremely strong motivation for obtaining complete facility. A similar motivation today energizes a generation of theoretical physicists to pursue a full and precise analytic understanding of string theory. Witten's remark, and those of other experts in the field, indicate that it could be decades or even centuries before string theory is fully developed and understood. This may well be true. In fact, the mathematics of string theory is so complicated that, to date, no one even knows the exact equations of the theory. Instead, physicists know only approximations to these equations, and even the approximate equations are so complicated that they, as yet, have been only partially solved. Nevertheless, an inspiring set of breakthroughs in the latter half of the 1990s, breakthroughs that have answered theoretical questions of hitherto unimaginable difficulty, may well indicate that complete quantitative understanding of string theory is much closer than initially thought. Physicists worldwide are developing powerful new techniques to transcend the numerous approximate methods so far used, collectively piecing together disparate elements of the string theory puzzle at an exhilarating rate, Surprisingly, these developments are providing new vantage points for reinterpreting some of the basic aspects of the theory that have been in place for some time. For instance, a natural question that may have occurred to you in looking at Figure 1.1 is, why strings? Why not little frisbee disks? Or microscopic blob-like nuggets? Or a combination of all of these possibilities? As we shall see in Chapter 12, the most recent insights show that these other kinds of ingredients do have an important role in string theory, and have revealed that string theory is actually part of an even grander synthesis currently and mysteriously named M-theory. These latest developments will be the subject of the final chapters of this book. Progress in science proceeds in fits and starts. Some periods are filled with great breakthroughs. At other times, researchers experience dry spells. Scientists put forward results, both theoretical and experimental. The results are debated by the community. Sometimes they're discarded, sometimes they are modified, and sometimes they provide inspirational jumping-off points for new and more accurate ways of understanding the physical universe. In other words, science proceeds along a zigzag path toward what we hope will be ultimate truth. A path that began with humanity's earliest attempts to fathom the cosmos and whose end we cannot predict. Whether string theory is an incidental rest stop along this path, a landmark turning point, or in fact the final destination, we do not know. But the last 2 decades of research by hundreds of dedicated physicists and mathematicians from numerous countries have given us well-founded hope that we are on the right and possibly final track. It is a telling testament of the rich and far-reaching nature of string theory that even our present level of understanding has allowed us to gain striking new insights into the workings of the universe. A central thread in what follows will be those developments that carry forward the revolution in our understanding of space and time initiated by Einstein's special and general theories of relativity. We will see that if string theory is correct, the fabric of our universe has properties that would likely have dazzled even Einstein. Part 2. The Dilemma of Space, Time, and the Quanta. Chapter 2. Space, Time, and the Eye of the Beholder. In June 1905, 26-year-old Albert Einstein submitted a technical article to the Annals of Physics in which he came to grips with a paradox about light that had first troubled him as a teenager, some 10 years earlier. Upon turning the final page of Einstein's manuscript, the editor of the journal, Max Planck, realized that the accepted scientific order had been overthrown. Without hoopla or fanfare, a patent clerk from Bern, Switzerland, had completely overturned the traditional notions of space and time and replaced them with a new conception whose properties fly in the face of everything we are familiar with from common experience. The paradox that had troubled Einstein for a decade was this. In the mid-1800s, after a close study of the experimental work of the English physicist Michael Faraday, the Scottish physicist James Clerk Maxwell succeeded in uniting electricity and magnetism in the framework of the electromagnetic field. If you've ever been on a mountaintop just before a severe thunderstorm or stood close to a Van de Graaff generator, you have a visceral sense of what an electromagnetic field is because you felt it. In case you haven't, it is somewhat like a tide of electric and magnetic lines of force that permeate a region of space through which they pass. When you sprinkle iron filings near a magnet, for example, the orderly pattern they form traces out some of the invisible lines of magnetic force. When you take off a wool sweater on an especially dry day and hear a crackling sound and perhaps feel a momentary shock or two, you are witnessing evidence of electric lines of force generated by electric charges swept up by the fibers in your sweater. Beyond uniting these and all other electric and magnetic phenomena in one mathematical framework, Maxwell's theory showed, quite unexpectedly, that electromagnetic disturbances travel at a fixed and never-changing speed, a speed that turns out to equal that of light. From this, Maxwell realized that visible light itself is nothing but a particular kind of electromagnetic wave, one that is now understood to interact with chemicals in the retina, giving rise to the sensation of sight. Moreover, and this is crucial, Maxwell's theory also showed that all electromagnetic waves, visible light among them, are the epitome of the peripatetic traveler. They never stop. They never slow down. Light always travels at light speed. All is well and good until we ask, as the 16-year-old Einstein did, what happens if we chase after a beam of light at light speed? Intuitive reasoning, rooted in Newton's laws of motion, tells us that we will catch up with the light waves and so they will appear stationary. Light will stand still. But according to Maxwell's theory and all reliable observations, there is simply no such thing as stationary light. No one has ever held a stationary clump of light in the palm of his or her hand, hence the problem. Luckily, Einstein was unaware that many of the world's leading physicists were struggling with this question and were heading down many a spurious path, and pondered the paradox of Maxwell and Newton largely in the pristine privacy of his own thoughts. In this chapter, we discuss how Einstein resolved the conflict through his special theory of relativity, and in so doing forever changed our conceptions of space and time. It is perhaps surprising that the essential concern of special relativity is to understand precisely how the world appears to individuals, often called observers, who are moving relative to one another. At first, this might seem to be an intellectual exercise of minimal importance. Quite the contrary. In the hands of Einstein, with his imaginings of observers chasing after light beams, there are profound implications to grasping fully how even the most mundane situations appear to individuals in relative motion. Intuition and its flaws. Common experience highlights certain ways in which observations by such individuals differ. Trees alongside a highway, for example, appear to be moving from the viewpoint of a driver but appear stationary to a hitchhiker sitting on a guardrail. Similarly, the dashboard of the automobile does not appear to be moving from the viewpoint of the driver, one hopes, but like the rest of the car, it does appear to be moving from the viewpoint of the hitchhiker. These are such basic and intuitive properties of how the world works that we hardly take note of them. Special relativity, however, proclaims that the differences in observations between two such individuals are more subtle and profound. It makes the strange claim that observers in relative motion will have different perceptions of distance and of time. This means, as we shall see, that identical wristwatches worn by two individuals in relative motion will tick at different rates, and hence will not agree on the amount of time that elapses between chosen events. Special relativity demonstrates that this statement does not slander the accuracy of the wristwatches involved. Rather, it is a true statement about time itself. Similarly, observers in relative motion carrying identical tape measures will not agree on the lengths of distances measured. Again, this is not due to inaccuracies in the measuring devices or to errors in how they are used. The most accurate measuring devices in the world confirm that space and time, as measured by distances and durations, are not experienced identically by everyone. In the precise way delineated by Einstein, special relativity resolves the conflict between our intuition about motion and the properties of light. But there is a price. Individuals who are moving with respect to each other will not agree on their observations of either space or time. It has been almost a century since Einstein informed the world of his dramatic discovery. Yet most of us still see space and time in absolute terms. Special relativity is not in our bones, we do not feel it. Its implications are not a central part of our intuition. The reason for this is quite simple. The effects of special relativity depend upon how fast one moves, and at the speeds of cars, planes, or even space shuttles, these effects are minuscule. Differences in perceptions of space and of time between individuals planted on the Earth and those traveling in cars or planes do occur, but they are so small that they go unnoticed. However, were one to take a trip in a futuristic space vehicle traveling at a substantial fraction of light speed, the effects of relativity would become plainly obvious. This, of course, is still in the realm of science fiction. Nevertheless, as we shall discuss in later sections, clever experiments allow clear and precise observation of the relative properties of space and time predicted by Einstein's theory. To get a sense of the scales involved, imagine that the year is 1970 and big, fast cars are in. Slim, having just spent all his savings on a new Trans Am, goes with his brother Jim to the local drag strip to give the car the kind of test drive forbidden by the dealer. After revving up the car, Slim streaks down the mile-long strip at 120 miles per hour, while Jim stands on the sideline and times him. Wanting an independent confirmation, Slim also uses a stopwatch to determine how long it takes his new car to traverse the track. Prior to Einstein's work, no one would have questioned that if both Slim and Jim have properly functioning stopwatches, each will measure the identical elapsed time. But according to special relativity, while Jim will measure an elapsed time of 30 seconds, Slim's stopwatch will record an elapsed time of 29.9999999999995 seconds, a tiny bit less. Of course, this difference is so small that it could be detected only through a measurement whose accuracy is well beyond the capacity of handheld stopwatches run by the press of a finger, Olympic-quality timing systems, or even the most precisely engineered atomic clocks. It is no wonder that our everyday experiences do not reveal the fact that the passage of time depends upon our state of motion. There will be a similar disagreement on measurements of length. For example, on another test run, Jim uses a clever trick to measure the length of Slim's new car. He starts his stopwatch just as the front of the car reaches him, and he stops it just as the back of the car passes. Since Jim knows that Slim is speeding along at 120 miles per hour, he is able to figure out the length of the car by multiplying this speed by the elapsed time on his stopwatch. Again, prior to Einstein, no one would have questioned that the length Jim measures in this indirect way would agree exactly with the length Slim carefully measured when the car sat motionless on the showroom floor. Special relativity proclaims, on the contrary, that if Slim and Jim carry out precise measurements in this manner, and Slim finds the car to be, say, exactly 16 feet long, then Jim's measurement will find the car to be 15.9999999999997 feet long, a tiny bit less. As with the measurement of time, this is such a minuscule difference that ordinary instruments are just not accurate enough to detect it. Although the differences are extremely small, they show a fatal flaw in the commonly held conception of universal and immutable space and time. As the relative velocity of individuals such as Slim and Jim gets larger, this flaw becomes increasingly apparent. To achieve noticeable differences, the speeds involved must be a sizable fraction of the maximum possible speed, that of light, which Maxwell's theory and experimental measurements show to be about 186,000 miles per second, or about 670 million miles per hour. This is fast enough to circle the Earth more than 7 times in a second. If Slim, for example, were to travel not at 120 miles per hour but at 580 million miles per hour, about 87% of light speed, the mathematics of special relativity predicts that Jim would measure the length of the car to be about 8 feet, which is substantially different from Slim's measurement as well as the specifications in the owner's manual. Similarly, the time to traverse the drag strip according to Jim will be about twice as long as the time measured by Slim. Since such enormous speeds are far beyond anything currently attainable, the effects of time dilation and Lorentz contraction, as these phenomena are technically called, are extremely small in day-to-day life. If we happen to live in a world in which things typically traveled at speeds close to that of light, these properties of space and time would be so completely intuitive, since we would experience them constantly, that they would deserve no more discussion than the apparent motion of trees on the side of the road mentioned at the outset of this chapter. But since we don't live in such a world, these features are unfamiliar. As we shall see, understanding and accepting them requires that we subject our worldview to a thorough makeover. The principle of relativity. There are 2 simple yet deeply rooted structures that form the foundation of special relativity. As mentioned, one concerns properties of light. We shall discuss this more fully in the next section. The other is more abstract. It is concerned not with any specific physical law, but rather with all physical laws, and is known as the principle of relativity. The principle of relativity rests on a simple fact. Whenever we discuss speed or velocity, an object's speed and its direction of motion, we must specify precisely who or what is doing the measuring. Understanding the meaning and importance of this statement is easily accomplished by contemplating the following situation. Imagine that George, who is wearing a spacesuit with a small, red flashing light, is floating in the absolute darkness of completely empty space, far away from any planets, stars, or galaxies. From George's perspective, he is completely stationary, engulfed in the uniform, still blackness of the cosmos. Off in the distance, George catches sight of a tiny, green, flashing light that appears to be coming closer and closer. Finally, it gets close enough for George to see that the light is attached to the spacesuit of another space dweller, Gracie, who is slowly floating by. She waves as she passes, as does George, and she recedes into the distance. This story can be told with equal validity from Gracie's perspective. It begins in the same manner with Gracie, completely alone, in the immense, still darkness of outer space. Off in the distance, Gracie sees a red, flashing light, which appears to be coming closer and closer. Finally, it gets close enough for Gracie to see that it is attached to the spacesuit of another being, George, who is slowly floating by. He waves as he passes, as does Gracie, and he recedes into the distance. The two stories describe one and the same situation from two distinct but equally valid points of view. Each observer feels stationary and perceives the other as moving. Each perspective is understandable and justifiable. As there is symmetry between the two space dwellers, there is, on quite fundamental grounds, no way of saying one perspective is right and the other wrong. Each perspective has an equal claim on truth. This example captures the meaning of the principle of relativity. The concept of motion is relative. We can speak about the motion of an object, but only relative to or by comparison with another. There is thus no meaning to the statement, George is traveling at 10 miles per hour, as we have not specified any other object for comparison. There is meaning to the statement, George is traveling at 10 miles per hour past Gracie, as we have now specified Gracie as the benchmark. As our example shows, this last statement is completely equivalent to Gracie is traveling at 10 miles per hour past George in the opposite direction. In other words, there is no absolute notion of motion. Motion is relative. A key element of this story is that neither George nor Gracie is being pushed, pulled, or in any other way acted upon by a force or influence that could disturb their serene state of force-free, constant velocity motion. Thus, a more precise statement is that force-free motion has meaning only by comparison with other objects. This is an important clarification, because if forces are involved, they cause changes in the velocity of the observers, changes to their speed and/or their direction of motion, and these changes can be felt. For instance, if George were wearing a jetpack firing away from his back, he would definitely feel that he was moving. This feeling is intrinsic. If the jetpack is firing away, George knows he is moving, even if his eyes are closed and therefore can make no comparisons with other objects. Even without such comparisons, he would no longer claim that he was stationary while the rest of the world was moving by him. Constant velocity motion is relative, not so for non-constant velocity motion or, equivalently, accelerated motion. We will re-examine this statement in the next chapter when we take up accelerated motion and discuss Einstein's general theory of relativity. Setting these stories in the darkness of empty space aids understanding by removing such familiar things as streets and buildings, which we typically, although unjustifiably, accord the special status of stationary. Nonetheless, the same principle applies to terrestrial settings and in fact is commonly experienced. For example, imagine that after you have fallen asleep on a train, you awake just as your train is passing another on adjacent parallel tracks. With your view through the window completely blocked by the other train, thereby preventing you from seeing any other objects, you may temporarily be uncertain as to whether your train is moving, the other train is moving, or both. Of course, if your train shakes or jostles, or if the train changes direction by rounding a bend, you can feel that you're moving. But if the ride is perfectly smooth, if the train's velocity remains constant, you will observe relative motion between the trains without being able to tell for certain which is moving. Let's take this one step further. Imagine you are on such a train and that you pull down the shades so that the windows are fully covered. Without the ability to see anything outside your own compartment, and assuming that the train moves at absolutely constant velocity, there will be no way for you to determine your state of motion. The compartment around you will look precisely the same, regardless of whether the train is sitting still on the tracks or moving at high speed. Einstein formalized this idea, one that actually goes back to insights of Galileo, by proclaiming that it is impossible for you or any fellow traveler to perform an experiment within the closed compartment that will determine whether or not the train is moving. This again captures the principle of relativity. Since all force-free motion is relative, it has meaning only by comparison with other objects or individuals also undergoing force-free motion. There is no way for you to determine anything about your state of motion without making some direct or indirect comparison with outside objects. There simply is no notion of absolute constant velocity motion. Only comparisons have any physical meaning. In fact, Einstein realized that the principle of relativity makes an even grander claim. The laws of physics, whatever they may be, must be absolutely identical for all observers undergoing constant velocity motion. If George and Gracie are not just floating solo in space, but rather are each conducting the same set of experiments in their respective floating space stations, the results they find will be identical. Once again, each is perfectly justified in believing that his or her station is at rest, even though the two stations are in relative motion. If all of their equipment is identical, there is nothing distinguishing the two experimental setups. They are completely symmetric. The laws of physics that each deduces from the experiments will likewise be identical. Neither they nor their experiments can feel, that is, depend upon in any way constant velocity travel. It is this simple concept that establishes complete symmetry between such observers. It is this concept that is embodied in the principle of relativity. We shall shortly make use of this principle to profound effect. The speed of light. The second key ingredient in special relativity has to do with light and properties of its motion. Contrary to our claim that there is no meaning to the statement, George is traveling at 10 miles per hour, without a specified benchmark for comparison, almost a century of effort by a series of dedicated experimental physicists has shown that any and all observers will agree that light travels at 670 million miles per hour regardless of benchmarks for comparison. This fact has required a revolution in our view of the universe. Let's first gain an understanding of its meaning by contrasting it with similar statements applied to more common objects. Imagine it's a nice sunny day and you go outside to play a game of catch with a friend. For a while, you both leisurely throw the ball back and forth with a speed of, say, 20 feet per second, when suddenly an unexpected electrical storm stirs overhead, sending you both running for cover. After it passes, you rejoin to resume your game of catch, but you notice that something has changed. Your friend's hair has become wild and spiky, and her eyes have grown severe and crazed. When you look at her hand, you are stunned to see that she is no longer planning to play catch with a baseball, but instead is about to toss you a hand grenade. Understandably, your enthusiasm for playing catch diminishes substantially. You turn to run. When your companion throws the grenade, it will still fly toward you. But because you are running, the speed with which it approaches you will be less than 20 feet per second. In fact, common experience tells us that if you can run at, say, 12 feet per second, then the hand grenade will approach you at 12 8 feet per second. As another example, if you are in the mountains and an avalanche of snow is rumbling toward you, your inclination is to turn and run, because this will cause the speed with which the snow approaches you to decrease, and this, generally, is a good thing. Again, a stationary individual perceives the speed of the approaching snow to be greater than that perceived by someone in retreat. Now, let's compare these basic observations about baseballs, grenades, and avalanches to those about light. To make the comparisons tighter, think about a light beam as composed of tiny packets or bundles known as photons, a feature of light we will discuss more fully in Chapter 4. When we turn on a flashlight or a laser beam, we are, in effect, shooting a stream of photons in whatever direction we point the device. As we did for grenades and avalanches, let's consider how the motion of a photon appears to someone who is moving. Imagine that your crazed friend has swapped her grenade for a powerful laser. If she fires the laser toward you, and if you had the appropriate measuring equipment, you would find that the speed of approach of the photons in the beam is 670 million miles per hour. But what if you run away, as you did when faced with the prospect of playing catch with a hand grenade? what speed will you now measure for the approaching photons? To make things more compelling, imagine that you can hitch a ride on the Starship Enterprise and zip away from your friend at, say, 100 million miles per hour. Following the reasoning based on the traditional Newtonian worldview, since you are now speeding away, you would expect to measure a slower speed for the oncoming photons. Specifically, you would expect to find them approaching you at 670 million miles per hour, 100 million miles per hour equal sign, 570 million miles per hour. Mounting evidence from a variety of experiments dating back as far as the 1880s, as well as careful analysis and interpretation of Maxwell's electromagnetic theory of light, slowly convinced the scientific community that, in fact, this is not what you will see. Even though you are retreating, you will still measure the speed of the approaching photons as 670 million miles per hour, not a bit less. Although at first it sounds completely ridiculous. Unlike what happens if one runs from an oncoming baseball, grenade, or avalanche, the speed of approaching photons is always 670 million miles per hour. The same is true if you run toward oncoming photons or chase after them. Their speed of approach or recession is completely unchanged. They still appear to travel at 670 million miles per hour. Regardless of relative motion between the source of photons and the observer, the speed of light is always the same. Technological limitations are such that the experiments with light as described cannot actually be carried out. However, comparable experiments can. For instance, in 1913, the Dutch physicist Willem de Sitter suggested that fast-moving binary stars, two stars that orbit one another, could be used to measure the effect of a moving source on the speed of light. Various experiments of this sort over the past 8 decades have verified that the speed of light received from a moving star is the same as that from a stationary star, 670 million miles per hour, to within the impressive accuracy of ever more refined measuring devices. Moreover, a wealth of other detailed experiments has been carried out during the past century, experiments that directly measure the speed of light in various circumstances, as well as test many of the implications arising from this characteristic of light, as discussed shortly, and all have confirmed the constancy of the speed of light. If you find this property of light hard to swallow, you are not alone. At the turn of the century, physicists went to great length to refute it. They couldn't. Einstein, to the contrary, embraced the constancy of the speed of light, for here was the answer to the paradox that had troubled him since he was a teenager. No matter how hard you chase after a light beam, it still retreats from you at light speed. You can't make the apparent speed with which light departs 1 iota less than 670 million miles per hour, let alone slow it down to the point of appearing stationary. Case closed. But this triumph over paradox was no small victory. Einstein realized that the constancy of light's speed spelled the downfall of Newtonian physics, truth and consequences. Speed is a measure of how far an object can travel in a given duration of time. If we are in a car going 65 miles per hour, this means, of course, that we will travel 65 miles if we persist in this state of motion for an hour. Phrased in this manner, speed is a rather mundane concept, and you may wonder about the fuss we have made regarding the speed of baseballs, snowballs, and photons. However, let's note that distance is a notion about space. In particular, it is a measure of how much space there is between 2 points. Also note that duration is a notion about time, how much time elapses between 2 events. Speed, therefore, is intimately connected with our notions of space and time. When we phrase it this way, we see that any experimental fact that defies our common conception about speed, such as the constancy of the speed of light, has the potential to defy our common conceptions of space and time themselves. It is for this reason that the strange fact about the speed of light deserves detailed scrutiny given to it by Einstein, leading him to remarkable conclusions. The effect on time. Part 1. With minimal effort, we can make use of the constancy of the speed of light to show that the familiar everyday conception of time is plain wrong. Imagine that the leaders of 2 warring nations, sitting at opposite ends of a long negotiating table, have just concluded an agreement for a ceasefire, but neither wants to sign the accord before the other. The Secretary General of the United Nations comes up with a brilliant resolution. A light bulb, initially turned off, will be placed midway between the two presidents. When it is turned on, the light it emits will reach each of the presidents simultaneously, since they are equidistant from the bulb. Each president agrees to sign a copy of the accord when he or she sees the light. The plan is carried out, and the agreement is signed to the satisfaction of both sides. Flushed with success, the Secretary General makes use of the same approach with two other embattled nations that have also reached a peace agreement. The only difference is that the presidents involved in this negotiation are sitting at opposite ends of a table inside a train traveling along at constant velocity. Fittingly, the president of forward land is facing in the direction of the train's motion while the president of backward land is facing in the opposite direction. Familiar with the fact that the laws of physics take precisely the same form regardless of one's state of motion, so long as this motion is unchanging, the Secretary General takes no heed of this difference and carries out the light bulb-initiated signing ceremony as before. Both presidents sign the agreement and, along with their entourage of advisors, celebrate the end of hostilities. Just then, word arrives that fighting has broken out between people from each country who had been watching the signing ceremony from the platform outside the moving train. All those on the negotiation train are dismayed to hear that the reason for the renewed hostilities is the claim by people from forward land that they have been duped, as their president signed the agreement before the president of backward land. As everyone on the train, from both sides, agrees that the accord was signed simultaneously, how can it be that the outside observers watching the ceremony think otherwise? Let's consider in more detail the perspective of an observer on the platform. Initially, the bulb on the train is dark, and then at a particular moment it illuminates, sending beams of light speeding toward both presidents. From the perspective of a person on the platform, the president of forward land is heading toward the emitted light, while the president of backward land is retreating. This means to the platform observers that the light beam does not have to travel as far to reach the president of forward land, who moves toward the approaching light, as it does to reach the president of backward land, who moves away from it. This is not a statement about the speed of the light as it travels toward the two presidents. We have already noted that regardless of the state of motion of the source or the observer, the speed of light is always the same. Instead, we are describing only how far, from the vantage point of the platform observers, the initial flash of light must travel to reach each of the presidents. Since this distance is less for the president of forward land than it is for the president of backward land, and since the speed of light toward each is the same, the light will reach the president of forward land first. This is why the citizens of forward land claim to have been duped. When CNN broadcasts the eyewitness account, the Secretary General, the two presidents, and all of their advisors can't believe their ears. They all agree that the light bulb was secured firmly, exactly midway between the two presidents, and that therefore, without further ado, the light it emitted traveled the same distance to reach each of them. Since the speed of the emitted light to the left and to the right is the same, they believe, and in fact observed, that the light clearly reached each president simultaneously. Who is right, those on or off the train? The observations of each group and their supporting explanations are impeccable. The answer is that both are right. Like our two space inhabitants, George and Gracie, each perspective has an equal claim on truth. The only subtlety here is that the respective truths seem to be contradictory. An important political issue is at stake. Did the presidents sign the agreement simultaneously? The observations and reasoning above ineluctably lead us to the conclusion that according to those on the train they did, while according to those on the platform they did not. In other words, things that are simultaneous from the viewpoint of some observers will not be simultaneous from the viewpoint of others, if the two groups are in relative motion. This is a startling conclusion. It is one of the deepest insights into the nature of reality ever discovered. Nevertheless, if long after you set down this book, you remember nothing of this chapter except for the ill-fated attempt at détente, you will have retained the essence of Einstein's discovery. Without highbrow mathematics or a convoluted chain of logic, this completely unexpected feature of time follows directly from the constancy of the speed of light, as the scenario illustrates. Notice that if the speed of light were not constant but behaved according to our intuition based on slow-moving baseballs and snowballs, the platform observers would agree with those on the train. A platform observer would still claim that the photons have to travel farther to reach the president of backwardland than they do to reach the president of forwardland. However, usual intuition implies that the light approaching the president of backwardland would be moving more quickly, having received a kick from the forward-moving train. Similarly, these observers would see that the light approaching the president of forwardland would be moving more slowly, being dragged back by the train's motion. When these erroneous effects were considered, the observers on the platform would see that the light beams reached each president simultaneously. However, in the real world, light does not speed up or slow down. It cannot be kicked to a higher speed or dragged to a slower one. Platform observers will therefore justifiably claim that the light reached the president of forwardland first. The constancy of the speed of light requires that we give up the age-old notion that simultaneity is a universal concept that everyone, regardless of their state of motion, agrees upon. The universal clock, previously envisioned to dispassionately tick off identical seconds here on Earth and on Mars and on Jupiter, and in the Andromeda Galaxy, and in each and every nook and cranny of the cosmos, does not exist. On the contrary, observers in relative motion will not agree on which events occur at the same time. Once again, the reason that this conclusion, a bona fide characteristic of the world we inhabit, is so unfamiliar is that the effects are extremely small when the speeds involved are those commonly encountered in everyday experience. If the negotiating table were 100 feet long and the train were moving at 10 miles per hour, platform observers would see that the light reached the president of forwardland about a millionth of a billionth of a second before it reached the president of backwardland. Although this represents a genuine difference, it is so tiny that it cannot be detected directly by human senses. If the train were moving considerably faster, say at 600 million miles per hour, from the perspective of someone on the platform, the light would take almost 20 times as long to reach the president of backwardland compared with the time to reach the president of forwardland. At high speeds, the startling effects of special relativity become increasingly pronounced. The effect on time. Part 2. It is difficult to give an abstract definition of time. Attempts to do so often wind up invoking the word time itself, or else go through linguistic contortions simply to avoid doing so. Rather than proceeding down such a path, we can take a pragmatic viewpoint and define time to be that which is measured by clocks. Of course, this shifts the burden of definition to the word clock. Here we can somewhat loosely think of a clock as a device that undergoes perfectly regular cycles of motion. We will measure time by counting the number of cycles our clock goes through. A familiar clock, such as a wristwatch, meets this definition. It has hands that move in regular cycles of motion, and we do indeed measure elapsed time by counting the number of cycles or fractions thereof that the hands swing through between chosen events. Of course, the meaning of perfectly regular cycles of motion implicitly involves a notion of time, since regular refers to equal time durations elapsing for each cycle. From a practical standpoint, we address this by building clocks out of simple physical components that, on fundamental grounds, we expect to undergo repetitive cyclical evolutions that do not change in any manner from one cycle to the next. Grandfather clocks with pendulums that swing back and forth, and atomic clocks based on repetitive atomic processes provide simple examples. Our goal is to understand how motion affects the passage of time. And since we have defined time operationally in terms of clocks, we can translate our question into how motion affects the ticking of clocks. It is crucial to emphasize at the outset that our discussion is not concerned with how the mechanical elements of a particular clock happen to respond to shaking or jostling that might result from bumpy motion. In fact, we will consider only the simplest and most serene kind of motion, motion at absolutely constant velocity, and therefore there will not be any shaking or jostling at all. Rather, we are interested in the universal question of how motion affects the passage of time, and therefore how it fundamentally affects the ticking of any and all clocks, regardless of their particular design or construction. For this purpose, we introduce the world's conceptually simplest, yet most impractical clock. It is known as a light clock, and consists of two small mirrors mounted on a bracket facing one another, with a single photon of light bouncing back and forth between them. If the mirrors are about 6 inches apart, it will take the photon about a billionth of a second to complete one round-trip journey. Ticks on the light clock may be thought of as occurring every time the photon completes a round trip. A billion ticks means that 1 second has elapsed. We can use the light clock like a stopwatch to measure the time elapsed between events. We simply count how many ticks occur during the period of interest and multiply by the time corresponding to one tick. For instance, if we are timing a horse race and count that between the start and finish the number of round-trip photon journeys is 55 billion, we can conclude that the race took 55 seconds. The reason we use the light clock in our discussion is that its mechanical simplicity pares away extraneous details, and therefore provides us with the clearest insight into how motion affects the passage of time. To see this, imagine that we are idly watching the passage of time by looking at a ticking light clock placed on a nearby table. Then, all of a sudden, a second light clock slides by on the table, moving at constant velocity. The question we ask is whether the moving light clock will tick at the same rate as the stationary light clock. To answer the question, let's consider the path, from our perspective, that the photon in the sliding clock must take in order for it to result in a tick. The photon starts at the base of the sliding clock, as in Figure 2.2, and first travels to the upper mirror. Since, from our perspective, the clock is moving, the photon must travel at an angle, as shown in Figure 2.3. If the photon did not travel along this path, it would miss the upper mirror and fly off into space. As the sliding clock has every right to claim that it's stationary and everything else is moving, we know that the photon will hit the upper mirror, and hence the path we have drawn is correct. The photon bounces off the upper mirror and again travels a diagonal path to hit the lower mirror, and the sliding clock ticks. The simple but essential point is that the double diagonal path that we see the photon traverse is longer than the straight up and down path taken by the photon in the stationary clock. In addition to traversing the up and down distance, the photon in the sliding clock must also travel to the right, from our perspective. Moreover, the constancy of the speed of light tells us that the sliding clock's photon travels at exactly the same speed as the stationary clock's photon. But since it must travel farther to achieve one tick, it will tick less frequently. This simple argument establishes that the moving light clock, from our perspective, ticks more slowly than the stationary light clock. And since we have agreed that the number of ticks directly reflects how much time has passed, we see that the passage of time has slowed down for the moving clock. You might wonder whether this merely reflects some special feature of light clocks and would not apply to grandfather clocks or Rolex watches. Would time as measured by these more familiar clocks also slow down? The answer is a resounding yes, as can be seen by an application of the principle of relativity. Let's attach a Rolex watch to the top of each of our light clocks and rerun the preceding experiment. As discussed, a stationary light clock and its attached Rolex measure identical time durations, with a billion ticks on the light clock occurring for every 1 second of elapsed time on the Rolex. But what about the moving light clock and its attached Rolex? Does the rate of ticking on the moving Rolex slow down so that it stays synchronized with the light clock to which it is attached? Well, to make the point most forcefully, imagine that the light clock Rolex watch combination is moving because it is bolted to the floor of a windowless train compartment gliding along perfectly straight and smooth tracks at constant speed. By the principle of relativity, there is no way for an observer on this train to detect any influence of the train's motion. But if the light clock and Rolex were to fall out of synchronization, this would be a noticeable influence indeed. And so the moving light clock and its attached Rolex must still measure equal time durations. The Rolex must slow down in exactly the same way that the light clock does. Regardless of brand, type, or construction, clocks that are moving relative to one another record the passage of time at different rates. The light clock discussion also makes clear that the precise time difference between stationary and moving clocks depends on how much farther the sliding clock's photon must travel to complete each round-trip journey. This in turn depends on how quickly the sliding clock is moving. From the viewpoint of a stationary observer, the faster the clock is sliding, the farther the photon must travel to the right. We conclude that in comparison to a stationary clock, the rate of ticking of the sliding clock becomes slower and slower as it moves faster and faster. To get a sense of scale, note that the photon traverses one round trip in about a billionth of a second. For the clock to be able to travel an appreciable distance during the time for one tick, it must therefore be traveling enormously quickly. That is, some significant fraction of the speed of light. If it is traveling at more commonplace speeds like 10 miles per hour, the distance it can move to the right before one tick is completed is minuscule, just about 15 billionths of a foot. The extra distance that the sliding photon must travel is tiny, and it has a correspondingly tiny effect on the rate of ticking of the moving clock. And again, by the principle of relativity, this is true for all clocks, that is, for time itself. This is why beings such as ourselves who travel relative to one another at such slow speeds are generally unaware of the distortions in the passage of time. The effects, although present to be sure, are incredibly small. If, on the other hand, we were able to grab hold of the sliding clock and move with it at, say, 3/4 the speed of light, the equations of special relativity can be used to show that stationary observers would see our moving clock ticking at just about 2/3 the rate of their own. Significant effect indeed. Life on the run. We have seen that the constancy of the speed of light implies that a moving light clock ticks more slowly than a stationary light clock. And by the principle of relativity, this must be true not only for light clocks but also for any clock. It must be true of time itself. Time elapses more slowly for an individual in motion than it does for a stationary individual. If the fairly simple reasoning that has led us to this conclusion is correct, then, for instance, shouldn't one be able to live longer by being in motion rather than staying stationary? After all, if time elapses more slowly for an individual in motion than for an individual at rest, then this disparity should apply not just to time as measured by watches, but also to time as measured by heartbeats and the decay of body parts. This is the case, as has been directly confirmed, not with the life expectancy of humans, but with certain particles from the micro-world, muons. There is one important catch, however, that prevents us from proclaiming a newfound fountain of youth. When sitting at rest in the laboratory, muons disintegrate by a process closely akin to radioactive decay, in an average of about 2/millionths of a second. This disintegration is an experimental fact supported by an enormous amount of evidence. It's as if a muon lives its life with a gun to its head. When it reaches 2/millionths of a second in age, it pulls the trigger and explodes apart into electrons and neutrinos. But if these muons are not sitting at rest in the laboratory and instead are traveling through a piece of equipment known as a particle accelerator that boosts them to just shy of light speed, their average life expectancy as measured by scientists in the laboratory increases dramatically. This really happens. At 667 million miles per hour, about 99.5% of light speed, the muon lifetime is seen to increase by a factor of about 10. The explanation, according to special relativity, is that wristwatches worn by the muons tick much more slowly than the clocks in the laboratory. So long after the laboratory clocks say that the muon should have pulled their triggers and exploded, the watches on the fast-moving muons have yet to reach doom time. This is a very direct and dramatic demonstration of the effect of motion on the passage of time. If people were to zip around as quickly as these muons, their life expectancy would also increase by the same factor. Rather than living 70 years, people would live 700 years. Now for the catch. Although laboratory observers see fast-moving muons living far longer than their stationary brethren, this is due to time elapsing more slowly for the muons in motion. This slowing of time applies not just to the watches worn by the muons, but also to all activities they might undertake. For instance, if a stationary muon can read 100 books in its short lifetime, its fast-moving cousin will also be able to read the same 100 books, because although it appears to live longer than the stationary muon, its rate of reading, as well as everything else in its life, has slowed down as well. From the laboratory perspective, it's as if the moving muon is living its life in slow motion. From this viewpoint, the moving muon will live longer than a stationary one. But the amount of life the muon will experience is precisely the same. The same conclusion, of course, holds true for the fast-moving people with a life expectancy of centuries. From their perspective, it's life as usual. From our perspective, they are living life in hyper-slow motion, and therefore one of their normal life cycles takes an enormous amount of our time. Who is moving anyway? The relativity of motion is both the key to understanding Einstein's theory and a potential source of confusion. You may have noticed that a reversal of perspective interchanges the roles of the moving muons, whose watches we have argued run slowly, and their stationary counterparts. Just as both George and Gracie had an equal right to declare that they were stationary and that the other was moving, the muons we have described as being in motion are fully justified in proclaiming that, from their perspective, they are motionless and that it is the stationary muons that are moving, in the opposite direction. The arguments presented can be applied equally well from this perspective, leading to the seemingly opposite conclusion that watches worn by the muons we christened as stationary are running slow compared with those worn by the muons we described as moving. We have already met a situation, the signing ceremony with the light bulb, in which different viewpoints lead to results that seem to be completely at odds. In that case, we were forced by the basic reasoning of special relativity to give up the ingrained idea that everyone, regardless of state of motion, agrees about which events happen at the same time. The present incongruity, though, appears to be worse. How can two observers each claim that the other's watch is running slower? More dramatically, the different but equally valid muon perspectives seem to lead us to the conclusion that each group will claim that it is the other group that dies first. We are learning that the world can have some unexpectedly strange features, but we would hope that it does not cross into the realm of logical absurdity. So, what's going on? As with all apparent paradoxes arising from special relativity, under close examination, these logical dilemmas resolve to reveal new insights into the workings of the universe. To avoid ever more severe anthropomorphizing, let's switch from muons back to George and Gracie, who now, in addition to their flashing lights, have bright digital clocks on their spacesuits. From George's perspective, he is stationary, while Gracie, with her flashing green light and large digital clock, appears in the distance and then passes him in the blackness of empty space. He notices that Gracie's clock is running slow in comparison to his, with the rate of slowdown depending on how fast they pass one another. Were he a bit more astute, he would also note that in addition to the passage of time on her clock, everything about Gracie, the way she waves as she passes, the speed with which she blinks her eyes, and so on, is occurring in slow motion. From Gracie's perspective, exactly the same observations apply to George. Although this seems paradoxical, let's try to pinpoint a precise experiment that would reveal a logical absurdity. The simplest possibility is to arrange things so that when George and Gracie pass one another, they both set their clocks to read 12 o'clock. As they travel apart, each claims that the other's clock is running slower. To confront this disagreement head-on, George and Gracie must rejoin each other and directly compare the time elapsed on their clocks. But how can they do this? Well, George has a jetpack that he can use from his perspective to catch up with Gracie. But if he does this, the symmetry of their two perspectives, which is the cause of the apparent paradox, is broken, since George will have undergone accelerated, non-force-free motion. When they rejoin in this manner, less time will indeed have elapsed on George's clock, as he can now definitively say that he was in motion, since he could feel it. No longer are George's and Gracie's perspectives on equal footing. By turning on the jetpack, George relinquishes his claim to being at rest. If George chases after Gracie in this manner, the time difference that their clocks will show depends on their relative velocity and the details of how George uses his jetpack. As is by now familiar, if the speeds involved are small, the difference will be minuscule. But if substantial fractions of light speed are involved, the differences can be minutes, days, years, centuries, or more. As one concrete example, imagine that the relative speed of George and Gracie when they pass and are moving apart is 99.5% of light speed. Further, let's say that George waits 3 years, according to his clock, before firing up his jetpack for a momentary blast that sends him closing in on Gracie at the same speed that they were previously moving apart. 99.5% of light speed. When he reaches Gracie, 6 years will have elapsed on his clock, since it will take him 3 years to catch her. However, the mathematics of special relativity shows that 60 years will have elapsed on her clock. This is no sleight of hand. Gracie will have to search her distant memory some 60 years before to recall passing George in space. For George, on the other hand, it was a mere 6 years ago. In a real sense, George's motion has made him a time traveler, albeit in a very precise sense. He has traveled into Gracie's future. Getting the two clocks back together for direct comparison might seem to be merely a logistical nuisance, but it is really at the heart of the matter. We can imagine a variety of tricks to circumvent this chink in the paradox armor, but all ultimately fail. For instance, rather than bringing the clocks back together, what if George and Gracie compare their clocks by cellular telephone communication? If such communication were instantaneous, we would be faced with an insurmountable inconsistency. Reasoning from Gracie's perspective, George's clock is running slow and hence he must communicate less elapsed time. Reasoning from George's perspective, Gracie's clock is running slow and hence she must communicate less elapsed time. They both can't be right. And we would be sunk. The key point, of course, is that cell phones, like all forms of communication, do not transmit their signals instantaneously. Cell phones operate with radio waves, a form of light, and the signal they transmit, therefore, travels at light speed. This means that it takes time for the signals to be received. Just enough time delay, in fact, to make each perspective compatible with the other. Let's see this first from George's perspective. Imagine that every hour, on the hour, George recites into his cell phone, "It's 12 o'clock and all is well. It's 1 o'clock and all is well," and so forth. Since from his perspective Gracie's clock runs slow, at first blush he thinks that Gracie will receive these messages prior to her clock's reaching the appointed hour. In this way, he concludes, Gracie will have to agree that hers is the slow clock. But then he rethinks it. Since Gracie is receding from me, the signal I send to her by cell phone must travel ever longer distances to reach her. Maybe this additional travel time compensates for the slowness of her clock. George's realization that there are competing effects, the slowness of Gracie's clock versus the travel time of his signal, inspires him to sit down and quantitatively work out their combined effect. The result he finds is that the travel time effect more than compensates for the slowness of Gracie's clock. He comes to the surprising conclusion that Gracie will receive his signals proclaiming the passing of an hour on his clock after the appointed hour has passed on hers. In fact, since George is aware of Gracie's expertise in physics, he knows that she will take the signal's travel time into account when drawing conclusions about his clock based on his cell phone communications. A little more calculation quantitatively shows that even taking the travel time into account, Gracie's analysis of his signals will lead her to the conclusion that George's clock ticks more slowly than hers. Exactly the same reasoning applies when we take Gracie's perspective, with her sending out hourly signals to George. At first, the slowness of George's clock from her perspective leads her to think that he will receive her hourly messages prior to broadcasting his own. But when she takes into account the ever longer distances her signal must travel to catch George as he recedes into the darkness, she realizes that George will actually receive them after sending out his own. Once again, she realizes that even if George takes the travel time into account, he will conclude from Gracie's cell phone communications that her clock is running slower than his. So long as neither George nor Gracie accelerates, their perspectives are on precisely equal footing. Even though it seems paradoxical, in this way they both realize that it is perfectly consistent for each to think the other's clock is running slow. Motion's effect on space. The preceding discussion reveals that observers see moving clocks ticking more slowly than their own. That is, time is affected by motion. It is a short step to see that motion has an equally dramatic effect on space. Let's return to Slim and Jim on the drag strip. While in the showroom, as we mentioned, Slim had carefully measured the length of his new car with a tape measure. As Slim is speeding along the drag strip, Jim cannot apply this method to measure the length of the car, so he must proceed in an indirect manner. One such approach, as we indicated earlier, is this. Jim starts his stopwatch just when the front bumper of the car reaches him and stops it just as the rear bumper passes. By multiplying the elapsed time by the speed of the car, Jim can determine the car's length. Using our newfound appreciation of the subtleties of time, we realize that from Slim's perspective, he is stationary while Jim is moving, and hence Slim sees Jim's clock as running slow. As a result, Slim realizes that Jim's indirect measurement of the car's length will yield a shorter result than he measured in the showroom, since in Jim's calculation, length equals speed multiplied by elapsed time, Jim measures the elapsed time on a watch that is running slow. If it runs slow, the elapsed time he finds will be less, and the result of his calculation will be a shorter length. Thus, Jim will perceive the length of Slim's car, when it is in motion, to be less than its length when measured at rest. This is an example of the general phenomenon that observers perceive a moving object as being shortened along the direction of its motion. For instance, the equations of special relativity show that if an object is moving at about 98% of light speed, then a stationary observer will view it as being 80% shorter than if it were at rest. This phenomenon is illustrated. Motion through spacetime. The constancy of the speed of light has resulted in a replacement of the traditional view of space and time as rigid and objective structures with a new conception in which they depend intimately on the relative motion between observer and observed. We could end our discussion here, having realized that moving objects evolve in slow motion and are foreshortened. Special relativity, though, provides a more deeply unified perspective to encompass these phenomena. To understand this perspective, let's imagine a rather impractical automobile that rapidly attains its cruising speed of 100 miles per hour and sticks to this speed, no more, no less, until it is shut off and rolls to a halt. Let's also imagine that, due to his growing reputation as a skilled driver, Slim is asked to test drive the vehicle on a long, straight, and wide track in the middle of a flat stretch of desert. As the distance between the start and finish lines is 10 miles, the car should cover this distance in 1/10 of an hour, or 6 minutes. Jim, who moonlights as an automobile engineer, inspects the data recorded from dozens of test drives and is disturbed to see that although most were timed to be 6 minutes, the last few are a good deal longer. 6.5, and even 7.5 minutes. At first, he suspects a mechanical problem, since those times seem to indicate that the car was traveling slower than 100 miles per hour on the last 3 runs. Yet after examining the car extensively, he convinces himself that it is in perfect condition. Unable to explain the anomalously long times, he consults Slim and asks him about the final few runs. Slim has a simple explanation. He tells Jim that, since the track runs from east to west, as it got later in the day, the sun was glaring into his view. During the last 3 runs, it was so bad that he drove from one end of the track to the other at a slight angle. He draws a rough sketch of the path he took on the last 3 runs, and it is shown in Figure 2.5. The explanation for the 3 longer times is now perfectly clear. The path, from start to finish, is longer when traveling at an angle, and therefore, at the same speed of 100 miles per hour, it will take more time to cover. Put another way, when traveling at an angle, part of the 100 miles per hour is expended on going from south to north, leaving a bit less to accomplish the trip from east to west. This implies that it will take a little longer to traverse the strip. As stated, Slim's explanation is easy to understand. However, it is worth rephrasing it slightly for the conceptual leap we are about to take. The north-south and east-west directions are 2 independent spatial dimensions in which a car can move. It can also move vertically when traversing a mountain pass, for example, but we will not need that ability here. Slim's explanation illustrates that even though the car was traveling at 100 miles per hour on each and every run, during the last few runs it shared this speed between the 2 dimensions, and hence appeared to be going slower than 100 miles per hour in the east-west direction. During the previous runs, all 100 miles per hour were devoted to purely east-west motion. During the last three, part of this speed was used for north-south motion as well. Einstein found that precisely this idea, the sharing of motion between different dimensions, underlies all of the remarkable physics of special relativity. So long as we realize that not only can spatial dimensions share an object's motion, but the time dimension can share this motion as well. In fact, in the majority of circumstances, most of an object's motion is through time, not space. Let's see what this means. Motion through space is a concept we learn about early in life. Although we often don't think of things in such terms, we also learn that we, our friends, our belongings, and so forth, all move through time as well. When we look at a clock or a wristwatch, even while we idly sit and watch TV, the reading on the watch is constantly changing, constantly moving forward in time. We and everything around us are aging, inevitably passing from one moment in time to the next. In fact, the mathematician Hermann Minkowski, and ultimately Einstein as well, advocated thinking about time as another dimension of the universe, the fourth dimension, in some ways quite similar to the three spatial dimensions in which we find ourselves immersed. Although it sounds abstract, the notion of time as a dimension is actually concrete. When we want to meet someone, we tell them where in space we will expect to see them. For instance, the 9th floor of the building on the corner of 53rd Street and 7th Avenue. There are three pieces of information here: 9th floor, 53rd Street, 7th Avenue, reflecting a particular location in the three spatial dimensions of the universe. Equally important, however, is our specification of when we expect to meet them. For instance, at 3 p.m., this piece of information tells us where in time our meeting will take place. Events are therefore specified by four pieces of information: 3 in space and 1 in time. Such data, it is said, specifies the location of the event in space and in time, or in spacetime for short. In this sense, time is another dimension. Since this view proclaims that space and time are simply different examples of dimensions, can we speak of an object's speed through time in a manner resembling the concept of its speed through space? We can. A big clue for how to do this comes from a central piece of information we have already encountered. When an object moves through space relative to us, its clock runs slow compared to ours. That is, the speed of its motion through time slows down. Here's the leap. Einstein proclaimed that all objects in the universe are always traveling through space-time at one fixed speed, that of light. This is a strange idea. We are used to the notion that objects travel at speeds considerably less than that of light. We have repeatedly emphasized this as the reason relativistic effects are so unfamiliar in the everyday world. All of this is true. We are presently talking about an object's combined speed through all four dimensions, 3 space and 1 time, and it is the object's speed in this generalized sense that is equal to that of light. To understand this more fully and to reveal its importance, we note that, like the impractical single-speed car discussed above, this one fixed speed can be shared between the different dimensions. Different space and time dimensions, that is. If an object is sitting still, relative to us, and consequently does not move through space at all, then, in analogy to the first runs of the car, all of the object's motion is used to travel through one dimension, in this case, the time dimension. Moreover, all objects that are at rest relative to us and to each other move through time, they age, at exactly the same rate or speed. If an object does move through space, however, this means that some of the previous motion through time must be diverted. Like the car traveling at an angle, this sharing of motion implies that the object will travel more slowly through time than its stationary counterparts, since some of its motion is now being used to move through space. That is, its clock will tick more slowly if it moves through space. This is exactly what we found earlier. We now see that time slows down when an object moves relative to us because this diverts some of its motion through time into motion through space. The speed of an object through space is thus merely a reflection of how much of its motion through time is diverted. We also see that this framework immediately incorporates the fact that there is a limit to an object's spatial velocity. The maximum speed through space occurs if all of an object's motion through time is diverted to motion through space. This occurs when all of its previous light-speed motion through time is diverted to light-speed motion through space. But having used up all of its motion through time, this is the fastest speed through space that the object, any object, can possibly achieve. This is analogous to our car being test-driven directly in the north-south direction. Just as the car will have no speed left for motion in the east-west dimension, something traveling at light speed through space will have no speed left for motion through time. Thus light does not get old. A photon that emerged from the Big Bang is the same age today as it was then. There is no passage of time at light speed. E equals m times c squared. Although Einstein did not advocate calling his theory relativity, suggesting instead the name invariance theory to reflect the unchanging character of the speed of light, among other things, the meaning of the term is now clear. Einstein's work showed that concepts such as space and time, which had previously seemed to be separate and absolute, are actually interwoven and relative. Einstein went on to show that other physical properties of the world are unexpectedly interwoven as well. His most famous equation provides one of the most important examples. In it, Einstein asserted that the energy, E of an object, and its mass, m, are not independent concepts. We can determine the energy from knowledge of the mass, by multiplying the latter twice by the speed of light, ci2, or we can determine the mass from knowledge of the energy, by dividing the latter twice by the speed of light. In other words, energy and mass, like dollars and francs, are convertible currencies. Unlike money, however, the exchange rate given by two factors of the speed of light is always and forever fixed. Since this exchange rate factor is so large, C2 is a big number, a little mass goes an extremely long way in producing energy. The world grasped the devastating destructive power arising from the conversion of less than 1% of 2 pounds of uranium into energy at Hiroshima. One day, through fusion power plants, we may productively use Einstein's formula to meet the energy demands of the whole world with our endless supply of seawater. From the viewpoint of the concepts we have emphasized in this chapter, Einstein's equation gives us the most concrete explanation for the central fact that nothing can travel faster than light speed. You may have wondered, for instance, why we can't take some object, a muon say, that an accelerator has boosted up to 667 million miles per hour, 99.5% of light speed, and push it a bit harder, getting it to 99.9% of light speed, and then really push it harder, impelling it to cross the light speed barrier. Einstein's formula explains why such efforts will never succeed. The faster something moves, the more energy it has, and from Einstein's formula we see that the more energy something has, the more massive it becomes. Muons traveling at 99.9% of light speed, for example, weigh a lot more than their stationary cousins. In fact, they are about 22 times as heavy, literally. The masses recorded in Table 1.1 are for particles at rest. But the more massive an object is, the harder it is to increase its speed. Pushing a child on a bicycle is one thing. Pushing a Mack truck is quite another. So, as a muon moves more quickly, it gets ever more difficult to further increase its speed. At 99.999% of light speed, the mass of a muon has increased by a factor of 224. At 99.9999999% of light speed, it has increased by a factor of more than 70,000. Since the mass of the muon increases without limit as its speed approaches that of light, it would require a push with an infinite amount of energy to reach or to cross the light barrier. This, of course, is impossible, and hence absolutely nothing can travel faster than the speed of light. As we shall see in the next chapter, this conclusion plants the seeds for the second major conflict faced by physics during the past century and ultimately spells doom for another venerable and cherished theory, Newton's universal theory of gravity. Chapter 3. Of Warps and Ripples. Through special relativity, Einstein resolved the conflict between the age-old intuition about motion and the constancy of the speed of light. In short, the solution is that our intuition is wrong. It is informed by motion that typically is extremely slow compared to the speed of light, and such low speeds obscure the true character of space and time. Special relativity reveals their nature and shows them to differ radically from previous conceptions. Tinkering with our understanding of the foundations of space and time, though, was no small undertaking. Einstein soon realized that of the numerous reverberations following from the revelations of special relativity, one was especially profound. The dictum that nothing can outrun light proves to be incompatible with Newton's revered universal theory of gravity, proposed in the latter half of the 17th century. And so, while resolving one conflict, special relativity gave rise to another. After a decade of intense, sometimes tormented study, Einstein resolved the dilemma with his general theory of relativity. In this theory, Einstein once again revolutionized our understanding of space and time by showing that they warp and distort to communicate the force of gravity. Newton's view of gravity. Isaac Newton, born in 1642 in Lincolnshire, England, changed the face of scientific research by bringing the full force of mathematics to the service of physical inquiry. Newton's was such a monumental intellect that, for example, when he found that the mathematics required for some of his investigations did not exist, he invented it. Nearly 3 centuries would pass before the world would host a comparable scientific genius. Of Newton's numerous profound insights into the workings of the universe, the one that primarily concerns us here is his universal theory of gravity. The force of gravity pervades everyday life. It keeps us and all of the objects around us fixed to the Earth's surface. It keeps the air we breathe from escaping to outer space. It keeps the moon in orbit around the Earth, and it keeps the Earth bound in orbit around the sun. Gravity dictates the rhythm of the cosmic dance that is tirelessly and meticulously executed by billions upon billions of cosmic inhabitants, from asteroids to planets to stars to galaxies. More than 3 centuries of Newton's influence causes us to take for granted that a single force, gravity, is responsible for this wealth of terrestrial and extraterrestrial happenings. But before Newton, there was no understanding that an apple falling to Earth from a tree bore witness to the same physical principle that keeps the planets revolving around the sun. With an audacious step in the service of scientific hegemony, Newton united the physics governing both heaven and earth, and declared the force of gravity to be the invisible hand at work in each realm. Newton's view of gravity might be called the great equalizer. He declared that absolutely everything exerts an attractive gravitational force on absolutely everything else. Regardless of physical composition, everything exerts as well as feels the force of gravity. Based on a close study of Johannes Kepler's analysis of planetary motion, Newton deduced that the strength of the gravitational attraction between 2 bodies depends on precisely 2 things: the amount of stuff composing each of the bodies and the distance between them. Stuff means matter. This comprises the total number of protons, neutrons, and electrons, which in turn determines the mass of the object. Newton's universal theory of gravity asserts that the strength of attraction between 2 objects is larger for larger mass objects and smaller for smaller mass objects. It also asserts that the strength of attraction is larger for smaller separations between the objects and smaller for larger separations. Newton went much further than this qualitative description and wrote down equations that quantitatively describe the strength of the gravitational force between 2 objects. In words, these equations state that the gravitational force between 2 bodies is proportional to the product of their masses, and inversely proportional to the square of the distance between them. This law of gravity can be used to predict the motion of planets and comets around the Sun, the Moon about the Earth, and rockets heading off for planetary explorations, as well as more Earth-bound applications such as baseballs flying through the air and divers spiraling poolward from springboards. The agreement between the predictions and the actual observed motion of such objects is spectacular. This success gave Newton's theory unequivocal support until the early part of the 20th century. Einstein's discovery of special relativity, however, raised what proved to be an insurmountable obstacle for Newton's theory: the incompatibility of Newtonian gravity and special relativity. A central feature of special relativity is the absolute speed barrier set by light. It is important to realize that this limit applies not only to material objects but also to signals and influences of any kind. There is simply no way to communicate information or a disturbance from one place to another at faster than light speed. Of course, the world is full of ways for transmitting disturbances at slower than the speed of light. Your speech and all other sounds, for example, are carried by vibrations that travel at about 700 miles per hour through air, a feeble rate compared with light's 670 million miles per hour. This speed difference becomes obvious when you watch a baseball game, for instance, from seats that are far from home plate. When a batter hits the ball, the sound reaches you moments after you see the ball being hit. A similar thing happens in a thunderstorm, although lightning and thunder are produced simultaneously. You see the lightning before hearing the thunder. Again, this reflects the substantial speed difference between light and sound. The success of special relativity informs us that the reverse situation, in which some signal reaches us before the light it emits, is just not possible. Nothing outruns photons. Here's the rub. In Newton's theory of gravity, one body exerts a gravitational pull on another with a strength determined solely by the mass of the objects involved and the magnitude of their separation. The strength has nothing to do with how long the objects have been in each other's presence. This means that if their mass or their separation should change, the objects will, according to Newton, immediately feel a change in their mutual gravitational attraction. For instance, Newton's theory of gravity claims that if the Sun were suddenly to explode, the Earth, some 93 million miles away, would instantaneously suffer a departure from its usual elliptical orbit. Even though it would take light from the explosion 8 minutes to travel from the Sun to the Earth, in Newton's theory, knowledge that the Sun had exploded would be instantaneously transmitted to the Earth through the sudden change in the gravitational force governing its motion. This conclusion is in direct conflict with special relativity, since the latter ensures that no information can be transmitted faster than the speed of light. Instantaneous transmission violates this precept maximally. In the early part of the 20th century, therefore, Einstein realized that the tremendously successful Newtonian theory of gravity was in conflict with his special theory of relativity. Confident in the veracity of special relativity and notwithstanding the mountain of experimental support for Newton's theory, Einstein sought a new theory of gravity compatible with special relativity. This ultimately led him to the discovery of general relativity, in which the character of space and time again went through a remarkable transformation. Einstein's happiest thought. Even before the discovery of special relativity, Newton's theory of gravity was lacking in one important respect. Although it can be used to make highly accurate predictions about how objects will move under the influence of gravity, it offers no insight into what gravity is. That is, how is it that two bodies that are physically separate from another, possibly hundreds of millions of miles apart if not more, nonetheless influence each other's motion? By what means does gravity execute its mission? This is a problem of which Newton himself was well aware. In his own words, it is inconceivable that inanimate brute matter should, without the mediation of something else, which is not material, operate upon and affect other matter without mutual contact. That gravity should be innate, inherent, and essential to matter so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial, I have left to the consideration of my readers. That is, Newton accepted the existence of gravity and went on to develop equations that accurately describe its effects, but he never offered any insight into how it actually works. He gave the world an owner's manual for gravity, which delineated how to use it, instructions that physicists, astronomers, and engineers have exploited successfully to plot the course of rockets to the Moon, Mars, and other planets in the solar system, to predict solar and lunar eclipses, to predict the motion of comets, and so on. But he left the inner workings, the contents of the black box of gravity, a complete mystery. When you use your CD player or your personal computer, you may find yourself in a similar state of ignorance regarding how it works internally. So long as you know how to operate the equipment, neither you nor anyone else needs to know how it accomplishes the tasks you set for it. But if your CD player or personal computer breaks, its repair relies crucially on knowledge of its internal workings. Similarly, Einstein realized that hundreds of years of experimental confirmation notwithstanding, special relativity implied that in some subtle way Newton's theory was broken, and that its repair required coming to grips with the question of the true and full nature of gravity. In 1907, while pondering these issues at his desk in the patent office in Bern, Switzerland, Einstein had the central insight that, through fits and starts, would eventually lead him to a radically new theory of gravity, an approach that would not merely fill in the gap in Newton's theory, but rather would completely reformulate thinking about gravity, and of utmost importance, would do so in a manner fully consistent with special relativity. The insight Einstein had is relevant for a question that may have troubled you in Chapter 2. There we emphasize that we were interested in understanding how the world appears to individuals undergoing constant velocity relative motion. By carefully comparing the observations of such individuals, we found some dramatic implications for the nature of space and time. But what about individuals who are experiencing accelerated motion? The observations of such individuals will be more complicated to analyze than those of constant velocity observers, whose motion is more serene. But nevertheless, we can ask whether there is some way of taming this complexity and bringing accelerated motion squarely into our newfound understanding of space and time. Einstein's happiest thought showed how to do so. To understand his insight, imagine the year is 2050. You are the FBI's chief explosives expert, and you have just received a frantic call to investigate what appears to be a sophisticated bomb planted in the heart of Washington, D.C. After rushing to the scene and examining the device, your worst nightmare is confirmed. The bomb is nuclear and of such powerful design that even if it were buried deeply in the Earth's crust or submerged in an ocean's depth, the damage from its blast would be devastating. After gingerly studying the bomb's detonation mechanism, you realize that there is no hope to disarm it, and so in fact we can keep the actual reading on the scale from changing at all. Albert's suggestion slowly begins to make sense. In other words, you respond, an upward acceleration can provide a stand-in or a substitute for gravity. We can imitate the effect of gravity through suitably accelerated motion. Exactly, responds Albert. So, you continue, we can launch the bomb into space, and by judiciously adjusting the acceleration of the rocket, we can ensure that the reading on the scale does not change, thus avoiding detonation until it is a safe distance from Earth. And so, by playing off gravity and accelerated motion, using the precision of 21st century rocket science, you are able to stave off disaster. The recognition that gravity and accelerated motion are profoundly interwoven is the key insight that Einstein had one happy day in the Bern patent office. Although the bomb experience highlights the essence of his idea, it is worth rephrasing it in a framework closer to that of Chapter 2. For this purpose, recall that if you are put into a sealed, windowless compartment that is not accelerating, there is no way for you to determine your speed. The compartment looks the same, and any experiments you do yield identical results regardless of how fast you are moving. More fundamentally, without outside benchmarks for comparison, there is no way that a velocity can even be assigned to your state of motion. On the other hand, if you are accelerating, then even with your perceptions limited to the confines of your sealed compartment, you will feel a force on your body. For instance, if your forward-facing chair is bolted to the floor and your compartment is being accelerated forward, you will feel the force of your seat on your back, just as with the car described by Albert. Similarly, if your compartment is being accelerated upward, you will feel the force of the floor on your feet. Einstein's realization was that within the confines of your tiny compartment, you will not be able to distinguish these accelerated situations from ones without acceleration, but with gravity. When their magnitudes are judiciously adjusted, the force you feel from a gravitational field or from accelerated motion are indistinguishable. If your compartment is placidly sitting upright on the Earth's surface, you will feel the familiar force of the floor on your feet, just as in the scenario of upward acceleration. This is exactly the same equivalence Albert exploited in his solution for launching the terrorist bomb into space. If your compartment is resting on its back end, you will feel the force of your seat on your back, preventing you from falling, just as when you were accelerating horizontally. Einstein called the indistinguishability between accelerated motion and gravity the equivalence principle. This description shows that general relativity finishes a job initiated by special relativity. Through its principle of relativity, the special theory of relativity declares a democracy of observational vantage points. The laws of physics appear identical to all observers undergoing constant velocity motion. But this is limited democracy indeed, for it excludes an enormous number of other viewpoints, those of individuals who are accelerating. Einstein's 1907 insight now shows us how to embrace all points of view, constant velocity and accelerating, within one egalitarian framework. Since there is no difference between an accelerated vantage point without a gravitational field and a non-accelerated vantage point with a gravitational field, we can invoke the latter perspective and declare that all observers, regardless of their state of motion, may proclaim that they are stationary and the rest of the world is moving by them, so long as they include a suitable gravitational field in the description of their own surroundings. In this sense, through the inclusion of gravity, general relativity ensures that all possible observational vantage points are on equal footing. As we shall see later, this means that distinctions between observers in Chapter 2 that relied on accelerated motion, as when George chased after Gracie by turning on his jetpack and aged less than she, admit an equivalent description without acceleration, but with gravity. This deep connection between gravity and accelerated motion is certainly a remarkable realization, but why did it make Einstein so happy? The reason, simply put, is that gravity is mysterious. It is a grand force permeating the life of the cosmos, but it is elusive and ethereal. On the other hand, accelerated motion, although somewhat more complicated than constant velocity motion, is concrete and tangible. By finding a fundamental link between the two, Einstein realized that he could use his understanding of motion as a powerful tool toward gaining a similar understanding of gravity. Putting this strategy into practice was no small task even for the genius of Einstein, but ultimately this approach bore the fruit of general relativity. Achieving this end required that Einstein forge a second link in the chain uniting gravity and accelerated motion, the curvature of space and time, to which we now turn. Acceleration and the warping of space and time. Einstein worked on the problem of understanding gravity with extreme, almost obsessive, intensity. About 5 years after his happy revelation in the Bern Patent Office, he wrote to the physicist Arnold Sommerfeld, "I am now working exclusively on the gravity problem. One thing is certain that never in my life have I tormented myself anything like this. Compared to this problem, the original, that is, special relativity theory, is child's play." He appears to have made the next key breakthrough, a simple yet subtle consequence of applying special relativity to the link between gravity and accelerated motion in 1912. To understand this step in Einstein's reasoning, it is easiest to focus, as apparently he did, on a particular example of accelerated motion. Recall that an object is accelerating if either the speed or the direction of its motion changes. For simplicity, we will focus on accelerated motion in which only the direction of our object's motion changes while its speed stays fixed. Specifically, we consider motion in a circle such as what one experiences on the tornado ride in an amusement park. In case you have never tested the stability of your constitution on this ride, you stand with your back against the inside of a circular plexiglass structure that spins at a high speed. Like all accelerated motion, you can feel this motion. You feel your body being pulled radially away from the ride's center, and you feel the circular wall of plexiglass pressing on your back, keeping you moving in a circle. In fact, although not relevant for the present discussion, the spinning motion pins your body to the plexiglass with such a force that when the ledge on which you're standing drops away, you do not slip downward. If the ride is extremely smooth and you close your eyes, the pressure of the ride on your back, like the support of a bed, can almost make you feel that you are lying down. The almost comes from the fact that you still feel ordinary vertical gravity, so your brain cannot be fully fooled. But if you were to ride the tornado in outer space, and if it were to spin at just the right rate, it would feel just like lying in a stationary bed on Earth. Moreover, were you to get up and walk along the interior of the spinning plexiglass, your feet would press against it just as they do against an earthbound floor. In fact, space stations are designed to spin in this manner to create an artificial feeling of gravity in outer space. Having used the accelerated motion of the spinning tornado to imitate gravity, we can now follow Einstein and set out to see how space and time appear to someone on the ride. His reasoning, adapted to this situation, went as follows. We stationary observers can easily measure the circumference and the radius of the spinning ride. For instance, to measure the circumference, we can carefully lay out a ruler head to tail alongside the ride's spinning girth. For its radius, we can similarly use the head-to-tail method, working our way from the central axle of the ride to its outer rim. As we anticipate from high school geometry, we find that their ratio is 2 times the number pi, about 6.28, just as it is for any circle drawn on a flat sheet of paper. But what do things look like from the perspective of someone on the ride itself? To find out, we ask Slim and Jim, who are currently enjoying a spin on the tornado, to take a few measurements for us. We toss one of our rulers to Slim, who sets out to measure the circumference of the ride, and another to Jim, who sets out to measure the radius. To get the clearest perspective, let's take a bird's-eye view of the ride. We have adorned this snapshot of the ride with an arrow that indicates the momentary direction of motion at each point. As Slim begins to measure the circumference, we immediately see from our bird's-eye perspective that he is going to get a different answer than we did. As he lays the ruler out along the circumference, we notice that the ruler's length is shortened. This is nothing but the Lorentz contraction discussed in Chapter 2, in which the length of an object appears shortened along the direction of its motion. A shorter ruler means that he will have to lay it out, head to tail, more times to traverse the whole circumference. Since he still considers the ruler to be 1 foot long, since there is no relative motion between Slim and his ruler, he perceives it as having its usual length of 1 foot. This means that Slim will measure a longer circumference than did we. What about the radius? Well, Jim also uses the head-to-tail method to find the length of a radial strut, and from our bird's-eye view we see that he is going to find the same answer as we did. The reason is that the ruler is not pointing along the instantaneous direction of the motion of the ride, as it is when measuring the circumference. Since he still considers the ruler to be 1 foot long, since there is no relative motion between Slim and his ruler, he perceives it as having its usual length of 1 foot. This means that Slim will measure a longer circumference than did we. What about the radius? Well, Jim also uses the head-to-tail method to find the length of a radial strut, and from our bird's-eye view we see that he is going to find the same answer as we did. The reason is that the ruler is not pointing along the instantaneous direction of the motion of the ride, as it is when measuring the circumference. Instead, it is pointed at a 90-degree angle to the motion, and therefore it is not contracted along its length. Jim will therefore find exactly the same radial length as we did. But now, when Slim and Jim calculate the ratio of the circumference of the ride to its radius, they will get a number that is larger than our answer of 2 times pi, since the circumference is longer but the radius is the same. This is weird. How in the world can something in the shape of a circle violate the ancient Greek realization that for any circle this ratio is exactly 2 times pi? Here is Einstein's explanation. The ancient Greek result holds true for circles drawn on a flat surface. But just as the warped or curved mirrors in an amusement park funhouse distort the normal spatial relationships of your reflection, if a circle is drawn on a warped or curved surface, its usual spatial relationships will also be distorted. The ratio of its circumference to its radius will generally not be 2 times pi. For instance, Figure 3.2 compares 3 circles whose radii are identical. Notice, however, that their circumferences are not the same. The circumference of the circle in B, drawn on the curved surface of a sphere, is less than the circumference of the circle drawn on the flat surface in A, even though they have the same radius. The curved nature of the sphere's surface causes the radial lines of the circle to converge toward each other slightly, resulting in a small decrease in the circle's circumference. The circumference of the circle in C, again drawn on a curved surface, a saddle shape, is greater than that drawn on a flat surface. The curved nature of the saddle's surface causes the radial lines of the circle to splay outward from each other slightly, resulting in a small increase in the circle's circumference. These observations imply that the ratio of the circumference to the radius of the circle in B will be less than 2 times pi, while the same ratio in C will be greater than 2 times pi. But this deviation from 2 times pi, especially the larger value found in C, is just what we found for the spinning tornado ride. This led Einstein to propose an idea, the curving of space, as an explanation for the violation of ordinary Euclidean geometry. The flat geometry of the Greeks, taught to schoolchildren for thousands of years, simply does not apply to someone on the spinning ride. Rather, its curved space generalization, as schematically drawn in Part C of Figure 3.2, takes its place. And so Einstein realized that the familiar geometrical spatial relationships codified by the Greeks, relationships that pertain to flat space figures like a circle on a flat table, do not hold from the perspective of an accelerated observer. Of course, we have discussed only one particular kind of accelerated motion, but Einstein showed that a similar result, the warping of space, holds in all instances of accelerated motion. In fact, accelerated motion not only results in a warping of space, it also results in an analogous warping of time. Historically, Einstein first focused on the warping of time and subsequently realized the importance of the warping of space. On one level, it should not be too surprising that time is also affected, since we have already seen in Chapter 2 that special relativity articulates a union between space and time. This merger was summarized by the poetic words of Minkowski, who during a lecture on special relativity in 1908 said, "Henceforward, space on its own and time on its own will decline into mere shadows, and only a kind of union between the two will preserve its independence." In more down-to-earth but similarly imprecise language, by knitting space and time together into the unified structure of space-time, special relativity declares, what's true for space is true for time. But this raises a question. Whereas we can picture warped space by its having a curved shape, what do we really mean by warped time? To get a feel for the answer, let's once again impose upon Slim and Jim on the tornado ride and ask them to carry out the following experiment. Slim will stand with his back against the ride at the far end of one of the ride's radial struts, while Jim will slowly crawl toward him along the strut, starting from the ride's center. Every few feet, Jim will stop his crawling and the two brothers are to compare the readings on their watches. What will they find? From our stationary bird's-eye perspective, we can again predict the answer. Their watches will not agree. We come to this conclusion because we realize that Slim and Jim are traveling at different speeds. On the tornado ride, the farther out along a radial strut you are, the farther you must travel to complete one rotation, and therefore the faster you must go. But from special relativity, the faster you go, the slower your watch ticks, and hence we realize that Slim's watch will tick more slowly than Jim's. Furthermore, Slim and Jim will find that as Jim gets closer to Slim, the ticking rate of Jim's watch will slow down, approaching that of Slim's. This reflects the fact that as Jim gets farther out along the strut, his circular speed increases toward that of Slim. We conclude that to observers on the spinning ride, such as Slim and Jim, the rate of passage of time depends upon their precise position. In this case, their distance from the center of the ride. This is an illustration of what we mean by warped time. Time is warped if its rate of passage differs from one location to another. And of particular importance to our present discussion, Jim will also notice something else as he crawls out along the strut. He will feel an increasingly strong outward pull, because not only does speed increase, but his acceleration increases as well, the farther he is from the spinning ride's center. On the tornado ride, then, we see that greater acceleration is tied up with slower clocks. That is, greater acceleration results in a more significant warping of time. These observations took Einstein to the final leap. Since he had already shown gravity and accelerated motion to be effectively indistinguishable, and since he now had shown that accelerated motion is associated with the warping of space and time, he made the following proposal for the innards of the black box of gravity, the mechanism by which gravity operates. Gravity, according to Einstein, is the warping of space and time. Let's see what this means. The basics of general relativity. To get a feel for this new view of gravity, let's consider the prototypical situation of a planet, such as the Earth, revolving around a star, such as the Sun. In Newtonian gravity, the Sun keeps the Earth in orbit with an unidentified gravitational tether that somehow instantaneously reaches out across vast distances of space and grabs hold of the Earth, and, similarly, the Earth reaches out and grabs hold of the Sun. Einstein provided a new conception of what actually happens. It will aid in our discussion of Einstein's approach to have a concrete visual model of spacetime that we can conveniently manipulate. To do so, we will simplify things in two ways. First, for the moment, we will ignore time and focus solely on a visual model of space. We will reincorporate time in our discussion shortly. Second, in order to allow us to draw and manipulate visual images on the pages of this book, we will often refer to a two-dimensional analog of three-dimensional space. Most of the insight we gain from thinking in terms of this lower-dimensional model is directly applicable to the physical three-dimensional setting, so the simpler model provides a powerful pedagogical device. In Figure 3.3, we make use of these simplifications and draw a two-dimensional model of a spatial region of our universe. The grid-like structure indicates a convenient means of specifying positions, just as a street grid gives a means of specifying locations in a city. In a city, of course, one gives an address by specifying a location on the two-dimensional street grid and also giving a location in the vertical direction, such as a floor number. It is the latter information, location in the third spatial dimension, that our two-dimensional analogy suppresses for visual clarity. In the absence of any matter or energy, Einstein envisioned that space would be flat. In our two-dimensional model, this means that the shape of space should be like the surface of a smooth table. This is the image of our spatial universe commonly held for thousands of years. But what happens to space if a massive object like the sun is present? Before Einstein, the answer was nothing. Space and time were thought to provide an inert theater, merely setting the stage on which the events of the universe play themselves out. The chain of Einstein's reasoning that we have been following, however, leads to a different conclusion. A massive body like the sun, and indeed any body, exerts a gravitational force on other objects. In the example of the terrorist bomb, we learned that gravitational forces are indistinguishable from accelerated motion. In the example of the tornado ride, we learned that a mathematical description of accelerated motion requires the relations of curved space. These links between gravity, accelerated motion, and curved space led Einstein to the remarkable suggestion that the presence of mass, such as the sun, causes the fabric of space around it to warp. A useful and oft-quoted analogy is that much like a rubber membrane on which a bowling ball has been placed, the fabric of space becomes distorted due to the presence of a massive object like the sun. According to this radical proposal, space is not merely a passive form providing the arena for the events of the universe. Rather, the shape of space responds to objects in the environment. This warping in turn affects other objects moving in the vicinity of the sun, as they now must traverse the distorted spatial fabric. Using the rubber membrane bowling ball analogy, if we place a small ball bearing on the membrane and set it off with some initial velocity, the path it will follow depends on whether or not the bowling ball is sitting in the center. If the bowling ball is absent, the rubber membrane will be flat and the ball bearing will travel along a straight line. If the bowling ball is present and thereby warps the membrane, the ball bearing will travel along a curved path. In fact, ignoring friction, if we set the ball bearing moving with just the right speed in just the right direction, it will continue to move in a recurring curved path around the bowling ball. In effect, it will go into orbit. Our language presages the application of this analogy to gravity. The sun, like the bowling ball, warps the fabric of space surrounding it, and the Earth's motion, like that of the ball bearing, is determined by the shape of the warp. The Earth, like the ball bearing, will move in orbit around the sun if its speed and orientation have suitable values. This effect on the motion of the Earth is what we normally would refer to as the gravitational influence of the sun, and is illustrated in Figure 3.5. The difference now is that unlike Newton, Einstein has specified the mechanism by which gravity is transmitted, the warping of space. In Einstein's view, the gravitational tether holding the Earth in orbit is not some mysterious instantaneous action of the sun. Rather, it is the warping of the spatial fabric caused by the sun's presence. This picture allows us to understand the two essential features of gravity in a new way. First, the more massive the bowling ball, the greater the distortion it causes in the rubber membrane. Similarly, in Einstein's description of gravity, the more massive an object is, the greater the distortion it causes in the surrounding space. This implies that the more massive an object, the greater the gravitational influence it can exert on other bodies, precisely in accord with our experiences. Second, just as the distortion of the rubber membrane due to the bowling ball gets smaller as one gets farther from it, the amount of spatial warping due to a massive body such as the Sun decreases as one's distance from it increases. This, again, jibes with our understanding of gravity, whose influence becomes weaker as the distance between objects becomes larger. An important point to note is that the ball bearing itself warps the rubber membrane, although only slightly. Similarly, the Earth, being a massive body in its own right, also warps the fabric of space, although far less than the Sun. This is how, in the language of general relativity, the Earth keeps the Moon in orbit, and it is also how the Earth keeps each of us bound to its surface. As a skydiver plunges earthward, he or she is sliding down a depression in the spatial fabric caused by the Earth's mass. Moreover, each of us, like any massive object, also warps the spatial fabric in close proximity to our bodies, although the comparatively small mass of a human body makes this a minuscule indentation. In summary, then, Einstein fully agreed with Newton's statement that gravity must be caused by an agent, and rose to Newton's challenge in which the identity of the agent was left to the consideration of my readers. The agent of gravity, according to Einstein, is the fabric of the cosmos. A few caveats. The rubber membrane bowling ball analogy is valuable because it gives us a visual image with which we can grasp tangibly what we mean by a warp in the spatial fabric of the universe. Physicists often use this and similar analogies to guide their own intuition regarding gravitation and curvature. However, its usefulness notwithstanding, the rubber membrane bowling ball analogy is not perfect, and for clarity we call attention to a few of its shortcomings. First, when the Sun causes the fabric of space around it to warp, this is not due to its being pulled downward by gravity, as in the case of the bowling ball, which warps the rubber membrane because it is pulled earthward by gravity. In the case of the Sun, there is no other object to do the pulling. Instead, Einstein has taught us that the warping of space is gravity. The mere presence of an object with mass causes space to respond by warping. Similarly, the Earth is not kept in orbit because the gravitational pull of some other external object guides it along the valleys in the warped spatial environment, as occurs for a ball bearing on the warped rubber membrane. Instead, Einstein showed that objects move through spacetime more precisely, along the shortest possible paths, the easiest possible paths or the paths of least resistance. If the space is warped, such paths will be curved. And so, although the rubber membrane bowling ball model provides a good visual analogy of how an object such as the Sun warps the space around it and thereby influences the motion of other bodies, the physical mechanism by which these distortions occur is totally different. The former appeals to our intuition about gravity in the traditional Newtonian framework, whereas the latter expresses a reformulation of gravity in terms of curved space. A second shortcoming of the analogy stems from the rubber membranes being two-dimensional. In reality, although harder to visualize, the Sun, and all other massive objects, actually warps the three-dimensional space surrounding it. Figure 3.6 is a rough attempt to depict this. All of the space surrounding the Sun, below, on the sides, on top, suffers the same kind of distortion, and Figure 3.6 schematically shows a partial sampling. A body, like the Earth, travels through the three-dimensional warped spatial environment caused by the Sun's presence. You may find this figure troubling. Why doesn't the Earth slam into the vertical part of curved space in the image? Bear in mind, though, that space, unlike the rubber membrane, is not a solid barrier. Instead, the warped grids in the image are but a couple of thin slices through the full three-dimensional warped space in which you, the Earth, and everything else are immersed fully and move freely. Perhaps you find that this only makes the problem seem worse. Why don't we feel space if we are immersed within its fabric? But we do. We feat gravity, and space is the medium by which the gravitational force is communicated. As the eminent physicist John Wheeler has often said in describing gravity, mass grips space by telling it how to curve, space grips mass by telling it how to move. A third, related shortcoming of the analogy is that we have suppressed the time dimension. We have done this for visual clarity because, notwithstanding the declaration of special relativity that we should think of the time dimension on par with the three familiar spatial dimensions, it is significantly harder to see time. But, as illustrated by the example of the tornado ride, acceleration, and hence gravity, warps both space and time. In fact, the mathematics of general relativity shows that in the case of a relatively slow-moving body like the Earth revolving around a typical star like the Sun, the warping of time actually has a far more significant impact on the Earth's motion than does the warping of space. We will return to a discussion of the warping of time after the next section. Important as these three caveats are, so long as you hold them in the back of your mind, it is perfectly acceptable to invoke the warped space image provided by the bowling ball on the rubber membrane as an intuitive summary of Einstein's new view of gravity. Conflict resolution. By introducing space and time as dynamic players, Einstein provided a clear conceptual image of how gravity works. The central question, though, is whether this reformulation of the gravitational force resolves the conflict with special relativity that afflicts Newton's theory of gravity. It does. Again, the rubber membrane analogy gives the essential idea. Imagine that we have a ball bearing rolling in a straight line along the flat membrane in the absence of the bowling ball. As we place the bowling ball on the membrane, the motion of the ball bearing will be affected, but not instantaneously. If we were to film this sequence of events and view it in slow motion, we would see that the disturbance caused by the introduction of the bowling ball spreads like ripples in a pond and eventually reaches the position of the ball bearing. After a short time, transitory oscillations along the rubber surface would settle down, leaving us with a static, warped membrane. The same is true for the fabric of space. When no mass is present, space is flat, and a small object will blissfully be at rest or will travel at a constant velocity. If a large mass comes on the scene, space will warp, but as in the case of the membrane, the distortion will not be instantaneous. Rather, it will spread outward from the massive body, ultimately settling down into a warped shape that communicates the gravitational pull of the new body. In our analogy, disturbances to the rubber membrane travel along its extent at a speed dictated by its particular material composition. In the real setting of general relativity, Einstein was able to calculate how fast disturbances to the fabric of the universe travel, and he found that they travel at precisely the speed of light. This means, for instance, that in the hypothetical example discussed earlier in which the demise of the Sun affects the Earth by virtue of changes in their mutual gravitational attraction, the influence will not be instantaneously communicated. Rather, as an object changes its position or even blows apart, it causes a change in the distortion of the space-time fabric that spreads outward at light speed, precisely in keeping with the cosmic speed limit of special relativity. Thus, we on Earth would visually learn of the Sun's destruction at the same moment that we would feel the gravitational consequences, about 8 minutes after it explodes. Einstein's formulation thereby resolves the conflict. Gravitational disturbances keep pace with, but do not outrun photons. The warping of time revisited. Illustrations, such as those of figures 3.2, 3.4, and 3.6 capture the essence of what warped space means. A warp distorts the shape of space. Physicists have invented analogous images to try to convey the meaning of warped time, but they are significantly more difficult to decipher, so we will not introduce them here. Instead, let's follow up the example of Slim and Jim on the tornado ride, and try to get a sense of the experience of gravitationally induced warped time. To do so, we revisit George and Gracie, no longer in the deep darkness of empty space, but floating near the outskirts of the solar system. They are still each wearing large digital clocks on their spacesuits that are initially synchronized. To keep things simple, we ignore the effects of the planets and consider only the gravitational field of the Sun. Let's further imagine that a spaceship hovering near George and Gracie has reeled out a long cable extending all the way down to the vicinity of the Sun's surface. George uses this cable to slowly lower himself toward the Sun. As he does so, he periodically stops so that he and Gracie can compare the rate at which time is elapsing on their clocks. The warping of time predicted by Einstein's general relativity implies that George's clock will run slower and slower compared with Gracie's, as the gravitational field he experiences gets stronger and stronger. That is, the closer he gets to the sun, the slower his clock will run. It is in this sense that gravity distorts time as well as space. You should note that unlike the case in Chapter 2 in which George and Gracie were in empty space, moving relative to each other with constant velocity, in the present setting there is no symmetry between them. George, unlike Gracie, feels the force of gravity getting stronger and stronger. He has to hold the cable tighter and tighter as he gets closer to the sun to avoid being pulled in. Each of them agrees that George's clock is running slow. There is no equally valid perspective that exchanges their roles and reverses this conclusion. This is in fact what we found in Chapter 2 when George experienced an acceleration by turning on his jetpack to catch up with Gracie. The acceleration George felt resulted in his clock definitively running slow relative to Gracie's. Since we now know that feeling accelerated motion is the same as feeling a gravitational force, the present situation of George on the cable involves the same principle, and once again we see that George's clock, and everything else in his life, runs in slow motion compared with Gracie's. In a gravitational field such as that at the surface of an ordinary star like the sun, the slowing of clocks is quite small. If Gracie stays put at 1 billion miles from the sun, then when George has climbed to within a few miles of its surface, the rate of ticking of his clock will be about 99.9998% of Gracie's. Slower, but not by much. If, however, George lowered himself on a cable so that he hovered just above the surface of a neutron star, whose mass, roughly equal to that of the sun, is crushed to a density some million billion times that of solar density, the larger gravitational field would cause his clock to tick at about 76% of the rate of Gracie's. Stronger gravitational fields, such as those just outside a black hole, as discussed below, cause the flow of time to slow even further. Stronger gravitational fields cause a more severe warping of time. Experimental verification of general relativity. Most people who study general relativity are captivated by its aesthetic elegance. By replacing the cold, mechanistic Newtonian view of space, time, and gravity with a dynamic and geometric description involving curved space-time, Einstein wove gravity into the basic fabric of the universe. Rather than being imposed as an additional structure, gravity becomes part and parcel of the universe at its most fundamental level, breathing life into space and time by allowing them to curve, warp, and ripple results in what we commonly refer to as gravity. Aesthetics aside, the ultimate test of a physical theory is its ability to explain and predict physical phenomena accurately. Since its inception in the late 1600s until the beginning of this century, Newton's theory of gravity passed this test with flying colors. Whether applied to balls thrown up in the air, objects dropped from leaning towers, comets whirling around the sun, or planets going about their solar orbits, Newton's theory provides extremely accurate explanations of all observations, as well as predictions that have been verified innumerable times in a wealth of situations. The motivation for questioning this experimentally successful theory, as we have emphasized, was its property of instantaneous transmission of the gravitational force in conflict with special relativity. The effects of special relativity, although central to a fundamental understanding of space, time, and motion, are extremely small in the slow-velocity world we typically inhabit. Similarly, the deviations between Einstein's general relativity, a theory of gravity compatible with special relativity, and Newton's theory of gravity are also extremely small in most common situations. This is both good and bad. It is good because any theory purporting to supplant Newton's theory of gravity had better closely agree with it when applied in those arenas in which Newton's theory has been experimentally verified. It is bad because it makes it difficult to adjudicate between the two theories experimentally. Distinguishing between Newton's and Einstein's theories requires extremely precise measurements applied to experiments that are very sensitive to the ways in which the two theories differ. If you throw a baseball, Newtonian and Einsteinian gravity can be used to predict where it will land, and the answers will be different. But the differences will be so slight that they are generally beyond our capacity to detect experimentally. A more clever experiment is called for, and Einstein suggested one. We see stars at night, but of course they are also there during the day. We usually don't see them because their distant, pinpoint light is overwhelmed by the light emitted by the sun. During a solar eclipse, however, the moon temporarily blocks the light of the sun and distant stars become visible. Nevertheless, the presence of the sun still has an effect. Light from some of the distant stars must pass close to the sun on the way to Earth. Einstein's general relativity predicts that the sun will cause the surrounding space and time to warp, and such distortion will influence the path taken by the starlight. After all, the photons of distant origin travel along the fabric of the universe. If the fabric is warped, the motion of the photons will be affected much as for a material body. The bending of the path of light is greatest for those light signals that just graze the sun on their way to Earth. A solar eclipse makes it possible to see such sun-grazing starlight without its being completely obscured by sunlight itself. The angle through which the light path is bent can be measured in a simple way. The bending of the starlight's path results in a shift in the apparent position of the star. The shift can be accurately measured by comparing this apparent position with the star's actual location, known from observations of the star at night, in the absence of the sun's warping influence, carried out when the Earth is at an appropriate position, some 6 months earlier or later. In November of 1915, Einstein used his new understanding of gravity to calculate the angle through which starlight signals that just graze the sun would be bent, and found the answer to be about 0.00049 of a degree, 1.75 arcseconds, where an arcsecond is 1/3600th of a degree. This tiny angle is equal to that subtended by a quarter placed upright and viewed from nearly 2 miles away. The detection of such a small angle was, however, within reach of the technology of the day. At the urging of Sir Frank Dyson, director of the Greenwich Observatory, Sir Arthur Eddington, a well-known astronomer and secretary of the Royal Astronomical Society in England, organized an expedition to the island of Principe off the coast of West Africa to test Einstein's prediction during the solar eclipse of May 29, 1919. On November 6, 1919, after some 5 months of analysis of the photographs taken during the eclipse at Principe and of other photographs of the eclipse taken by a second British team led by Charles Davidson and Andrew Crommelin in Sobral, Brazil, it was announced at a joint meeting of the Royal Society and the Royal Astronomical Society that Einstein's prediction based on general relativity had been confirmed. It took little time for word of this success, a complete overturning of previous conceptions of space and time, to spread well beyond the confines of the physics community, making Einstein a celebrated figure worldwide. On November 7, 1919, the headline in the London Times read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." This was Einstein's moment of glory. In the years following this experiment, Eddington's confirmation of general relativity came under some critical scrutiny. Numerous difficult and subtle aspects of the measurement made it hard to reproduce and raised some questions regarding the trustworthiness of the original experiment. Nevertheless, in the last 40 years, a variety of experiments making use of technological advancements have tested numerous aspects of general relativity with great precision. The predictions of general relativity have been uniformly confirmed. There is no longer any doubt that Einstein's description of gravity is not only compatible with special relativity, but yields predictions closer to experimental results than those of Newton's theory. Black holes, the Big Bang, and the expansion of space. Whereas special relativity is most manifest when things are moving fast, general relativity comes into its own when things are very massive, and the warps in space and time are correspondingly severe. Let's describe 2 examples. The first is a discovery made by the German astronomer Karl Schwarzschild while studying Einstein's revelations on gravity in between his own calculations of artillery trajectories at the Russian front during World War I in 1916. Remarkably, just months after Einstein had put the finishing touches on general relativity, Schwarzschild was able to use the theory to gain a complete and exact understanding of the way space and time warp in the vicinity of a perfectly spherical star. Schwarzschild sent his results from the Russian front to Einstein, who presented them on Schwarzschild's behalf to the Prussian Academy. Beyond confirming and making mathematically precise the warping that was schematically illustrated in Figure 3.5, Schwarzschild's work, which has now come to be known as Schwarzschild's solution, revealed a stunning implication of general relativity. He showed that if the mass of a star is concentrated in a small enough spherical region, so that its mass divided by its radius exceeds a particular critical value, the resulting spacetime warp is so radical that anything, including light, that gets too close to the star will be unable to escape its gravitational grip. Since not even light can escape such compressed stars, they were initially called dark or frozen stars. A more catchy name was coined years later by John Wheeler, who called them black holes. Black because they cannot emit light, holes because anything getting too close falls into them, never to return. The name stuck. We illustrate Schwarzschild's solution in Figure 3.7. Although black holes have a reputation for rapacity, objects that pass by them at a safe distance are deflected in much the same way that they would be by an ordinary star, and can proceed on their merry way. But objects of any composition whatsoever that get too close, closer than what has been termed the black hole's event horizon, are doomed. They will be drawn inexorably toward the center of the black hole and subject to an ever-increasing and ultimately destructive gravitational strain. For example, if you dropped feet first through the event horizon as you approached the black hole's center, you would find yourself getting increasingly uncomfortable. The gravitational force of the black hole would increase so dramatically that its pull on your feet would be much stronger than its pull on your head, since in a feet-first fall your feet are always a bit closer than your head to the black hole's center. So much stronger, in fact, that you would be stretched with a force that would quickly tear your body to shreds. If, on the contrary, you were more prudent in your wanderings near a black hole and took great care not to trespass beyond the event horizon, you could make use of the black hole for a rather amazing feat. Imagine, for example, that you were to discover a black hole whose mass was about 1,000 times the mass of the Sun, and that you were to lower yourself on a cable, much as George did near the Sun, to about an inch above the black hole's event horizon. As we have discussed, gravitational fields cause a warping of time, and this means that your passage through time would slow down. In fact, since black holes have such strong gravitational fields, your passage through time would slow way down. Your watch would tick about 10,000 times more slowly than those of your friends back on Earth. If you were to hover just above the black hole's event horizon in this manner for a year, and then climb up the cable to your waiting starship for a short, yet leisurely journey home, upon arrival at Earth, you would find that more than 10,000 years had passed since your initial departure. You would have successfully used the black hole as a kind of time machine, allowing you to travel to Earth's distant future. To get a sense of the extreme scales involved, a star with the mass of the Sun would be a black hole if its radius were not its actual value, about 450,000 miles, but instead just under 2 miles. Imagine the whole of the Sun squeezed to fit comfortably within Upper Manhattan. A teaspoonful of such a compressed sun would weigh about as much as Mount Everest. To make a black hole out of the Earth, we would need to crush it into a sphere whose radius is less than half an inch. For a long time, physicists were skeptical about whether such extreme configurations of matter could ever actually occur, and many thought that black holes were merely a reflection of an overworked theoretician's imagination. Nevertheless, during the last decade, an increasingly convincing body of experimental evidence for the existence of black holes has accumulated. Of course, since they are black, they cannot be observed directly by scanning the sky with telescopes. Instead, astronomers search for black holes by seeking anomalous behavior of other more ordinary, light-emitting stars that may be positioned just outside a black hole's event horizon. For instance, as dust and gas from the outer layers of nearby ordinary stars fall toward the event horizon of a black hole, they are accelerated to nearly the speed of light. At such speeds, friction within the maelstrom of downward swirling material generates an enormous amount of heat, causing the dust-gas mixture to glow, giving off both ordinary visible light and X-rays. Since this radiation is produced just outside the event horizon, it can escape the black hole and travel through space to be observed and studied directly. General relativity makes detailed predictions about properties that such X-ray emissions will have. Observation of these predicted properties gives strong, albeit indirect, evidence for the existence of black holes. For example, mounting evidence indicates that there is a very massive black hole, some 2.5 million times as massive as the Sun, sitting in the center of our own Milky Way galaxy. And even this seemingly gargantuan black hole pales in comparison to what astronomers believe to reside in the core of the astonishingly luminous quasars that are scattered throughout the cosmos. Black holes whose masses may well be billions of times that of the Sun. Schwarzschild died only a few months after finding his solution, from a skin disease he contracted at the Russian front. He was 42. His tragically brief encounter with Einstein's theory of gravity uncovered one of the most striking and mysterious facets of the natural world. The second example in which general relativity flexes its muscle concerns the origin and evolution of the whole universe. As we have seen, Einstein showed that space and time respond to the presence of mass and energy. This distortion of spacetime affects the motion of other cosmic bodies moving in the vicinity of the resulting warps. In turn, the precise way in which these bodies move, by virtue of their own mass and energy, has a further effect on the warping of spacetime, which further affects the motion of the bodies. And on the interconnected cosmic dance goes. Through the equations of general relativity, equations rooted in geometrical insights into curved space spearheaded by the great 19th century mathematician Georg Bernhard Riemann, more about Riemann later, Einstein was able to describe the mutual evolution of space, time, and matter quantitatively. To his great surprise, when the equations are applied beyond an isolated context within the universe, such as a planet or a comet orbiting a star, to the universe as a whole, a remarkable conclusion is reached. The overall size of the spatial universe must be changing in time. That is, either the fabric of the universe is stretching or it is shrinking, but it is not simply staying put. The equations of general relativity show this explicitly. This conclusion was too much even for Einstein. He had overturned the collective intuition regarding the nature of space and time built up through everyday experiences over thousands of years. But the notion of an always existing, never-changing universe was too ingrained for even this radical thinker to abandon. For this reason, Einstein revisited his equations and modified them by introducing something known as a cosmological constant, an additional term that allowed him to avoid this prediction and once again bask in the comfort of a static universe. However, 12 years later, through detailed measurements of distant galaxies, the American astronomer Edwin Hubble experimentally established that the universe is expanding. In a now famous story in the annals of science, Einstein then returned to the original form of his equations, citing his temporary modification of them as the biggest blunder of his life. His initial unwillingness to accept the conclusion notwithstanding, Einstein's theory predicted the expansion of the universe. In fact, in the early 1920s, years before Hubble's measurements, the Russian meteorologist Alexander Friedmann had used Einstein's original equations to show, in some detail, that all galaxies would be carried along on the substrate of stretching spatial fabric, thereby speedily moving away from all others. Hubble's observations and numerous subsequent ones have thoroughly verified this astonishing conclusion of general relativity. By offering the explanation for the expansion of the universe, Einstein achieved one of the greatest intellectual feats of all time. If the fabric of space is stretching, thereby increasing the distance between galaxies that are carried along on the cosmic flow, we can imagine running the evolution backward in time to learn about the origin of the universe. In reverse, the fabric of space shrinks, bringing all galaxies closer and closer to each other. Like the contents of a pressure cooker, as the shrinking universe compresses the galaxies together, the temperature dramatically increases, stars disintegrate, and a hot plasma of matter's elementary constituents is formed. As the fabric continues to shrink, the temperature rises unabated, as does the density of the primordial plasma. As we imagine running the clock backward from the age of the presently observed universe, about 15 billion years, the universe as we know it is crushed to an ever smaller size. The matter making up everything, every car, house, building, mountain on Earth, the Earth itself, the Moon, Saturn, Jupiter, and every other planet, the Sun and every other star in the Milky Way, the Andromeda Galaxy with its 100 billion stars and each and every other of the more than 100 billion galaxies is squeezed by a cosmic vice to astounding density, and as the clock is turned back to ever earlier times, the whole of the cosmos is compressed to the size of an orange, a lemon, a pea, a grain of sand, and to yet tinier size still. Extrapolating all the way back to the beginning, the universe would appear to have begun as a point, an image we will critically re-examine in later chapters, in which all matter and energy is squeezed together to unimaginable density and temperature. It is believed that a cosmic fireball, the Big Bang, erupted from this volatile mixture, spewing forth the seeds from which the universe as we know it evolved. The image of the Big Bang as a cosmic explosion ejecting the material contents of the universe like shrapnel from an exploding bomb is a useful one to bear in mind, but it is a little misleading. When a bomb explodes, it does so at a particular location in space and at a particular moment in time. Its contents are ejected into the surrounding space. In the Big Bang, there is no surrounding space. As we devolve the universe backward toward the beginning, the squeezing together of all material content occurs because all of space is shrinking. The orange size, the pea size, the grain of sand-sized evolution describes the whole of the universe, not something within the universe. Carrying on to the beginning, there is simply no space outside the primordial pinpoint grenade. Instead, the Big Bang is the eruption of compressed space whose unfurling, like a tidal wave, carries along matter and energy even to this day. Is general relativity right? No deviations from the predictions of general relativity have been found in experiments performed with our present level of technology. Only time will tell if greater experimental precision will ultimately uncover some, thereby showing this theory too to be only an approximate description of how nature actually works. The systematic testing of theories to greater and greater levels of accuracy is certainly one of the ways science progresses, but it is not the only way. In fact, we have already seen this. The search for a new theory of gravity was initiated not by an experimental refutation of Newton's theory, but rather by the conflict of Newtonian gravity with another theory, special relativity. It was only after the discovery of general relativity as a competing theory of gravity that experimental flaws in Newton's theory were identified by seeking out tiny but measurable ways in which the two theories differ. Thus, internal theoretical inconsistencies can play as pivotal a role in driving progress as do experimental data. For the last half-century, physics has been faced with still another theoretical conflict whose severity is on par with that between special relativity and Newtonian gravity. General relativity appears to be fundamentally incompatible with another extremely well-tested theory, quantum mechanics. Regarding the material covered in this chapter, the conflict prevents physicists from understanding what really happens to space, time, and matter when crushed together fully at the moment of the Big Bang or at the central point of a black hole. But more generally, the conflict alerts us to a fundamental deficiency in our conception of nature. The resolution of this conflict has eluded attempts by some of the greatest theoretical physicists, giving it a well-deserved reputation as the central problem of modern theoretical physics. Understanding the conflict requires familiarity with some basic features of quantum theory to which we now turn. Chapter 4. Microscopic Weirdness. A bit worn out from their trans-solar system expedition, George and Gracie return to Earth and head over to the H-bar for some post-space sojourning refreshments. George orders the usual, papaya juice on the rocks for himself and a vodka tonic for Gracie, and kicks back in his chair, hands clasped behind his head, to enjoy a freshly lit cigar. Just as he prepares to inhale, though, he is stunned to find that the cigar has vanished from between his teeth. Thinking that the cigar must somehow have slipped from his mouth, George sits forward, expecting to find it burning a hole in his shirt or trousers. But it is not there. The cigar is not to be found. Gracie, roused by George's frantic movement, glances over and spots the cigar lying on the counter directly behind George's chair. "Strange," George says. "How in the heck could it have fallen over there? It's as if it went right through my head. But my tongue isn't burned, and I don't seem to have any new holes." Gracie examines George and reluctantly confirms that his tongue and head appear to be perfectly normal. As the drinks have just arrived, George and Gracie shrug their shoulders and chalk up the fallen cigar to one of life's little mysteries. But the weirdness at the H-bar continues. George looks into his papaya juice and notices that the ice cubes are incessantly rattling around. bouncing off of each other and the sides of the glass like overcharged automobiles in a bumper car arena. And this time, he is not alone. Gracie holds up her glass, which is about half the size of George's, and both of them see that her ice cubes are bouncing around even more frantically. They can hardly make out the individual cubes as they all blur together into an icy mass, but none of this compares to what happens next. As George and Gracie stare at her rattling drink with wide-eyed wonderment, they see a single ice cube pass through the side of her glass and drop down to the bar. They grab the glass and see that it is fully intact. Somehow, the ice cube went right through the solid glass without causing any damage. "Must be post-spacewalk hallucinations," says George. They each fight off the frenzy of careening ice cubes to down their drinks in one go and head home to recover. Little do George and Gracie realize that in their haste to leave, they mistook a decorative door painted on a wall of the bar for the real thing. The patrons of the H-Bar, though, are well accustomed to people passing through walls and hardly take note of George and Gracie's abrupt departure. A century ago, while Conrad and Freud were illuminating the heart and the soul of darkness, the German physicist Max Planck shed the first ray of light on quantum mechanics, a conceptual framework that proclaims, among other things, that the H-bar experiences of George and Gracie, when scaled down to the microscopic realm, need not be attributed to clouded faculties. Such unfamiliar and bizarre happenings are typical of how our universe on extremely small scales actually behaves. The quantum framework. Quantum mechanics is a conceptual framework for understanding the microscopic properties of the universe. And just as special relativity and general relativity require dramatic changes in our worldview when things are moving very quickly or when they are very massive, quantum mechanics reveals that the universe has equally, if not more startling properties when examined on atomic and subatomic distance scales. In 1965, Richard Feynman, one of the greatest practitioners of quantum mechanics, wrote, "There was a time when the newspapers said that only 12 men understood the theory of relativity. I do not believe there ever was such a time. There might have been a time when only one man did, because he was the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people understood the theory of relativity in one way or other, certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Although Feynman expressed this view more than 3 decades ago, it applies equally well today. What he meant is that although the special and general theories of relativity require a drastic revision of previous ways of seeing the world, when one fully accepts the basic principles underlying them, the new and unfamiliar implications for space and time follow directly from careful logical reasoning. If you ponder the descriptions of Einstein's work in the preceding 2 chapters with adequate intensity, you will, if even for just a moment, recognize the inevitability of the conclusions we have drawn. Quantum mechanics is different. By 1928 or so, many of the mathematical formulas and rules of quantum mechanics had been put in place, and ever since, it has been used to make the most precise and successful numerical predictions in the history of science. But in a real sense, those who use quantum mechanics find themselves following rules and formulas laid down by the founding fathers of the theory, calculational procedures that are straightforward to carry out, without really understanding why the procedures work or what they really mean. Unlike relativity, few, if any, people ever grasp quantum mechanics at a soulful level. What are we to make of this? Does it mean that on a microscopic level the universe operates in ways so obscure and unfamiliar that the human mind, evolved over eons to cope with phenomena on familiar everyday scales, is unable to fully grasp what really goes on? Or might it be that through historical accident, physicists have constructed an extremely awkward formulation of quantum mechanics that, although quantitatively successful, obfuscates the true nature of reality? No one knows. Maybe sometime in the future some clever person will see clear to a new formulation that will fully reveal the whys and the whats of quantum mechanics. And then again, maybe not. The only thing we know with certainty is that quantum mechanics absolutely and unequivocally shows us that a number of basic concepts essential to our understanding of the familiar everyday world fail to have any meaning when our focus narrows to the microscopic realm. As a result, we must significantly modify both our language and our reasoning when attempting to understand and explain the universe on atomic and subatomic scales. In the following sections, we will develop the basics of this language and describe a number of the remarkable surprises it entails. If along the way quantum mechanics seems to you to be altogether bizarre or even ludicrous, you should bear in mind two things. First, beyond the fact that it is a mathematically coherent theory, the only reason we believe in quantum mechanics is because it yields predictions that have been verified to astounding accuracy. If someone can tell you volumes of intimate details of your childhood in excruciating detail, it's hard not to believe their claim of being your long-lost sibling. Second, you are not alone in having this reaction to quantum mechanics. It is a view held to a greater or lesser extent by some of the most revered physicists of all time. Einstein refused to accept quantum mechanics fully, and even Niels Bohr, one of the central pioneers of quantum theory and one of its strongest proponents, once remarked that if you do not get dizzy sometimes when you think about quantum mechanics, then you have not really understood it. It's too hot in the kitchen. The road to quantum mechanics began with a puzzling problem. Imagine that your oven at home is perfectly insulated, that you set it to some temperature, say 400 degrees Fahrenheit, and you give it enough time to heat up. Even if you had sucked all the air from the oven before turning it on, by heating its walls, you generate waves of radiation in its interior. This is the same kind of radiation, heat and light in the form of electromagnetic waves, that is emitted by the surface of the sun or a glowing hot iron poker. Here's the problem. Electromagnetic waves carry energy. Life on Earth, for example, relies crucially on solar energy transmitted from the sun to the Earth by electromagnetic waves. At the beginning of the 20th century, physicists calculated the total energy carried by all of the electromagnetic radiation inside an oven at a chosen temperature. Using well-established calculational procedures, they came up with a ridiculous answer. For any chosen temperature, the total energy in the oven is infinite. It was clear to everyone that this was nonsense. A hot oven can embody significant energy, but surely not an infinite amount. To understand the resolution proposed by Planck, it is worth understanding the problem in a bit more detail. It turns out that when Maxwell's electromagnetic theory is applied to the radiation in an oven, it shows that the waves generated by the hot walls must have a whole number of peaks and troughs that fit perfectly between opposite surfaces. Some examples are shown in Figure 4.1. Physicists use three terms to describe these waves: wavelength, frequency, and amplitude. The wavelength is the distance between successive peaks or successive troughs of the waves. More peaks and troughs mean a shorter wavelength, as they must all be crammed in between the fixed walls of the oven. The frequency refers to the number of up and down cycles of oscillation that a wave completes every second. It turns out that the frequency is determined by the wavelength and vice versa. Longer wavelengths imply lower frequency. Shorter wavelengths imply higher frequency. To see why, think of what happens when you produce waves by shaking a long rope that is tied down at one end. To generate a long wavelength, you leisurely shake your end up and down. The frequency of the waves matches the number of cycles per second your arm goes through and is consequently fairly low. But to generate short wavelengths, you shake your end more frantically, more frequently, so to speak, and this yields a higher frequency wave. Finally, physicists use the term amplitude to describe the maximum height or depth of a wave. In case you find electromagnetic waves a bit abstract, another good analogy to keep in mind are the waves that are produced by plucking a violin string. Different wave frequencies correspond to different musical notes. The higher the frequency, the higher the note. The amplitude of a wave on a violin string is determined by how hard you pluck it. A harder pluck means that you put more energy into the wave disturbance. More energy, therefore, corresponds to a larger amplitude. You can hear this as the resulting tone is louder. Similarly, less energy corresponds to a smaller amplitude and a lower volume of sound. By making use of 19th century thermodynamics, physicists were able to determine how much energy the hot walls of the oven would pump into electromagnetic waves of each allowed wavelength. How hard the walls would, in effect, pluck each wave. The result they found is simple to state. Each of the allowed waves, regardless of its wavelength, carries the same amount of energy, with the precise amount determined by the temperature of the oven. In other words, all of the possible wave patterns within the oven are on completely equal footing when it comes to the amount of energy they embody. At first, this seems like an interesting, albeit innocuous result. It isn't. It spells the downfall of what has come to be known as classical physics. The reason is this: even though requiring that all waves have a whole number of peaks and troughs rules out an enormous variety of conceivable wave patterns in the oven, there are still an infinite number that are possible, those with ever more peaks and troughs. Since each wave pattern carries the same amount of energy, an infinite number of them translates into an infinite amount of energy. At the turn of the century, there was a gargantuan fly in the theoretical ointment, making lumps at the turn of the century. In 1900, Planck made an inspired guess that allowed a way out of this puzzle and would earn him the 1918 Nobel Prize in Physics. To get a feel for his resolution, imagine that you and a huge crowd of people, infinite in number, are crammed into a large, cold warehouse run by a miserly landlord. There's a fancy digital thermostat on the wall that controls the temperature, but you are shocked when you discover the charges that the landlord levies for heat. If the thermostat is set to 50 degrees Fahrenheit, everyone must give the landlord $50. If it is set to 55 degrees, everyone must pay $55, and so on. You realize that since you are sharing the warehouse with an infinite number of companions, the landlord will earn an infinite amount of money if you turn on the heat at all. But on closer reading of the landlord's rules of payment, you see a loophole. Because the landlord is a very busy man, he does not want to give change, especially not to an infinite number of individual tenants. So he works on an honor system. Those who can pay exactly what they owe do so. Otherwise, they pay only as much as they can without requiring change. And so, wanting to involve everyone, but wanting to avoid the exorbitant charges for heat, you compel your comrades to organize the wealth of the group in the following manner. One person carries all of the pennies, one person carries all of the nickels, one carries all of the dimes, one carries all of the quarters, and so on through dollar bills, $5 bills, $10 bills, 20s, 50s, hundreds, thousands, and ever larger and unfamiliar denominations. You brazenly set the thermostat to 80 degrees and await the landlord's arrival. When he does come, the person carrying pennies goes to pay first and turns over 8,000. The person carrying nickels then turns over 1,600 of them. The person carrying dimes turns over 800. The person with quarters turns over 320. The person with dollars gives the landlord 80. The person with $5 bills turns over 16. The person with $10 bills gives him 8. The person with 20s gives him 4. And the person with 50s hands over 1, since two $50 bills would exceed the necessary payment, thereby requiring change. But everyone else carries only a denomination, a minimal lump of money that exceeds the required payment. Therefore, they cannot pay the landlord, and hence, rather than getting the infinite amount of money he expected, the landlord leaves with the paltry sum of $690. Planck made use of a very similar strategy to reduce the ridiculous result of infinite energy in an oven to one that is finite. Here's how. Planck boldly guessed that the energy carried by an electromagnetic wave in the oven, like money, comes in lumps. The energy can be 1 times some fundamental energy denomination, or 2 times it, or 3 times it, and so forth. But that's it. Just as you can't have 1/3 of a penny or 2½ quarters, Planck declared that when it comes to energy, no fractions are allowed. Now, our monetary denominations are determined by the United States Treasury. Seeking a more fundamental explanation, Planck suggested that the energy denomination of a wave, the minimal lump of energy that it can have, is determined by its frequency. Specifically, he posited that the minimum energy a wave can have is proportional to its frequency. Larger frequency, shorter wavelength, implies larger minimum energy. Smaller frequency, longer wavelength, implies smaller minimum energy. Roughly speaking, just as gentle ocean waves are long and luxurious, while harsh ones are short and choppy, long wavelength radiation is intrinsically less energetic than short wavelength radiation. Here's the punchline. Planck's calculations showed that this lumpiness of the allowed energy in each wave cured the previous ridiculous result of infinite total energy. It's not hard to see why. When an oven is heated to some chosen temperature, the calculations based on 19th century thermodynamics predicted the common energy that each and every wave would supposedly contribute to the total. But like those comrades who cannot contribute the common amount of money they each owe the landlord because the monetary denomination they carry is too large, if the minimum energy a particular wave can carry exceeds the energy it is supposed to contribute, it can't contribute and instead lies dormant. Since, according to Planck, the minimum energy a wave can carry is proportional to its frequency. As we examine waves in the oven of ever larger frequency, shorter wavelength, sooner or later the minimum energy they can carry is bigger than the expected energy contribution. Like the comrades in the warehouse entrusted with denominations larger than $50 bills, these waves with ever larger frequencies cannot contribute the amount of energy demanded by 19th century physics. And so, just as only a finite number of comrades are able to contribute to the total heat payment, leading to a finite amount of total money, only a finite number of waves are able to contribute to the oven's total energy, again leading to a finite amount of total energy. Be it energy or money, the lumpiness of the fundamental units, and the ever-increasing size of these lumps as we go to higher frequencies or to larger monetary denominations, changes an infinite answer to one that is finite. By eliminating the manifest nonsense of an infinite result, Planck had taken an important step. But what really made people believe that his guess had validity is that the finite answer that his new approach gave for the energy in an oven agreed spectacularly with experimental measurements. Specifically, Planck found that by adjusting one parameter that entered into his new calculations, he could predict accurately the measured energy of an oven for any selected temperature. This one parameter is the proportionality factor between the frequency of a wave and the minimal lump of energy it can have. Planck found that this proportionality factor, now known as Planck's constant and denoted h, pronounced h bar, is about a billionth of a billionth of a billionth in everyday units. The tiny value of Planck's constant means that the size of the energy lumps are typically very small. This is why, for example, it seems to us that we can cause the energy of a wave on a violin string, and hence the volume of sound it produces, to change continuously. In reality, though, the energy of the wave passes through discrete steps, a la Planck, but the size of the steps is so small that the discrete jumps from one volume to another appear to be smooth. According to Planck's assertion, the size of these jumps in energy grows as the frequency of the waves gets higher and higher, while wavelengths get shorter and shorter. This is the crucial ingredient that resolves the infinite energy paradox. As we shall see, Planck's quantum hypothesis does far more than allow us to understand the energy content of an oven. It overturns much about the world that we hold to be self-evident. The smallness of AH confines most of these radical departures from life as usual to the microscopic realm. But if it happened to be much larger than it is, the strange happenings at the h-bar would actually be commonplace. As we shall see, their microscopic counterparts certainly are. What are the lumps? Planck had no justification for his pivotal introduction of lumpy energy. Beyond the fact that it worked, neither he nor anyone else could give a compelling reason for why it should be true. As the physicist George Gamow once said, it was as if nature allowed one to drink a whole pint of beer or no beer at all, but nothing in between. In 1905, Einstein found an explanation, and for this insight he was awarded the 1921 Nobel Prize in Physics. Einstein came up with his explanation by puzzling over something known as the photoelectric effect. The German physicist Heinrich Hertz in 1887 was the first to find that when electromagnetic radiation, light, shines on certain metals, they emit electrons. By itself, this is not particularly remarkable. Metals have the property that some of their electrons are only loosely bound within atoms, which is why they are such good conductors of electricity. When light strikes the metallic surface, it relinquishes its energy, much as it does when it strikes the surface of your skin, causing you to feel warmer. This transferred energy can agitate electrons in the metal, and some of the loosely bound ones can be knocked clear off the surface. But the strange features of the photoelectric effect become apparent when one studies more detailed properties of the ejected electrons. At first sight, you would think that as the intensity of the light, its brightness, is increased, the speed of the ejected electrons will also increase since the impinging electromagnetic wave has more energy. But this does not happen. Rather, the number of ejected electrons increases, but their speed stays fixed. On the other hand, it has been experimentally observed that the speed of the ejected electrons does increase if the frequency of the impinging light is increased, and, equivalently, their speed decreases if the frequency of the light is decreased. For electromagnetic waves in the visible part of the spectrum, an increase in frequency corresponds to a change in color from red to orange to yellow to green to blue to indigo, and finally to violet. Frequencies higher than that of violet are not visible and correspond to ultraviolet and subsequently X-rays. Frequencies lower than that of red are also not visible and correspond to infrared radiation. In fact, as the frequency of the light used is decreased, there comes a point when the speed of the emitted electrons drops to zero and they stop being ejected from the surface, regardless of the possibly blinding intensity of the light source. For some unknown reason, the color of the impinging light beam, not its total energy, controls whether or not electrons are ejected, and if they are, the energy they have. To understand how Einstein explained these puzzling facts, let's go back to the warehouse, which is now heated up to a balmy 80 degrees. Imagine that the landlord, who hates children, requires everyone under the age of 15 to live in the sunken basement of the warehouse, which the adults can view from a huge wraparound balcony. Moreover, the only way any of the enormous number of basement-bound children can leave the warehouse is if they can pay the guard an 85-cent exit fee. This landlord is such an ogre. The adults, who at your urging have arranged the collective wealth by denomination as described above, can give money to the children only by throwing it down to them from the balcony. Let's see what happens. The person carrying pennies begins by tossing a few down, but this is far too meager a sum for any of the children to be able to afford the departure fee. And because there is an essentially infinite sea of children all ferociously fighting in a turbulent tumult for the falling money, even if the penny-entrusted adult throws enormous numbers down, no individual child will come anywhere near collecting the 85 he or she needs to pay the guard. The same is true for the adults carrying nickels, dimes, and quarters. Although each tosses down a staggeringly large total amount of money, any single child is lucky if he or she gets even one coin. Most get nothing at all. And certainly no child collects the 85 cents necessary to leave. But then, when the adult carrying dollars starts throwing them down, even comparatively tiny sums, dollar by single dollar, those lucky children who catch a single bill are able to leave immediately. Notice, though, that even as this adult loosens up and throws down barrels of dollar bills, the number of children who are able to leave increases enormously, but each has exactly 15 cents left after paying the guard. This is true regardless of the total number of dollars tossed. Here is what all this has to do with the photoelectric effect. Based on the experimental data reviewed above, Einstein suggested incorporating Planck's lumpy picture of wave energy into a new description of light. A light beam, according to Einstein, should actually be thought of as a stream of tiny packets, tiny particles of light, which were ultimately christened photons by the chemist Gilbert Lewis, an idea we made use of in our example of the light clock of Chapter 2. To get a sense of scale, according to this particle view of light, a typical 100-watt bulb emits about 100 billion 1020 photons per second. Einstein used this new conception to suggest a microscopic mechanism underlying the photoelectric effect. An electron is knocked off a metallic surface, he proposed, if it gets hit by a sufficiently energetic photon. And what determines the energy of an individual photon? To explain the experimental data, Einstein followed Planck's lead and proposed that the energy of each photon is proportional to the frequency of the light wave, with the proportionality factor being Planck's constant. Now, like the children's minimum departure fee, the electrons in a metal must be jostled by a photon possessing a certain minimum energy in order to be kicked off the surface. As with the children fighting for money, it is extremely unlikely that any one electron gets hit by more than one photon. Most don't get hit at all. But if the impinging light beam's frequency is too low, its individual photons will lack the punch necessary to eject electrons. Just as no children can afford to leave regardless of the huge total number of coins the adults shower upon them, no electrons are jostled free regardless of the huge total energy embodied in the impinging light beam, if its frequency, and thus the energy of its individual photons, is too low. But just as children are able to leave the warehouse as soon as the monetary denomination showered upon them gets large enough, electrons will be knocked off the surface as soon as the frequency of the light shone on them. Its energy denomination gets high enough. Moreover, just as the dollar-entrusted adult increases the total money thrown down by increasing the number of individual bills tossed, the total intensity of a light beam of a chosen frequency is increased by increasing the number of photons it contains. And just as more dollars result in more children being able to leave, more photons result in more electrons being hit and knocked clear off the surface. But notice that the leftover energy that each of these electrons has after ripping free of the surface depends solely on the energy of the photon that hits it, and this is determined by the frequency of the light beam, not its total intensity. Just as children leave the basement with 15 cents no matter how many dollar bills are thrown down, each electron leaves the surface with the same energy, and hence the same speed, regardless of the total intensity of the impinging light. More total money simply means more children can leave. More total energy in the light beam simply means more electrons are knocked free. If we want children to leave the basement with more money, we must increase the monetary denomination tossed down. If we want electrons to leave the surface with greater speed, we must increase the frequency of the impinging light beam. That is, we must increase the energy denomination of the photons we shine on the metallic surface. This is precisely in accord with the experimental data. The frequency of the light, its color, determines the speed of the ejected electrons. The total intensity of the light determines the number of ejected electrons. And so Einstein showed that Planck's guess of lumpy energy actually reflects a fundamental feature of electromagnetic waves. They are composed of particles, photons, that are little bundles or quanta of light. The lumpiness of the energy embodied by such waves is due to their being composed of lumps. Einstein's insight represented great progress, but, as we shall now see, the story is not as tidy as it might appear. Is it a wave, or is it a particle? Everyone knows that water, and hence water waves, are composed of a huge number of water molecules. So is it really surprising that light waves are also composed of a huge number of particles, namely photons? It is. But the surprise is in the details. You see, more than 300 years ago, Newton proclaimed that light consisted of a stream of particles, so the idea is not exactly new. However, some of Newton's colleagues, most notably the Dutch physicist Christian Huygens, disagreed with him and argued that light is a wave. The debate raged, but ultimately experiments carried out by the English physicist Thomas Young in the early 1800s showed that Newton was wrong. A version of Young's experimental setup, known as the double slit experiment, is schematically illustrated in Figure 4.3. Feynman was fond of saying that all of quantum mechanics can be gleaned from carefully thinking through the implications of this single experiment, so it's well worth discussing. As we see from Figure 4.3, gamma light is shown on a thin solid barrier in which two slits are cut. A photographic plate records the light that gets through the slits. Brighter areas of the photograph indicate more incident light. The experiment consists of comparing the images on photographic plates that result when either or both of the slits in the barrier are kept open and the light source is turned on. If the left slit is covered and the right slit is open, the photograph looks like that shown in Figure 4.4. This makes good sense, since the light that hits the photographic plate must pass through the only open slit and will therefore be concentrated around the right part of the photograph. Similarly, if the right slit is covered and the left slit open, the photograph will look like that in Figure 4.5. If both slits are open, Newton's particle picture of light leads to the prediction that the photographic plate will look like that in Figure 4.6, an amalgam of Figures 4.4 and 4.5. In essence, if you think of Newton's corpuscles of light as if they were little pellets you fire at the wall, the ones that get through will be concentrated in the two areas that line up with the two slits. The wave picture of light, on the contrary, leads to a very different prediction for what happens when both slits are open. Let's see this. Imagine for a moment that rather than dealing with light waves, we use water waves. The result we will find is the same, but water is easier to think about. When water waves strike the barrier, outgoing circular water waves emerge from each slit, much like those created by throwing a pebble into a pond, as illustrated in Figure 4.7. It is simple to try this using a cardboard barrier with 2 slits in a pan of water. As the waves emerging from each slit overlap with each other, something quite interesting happens. If 2 wave peaks overlap, the height of the water wave at that point increases. It's the sum of the heights of the 2 individual peaks. If 2 wave troughs overlap, the depth of the water depression at that point is similarly increased. And finally, if a wave peak emerging from one slit overlaps with a wave trough emerging from the other, they cancel each other out. In fact, this is the idea behind fancy noise-eliminating headphones. They measure the shape of the incoming sound wave and then produce another whose shape is exactly opposite, leading to a cancellation of the undesired noise. In between these extreme overlaps, peaks with peaks, troughs with troughs, and peaks with troughs are a host of partial height augmentations and cancellations. If you and a slew of companions form a line of little boats parallel to the barrier, and you each declare how severely you are jostled by the resulting water wave as it passes, the result will look something like that shown on the far right of Figure 4.7. Locations of significant jostling are where wave peaks or troughs from each slit coincide. Regions of minimal or no jostling are where peaks from one slit coincide with troughs from the other, resulting in a cancellation. Since the photographic plate records how much it is jostled by the incoming light, exactly the same reasoning applied to the wave picture of a light beam tells us that when both slits are open, the photograph will look like that in Figure 4.8. The brightest areas in Figure 4.8 are where light wave peaks or troughs from each slit coincide. Dark areas are where wave peaks from one slit coincide with wave troughs from the other, resulting in a cancellation. The sequence of light and dark bands is known as an interference pattern. This photograph is significantly different from that shown in Figure 4.6, and hence there is a concrete experiment to distinguish between the particle and the wave pictures of light. Young carried out a version of this experiment, and his results matched Figure 4.8, thereby confirming the wave picture. Newton's corpuscular view was defeated, although it took quite some time before physicists accepted this. The prevailing wave view of light was subsequently put on a mathematically firm foundation by Maxwell. But Einstein, the man who brought down Newton's revered theory of gravity, seems now to have resurrected Newton's particle model of light by his introduction of photons. Of course, we still face the same question. How can a particle perspective account for the interference pattern shown in Figure 4.8? At first blush, you might make the following suggestion. Water is composed of H2O molecules, the particles of water. Nevertheless, when a lot of these molecules stream along with one another, they can produce water waves, with the attendant interference properties illustrated in Figure 4.7. And so, it might seem reasonable to guess that wave properties, such as interference patterns, can arise from a particle picture of light, provided a huge number of photons, the particles of light, are involved. In reality, though, the microscopic world is far more subtle. Even if the intensity of the light source in Figure 4.8 is turned down and down, finally to the point where individual photons are being fired one by one at the barrier, say at the rate of 1 every 10 seconds, the resulting photographic plate will still look like that in Figure 4.8, so long as we wait long enough for a huge number of these separate bundles of light to make it through the slits and to each be recorded by a single dot where they hit the photographic plate. These dots will build up to form the image of an interference pattern, the image in Figure 4.8. This is astounding. How can individual photon particles that sequentially pass through the screen and separately hit the photographic plate conspire to produce the bright and dark bands of interfering waves? Conventional reasoning tells us that each and every photon passes through either the left slit or the right slit, and we would therefore expect to find the pattern shown in Figure 4.6. But we don't. If you are not bowled over by this fact of nature, it means that either you have seen it before and have become blasé, or the description so far has not been sufficiently vivid. So in case it's the latter, let's describe it again, but in a slightly different way. You close off the left slit and fire the photons one by one at the barrier. Some get through, some don't. The ones that do create an image on the photographic plate, dot by single dot, which looks like that in figure 4.4. You then run the experiment again with a new photographic plate, but this time you open both slits. Naturally enough, you think that this will only increase the number of photons that pass through the slits in the barrier and hit the photographic plate, thereby exposing the film to more total light than in your first run of the experiment. But when you later examine the image produced, you find that not only are there places on the photographic plate that were dark in the first experiment and are now bright, as expected, there are also places on the photographic plate that were bright in your first experiment but are now dark, as in figure 4.8. By increasing the number of individual photons that hit the photographic plate, you have decreased the brightness in certain areas. Somehow, temporally separated, individual particulate photons are able to cancel each other out. Think about how crazy this is. Photons that would have passed through the right slit and hit the film in one of the dark bands in figure 4.8 fail to do so when the left slit is opened, which is why the band is now dark. But how in the world can a tiny bundle of light that passes through one slit be at all affected by whether or not the other slit is open? As Feynman noted, it's as strange as if you fire a machine gun at the screen. And when both slits are open independent, separately fired bullets somehow cancel one another out, leaving a pattern of unscathed positions on the target, positions that are hit when only one slit in the barrier is open. Such experiments show that Einstein's particles of light are quite different from Newton's. Somehow, photons, although they are particles, embody wave-like features of light as well. The fact that the energy of these particles is determined by a wave-like feature, frequency, is the first clue that a strange union is occurring. But the photoelectric effect and the double-slit experiment really bring the lesson home. The photoelectric effect shows that light has particle properties. The double-slit experiment shows that light manifests the interference properties of waves. Together, they show that light has both wave-like and particle-like properties. The microscopic world demands that we shed our intuition that something is either a wave or a particle and embrace the possibility that it is both. It is here that Feynman's pronouncement that nobody understands quantum mechanics comes to the fore. We can utter words such as wave-particle duality. We can translate these words into a mathematical formalism that describes real-world experiments with amazing accuracy. But it is extremely hard to understand at a deep, intuitive level this dazzling feature of the microscopic world. Matter particles are also waves. In the first few decades of the 20th century, many of the greatest theoretical physicists grappled tirelessly to develop a mathematically sound and physically sensible understanding of these hitherto hidden microscopic features of reality. Under the leadership of Niels Bohr in Copenhagen, for example, substantial progress was made in explaining the properties of light emitted by glowing hot hydrogen atoms. But this and other work prior to the mid-1920s was more a makeshift union of 19th century ideas with newfound quantum concepts than a coherent framework for understanding the physical universe. Compared with the clear, logical framework of Newton's laws of motion or Maxwell's electromagnetic theory, the partially developed quantum theory was in a chaotic state. In 1923, the young French nobleman Prince Louis de Broglie added a new element to the quantum fray, one that would shortly help to usher in the mathematical framework of modern quantum mechanics, and that earned him the 1929 Nobel Prize in Physics. Inspired by a chain of reasoning rooted in Einstein's special relativity, de Broglie suggested that the wave-particle duality applied not only to light but to matter as well. He reasoned, roughly speaking, that Einstein's E equals sine mc2 relates mass to energy, that Planck and Einstein had related energy to the frequency of waves, and therefore, by combining the two, mass should have a wave-like incarnation as well. After carefully working through this line of thought, he suggested that just as light is a wave phenomenon that quantum theory shows to have an equally valid particle description, an electron, which we normally think of as being a particle, might have an equally valid description in terms of waves. Einstein immediately took to de Broglie's idea as it was a natural outgrowth of his own contributions of relativity and of photons. Even so, nothing is a substitute for experimental proof. Such proof was soon to come from the work of Clinton Davison and Lester Germer. In the mid-1920s, Davison and Germer, experimental physicists at the Bell Telephone Company, were studying how a beam of electrons bounces off of a chunk of nickel. The only detail that matters for us is that the nickel crystals in such an experiment act very much like the two slits in the experiment illustrated by the figures of the last section. In fact, it's perfectly okay to think of this experiment as being the same one illustrated there, except that a beam of electrons is used in place of a beam of light. We will adopt this point of view. When Davison and Germer examined electrons making it through the two slits in the barrier by allowing them to hit a phosphorescent screen that recorded the location of impact of each electron by a bright dot, essentially what happens inside a television, they found something remarkable. A pattern very much akin to that of Figure 4.8 emerged. Their experiment, therefore, showed that electrons exhibit interference phenomena, the telltale sign of waves. At dark spots on the phosphorescent screen, electrons were somehow canceling each other out, just like the overlapping peak and trough of water waves. Even if the beam of fired electrons was thinned so that, for instance, only one electron was emitted every 10 seconds, the individual electrons still built up the bright and dark bands, one spot at a time. Somehow, as with photons, individual electrons interfere with themselves in the sense that individual electrons, over time, reconstruct the interference pattern associated with waves. We are inescapably forced to conclude that each electron embodies a wave-like character in conjunction with its more familiar depiction as a particle. Although we have described this in the case of electrons, similar experiments lead to the conclusion that all matter has a wave-like character. But how does this jibe with our real-world experience of matter as being solid and sturdy and in no way wave-like? Well, de Broglie set down a formula for the wavelength of matter waves, and it shows that the wavelength is proportional to Planck's constant h. More precisely, the wavelength is given by h divided by the material body's momentum. Since h is so small, the resulting wavelengths are similarly minuscule compared with everyday scales. This is why the wave-like character of matter becomes directly apparent only upon careful microscopic investigation. Just as the large value of c, the speed of light, obscures much of the true nature of space and time, the smallness of h obscures the wave-like aspects of matter in the day-to-day world. Waves of what? The interference phenomenon found by Davison and Germer made the wave-like nature of electrons tangibly evident. But waves of what? One early suggestion made by Austrian physicist Erwin Schrödinger was that the waves were smeared-out electrons. This captured some of the feeling of an electron wave, but it was too rough. When you smear something out, part of it is here and part of it is there. However, one never encounters half of an electron or a third of an electron or any other fraction for that matter. This makes it hard to grasp what a smeared electron actually is. As an alternative, in 1926, German physicist Max Born sharply refined Schrödinger's interpretation of an electron wave, and it is his interpretation, amplified by Bohr and his colleagues, that is still with us today. Born's suggestion is one of the strangest features of quantum theory, but is supported nonetheless by an enormous amount of experimental data. He asserted that an electron wave must be interpreted from the standpoint of probability. Places where the magnitude, a bit more correctly the square of magnitude of the wave is large, are places where the electron is more likely to be found. Places where the magnitude is small are places where the electron is less likely to be found. This is truly a peculiar idea. What business does probability have in the formulation of fundamental physics? We are accustomed to probability showing up in horse races, in coin tosses, and at the roulette table. But in those cases, it merely reflects our incomplete knowledge. If we knew precisely the speed of the roulette wheel, the weight and hardness of the white marble, the location and speed of the marble when it drops to the wheel, the exact specifications of the material constituting the cubicles, and so on, and if we made use of sufficiently powerful computers to carry out our calculations, we would, according to classical physics, be able to predict with certainty where the marble would settle. Gambling casinos rely on your inability to ascertain all of this information and to do the necessary calculations prior to placing your bet. But we see that probability, as encountered at the roulette table, does not reflect anything particularly fundamental about how the world works. Quantum mechanics, on the contrary, injects the concept of probability into the universe at a far deeper level. According to Born, and more than half a century of subsequent experiments, the wave nature of matter implies that matter itself must be described fundamentally in a probabilistic manner. For macroscopic objects like a coffee cup or the roulette wheel, de Broglie's rule shows that the wave-like character is virtually unnoticeable, and for most ordinary purposes the associated quantum mechanical probability can be completely ignored. But at a microscopic level, we learn that the best we can ever do is say that an electron has a particular probability of being found at any given location. The probabilistic interpretation has the virtue that if an electron wave does what other waves can do, for instance, slam into some obstacle and develop all sorts of distinct ripples, it does not mean that the electron itself has shattered into separate pieces. Rather, it means that there are now a number of locations where the electron might be found with a non-negligible probability. In practice, this means that if a particular experiment involving an electron is repeated over and over again in an absolutely identical manner, the same answer for, say, the measured position of an electron will not be found over and over again. Rather, the subsequent repeats of the experiment will yield a variety of different results with the property that the number of times the electron is found at any given location is governed by the shape of the electron's probability wave. If the probability wave, more precisely the square of the probability wave, is twice as large at location A than at location B, then the theory predicts that in a sequence of many repeats of the experiment, the electron will be found at location A twice as often as at location B. Exact outcomes of experiments cannot be predicted. The best we can do is predict the probability that any given outcome may occur. Even so, as long as we can determine mathematically the precise form of probability waves, their probabilistic predictions can be tested by repeating a given experiment numerous times, thereby experimentally measuring the likelihood of getting one particular result or another. Just a few months after de Broglie's suggestion, Schrödinger took the decisive step toward this end by determining an equation that governs the shape and the evolution of probability waves, or as they came to be known, wave functions. It was not long before Schrödinger's equation and the probabilistic interpretation were being used to make wonderfully accurate predictions. By 1927, therefore, classical innocence had been lost. Gone were the days of a clockwork universe whose individual constituents were set in motion at some moment in the past and obediently fulfilled their inescapable, uniquely determined destiny. According to quantum mechanics, the universe evolves according to a rigorous and precise mathematical formalism, but this framework determines only the probability that any particular future will happen, not which future actually ensues. Many find this conclusion troubling or even downright unacceptable. Einstein was one. In one of physics' most time-honored utterances, Einstein admonished the quantum stalwarts that God does not play dice with the universe. He felt that probability was turning up in fundamental physics because of a subtle version of the reason it turns up at the roulette wheel, some basic incompleteness in our understanding. The universe, in Einstein's view, had no room for a future whose precise form involves an element of chance. Physics should predict how the universe evolves, not merely the likelihood that any particular evolution might occur, but experiment after experiment. Some of the most convincing ones being carried out after his death convincingly confirm that Einstein was wrong. As the British theoretical physicist Stephen Hawking has said, on this point, Einstein was confused, not the quantum theory. Nevertheless, the debate about what quantum mechanics really means continues unabated. Everyone agrees on how to use the equations of quantum theory to make accurate predictions, but there is no consensus on what it really means to have probability waves, nor on how a particle chooses which of its many possible futures to follow, nor even on whether it really does choose, or instead splits off like a branching tributary to live out all possible futures in an ever-expanding arena of parallel universes. These interpretational issues are worthy of a book-length discussion in their own right, and in fact there are many excellent books that espouse one or another way of thinking about quantum theory. But what appears certain is that no matter how you interpret quantum mechanics, it undeniably shows that the universe is founded on principles that, from the standpoint of our day-to-day experiences, are bizarre. The meta-lesson of both relativity and quantum mechanics is that when we deeply probe the fundamental workings of the universe, we may come upon aspects that are vastly different from our expectations. The boldness of asking deep questions may require unforeseen flexibility if we are to accept the answers. Feynman's perspective. Richard Feynman was one of the greatest theoretical physicists since Einstein. He fully accepted the probabilistic core of quantum mechanics, but in the years following World War II, he offered a powerful new way of thinking about the theory. From the standpoint of numerical predictions, Feynman's perspective agrees exactly with all that went before. But its formulation is quite different. Let's describe it in the context of the electron two-slit experiment. The troubling thing about figure 4.8 is that we envision each electron as passing through either the left slit or the right slit, and therefore we expect the union of figures 4.4 and 4.5, as in figure 4.6, to represent the resulting data accurately. An electron that passes through the right slit should not care that there also happens to be a left slit and vice versa, but somehow it does. The interference pattern generated requires an overlapping and an intermingling between something sensitive to both slits, even if we fire electrons one by one. Schrödinger, de Broglie, and Born explained this phenomenon by associating a probability wave to each electron. Like the water waves in figure 4.7, the electron's probability wave sees both slits and is subject to the same kind of interference from intermingling. Places where the probability wave is augmented by the intermingling, like the places of significant jostling in figure 4.7, are locations where the electron is likely to be found. Places where the probability wave is diminished by the intermingling, like the places of minimal or no jostling in figure 4.7, are locations where the electron is unlikely or never to be found. Electrons hit the phosphorescent screen one by one, distributed according to this probability profile, and thereby build up an interference pattern like that in figure 4.8. Feynman took a different tack. He challenged the basic classical assumption that each electron either goes through the left slit or the right slit. You might think this to be such a basic property of how things work that challenging it is fatuous. After all, can't you look in the region between the slits and the phosphorescent screen to determine through which slit each electron passes? You can, but now you have changed the experiment. To see the electron, you must do something to it. For instance, you can shine light on it, that is, bounce photons off it. Now, on everyday scales, photons act as negligible little probes that bounce off trees, paintings, and people with essentially no effect on the state of motion of these comparatively large material bodies. But electrons are little wisps of matter. Regardless of how gingerly you carry out your determination of the slit through which it passed, photons that bounce off the electron necessarily affect its subsequent motion. And this change in motion changes the results of our experiment. If you disturb the experiment just enough to determine the slit through which each electron passes, experiments show that the results change from that of figure 4.8 and become like that of figure 4.6. The quantum world ensures that once it has been established that each electron has gone through either the left slit or the right slit. Quantum weirdness. By now you should have some sense of the dramatically new way that the universe works according to quantum mechanics. If you have not as yet fallen victim to Bohr's dizziness dictum, the quantum weirdness we now discuss should at least make you feel a bit lightheaded. Even more so than with the theories of relativity, it is hard to embrace quantum mechanics viscerally, to think like a miniature person born and raised in the microscopic realm. There is, though, one aspect of the theory that can act as a guidepost for your intuition, as it is the hallmark feature that fundamentally differentiates quantum from classical reasoning. It is the uncertainty principle, discovered by the German physicist Werner Heisenberg in 1927. This principle grows out of an objection that may have occurred to you earlier. We noted that the act of determining the slit through which each electron passes, its position, necessarily disturbs its subsequent motion, its velocity. But, just as we can assure ourselves of someone's presence either by gently touching them or by giving them an overzealous slap on the back, why can't we determine the electron's position with an ever gentler light source in order to have an ever-decreasing impact on its motion? From the standpoint of 19th century physics, we can. By using an ever-dimmer lamp and an ever more sensitive light detector, we can have a vanishingly small impact on the electron's motion. But quantum mechanics itself illuminates a flaw in this reasoning. As we turn down the intensity of the light source, we now know that we are decreasing the number of photons it emits. Once we get down to emitting individual photons, we cannot dim the light any further without actually turning it off. There is a fundamental quantum mechanical limit to the gentleness of our probe, and hence there is always a minimal disruption that we cause to the electron's velocity through our measurement of its position. Well, that's almost correct. Planck's law tells us that the energy of a single photon is proportional to its frequency, inversely proportional to its wavelength. By using light of lower and lower frequency, larger and larger wavelength, we can therefore produce ever gentler individual photons. But here's the catch. When we bounce a wave off of an object, the information we receive is only enough to determine the object's position to within a margin of error equal to the wave's wavelength. To get an intuitive feel for this important fact, imagine trying to pinpoint the location of a large, slightly submerged rock by the way it affects passing ocean waves. As the waves approach the rock, they form a nice orderly train of one up and down wave cycle followed by another. After passing by the rock, the individual wave cycles are distorted, the telltale sign of the submerged rock's presence. But like the finest set of tick marks on a ruler, the individual up and down wave cycles are the finest units making up the wave train, and therefore, by examining solely how they are disrupted, we can determine the rock's location only to within a margin of error equal to the length of the wave cycles, that is, the wave's wavelength. In the case of light, the constituent photons are, roughly speaking, the individual wave cycles, with the height of the wave cycles being determined by the number of photons. A photon, therefore, can be used to pinpoint an object's location only to within a precision of one wavelength, and so we are faced with a quantum mechanical balancing act. If we use high-frequency, short-wavelength light, we can locate an electron with greater precision, but high-frequency photons are very energetic and therefore sharply disturb the electron's velocity. If we use low-frequency, long-wavelength light, we minimize the impact on the electron's motion, since the constituent photons have comparatively low energy, but we sacrifice precision in determining the electron's position. Heisenberg quantified this competition and found a mathematical relationship between the precision with which one measures the electron's position and the precision with which one measures its velocity. He found, in line with our discussion, that each is inversely proportional to the other. Greater precision in a position measurement necessarily entails greater imprecision in a velocity measurement, and vice versa. And of utmost importance, although we have tied our discussion to one particular means for determining the electron's whereabouts, Heisenberg showed that the trade-off between the precision of position and velocity measurements is a fundamental fact that holds true regardless of the equipment used or the procedure employed. Unlike the framework of Newton or even of Einstein, in which the motion of a particle is described by giving its location and its velocity, quantum mechanics shows that at a microscopic level you cannot possibly know both of these features with total precision. Moreover, the more precisely you know one, the less precisely you know the other. And although we have described this for electrons, the ideas directly apply to all constituents of nature. Einstein tried to minimize this departure from classical physics by arguing that although quantum reasoning certainly does appear to limit one's knowledge of the position and velocity, the electron still has a definite position and velocity exactly as we have always thought. But during the last couple of decades, theoretical progress spearheaded by the late Irish physicist John Bell and the experimental results of Alan Aspect and his collaborators have shown convincingly that Einstein was wrong. Electrons, and everything else for that matter, cannot be described as simultaneously being at such and such location and having such and such speed. Quantum mechanics shows that not only could such a statement never be experimentally verified, as explained above, but it directly contradicts other, more recently established experimental results. In fact, if you were to capture a single electron in a big solid box and then slowly crush the sides to pinpoint its position with ever greater precision, you would find the electron getting more and more frantic. Almost as if it were overcome with claustrophobia, the electron will go increasingly haywire, bouncing off of the walls of the box with increasingly frenetic and unpredictable speed. Nature does not allow its constituents to be cornered. In the H-bar, where we imagine H to be much larger than in the real world, thereby making everyday objects directly subject to quantum effects, the ice cubes in George's and Gracie's drinks frantically rattle around as they too suffer from quantum claustrophobia. Although the H-bar is a fantasy land, in reality H is terribly small. Precisely this kind of quantum claustrophobia is a pervasive feature of the microscopic realm. The motion of microscopic particles becomes increasingly wild when they are examined and confined to ever smaller regions of space. The uncertainty principle also gives rise to a striking effect known as quantum tunneling. If you fire a plastic pellet against a 10-foot thick concrete wall, classical physics confirms what your instincts tell you will happen. The pellet will bounce back at you. The reason is that the pellet simply does not have enough energy to penetrate such a formidable obstacle. But at the level of fundamental particles, quantum mechanics shows unequivocally that the wave functions, that is, the probability waves, of the particles making up the pellet, all have a tiny piece that spills out through the wall. This means that there is a small, but not zero chance that the pellet actually can penetrate the wall and emerge on the other side. How can this be? The reason comes down once again to Heisenberg's uncertainty principle. To see this, imagine that you are completely destitute and suddenly learn that a distant relative has passed on in a far-off land, leaving you a tremendous fortune to claim. The only problem is that you don't have the money to buy a plane ticket to get there. You explain the situation to your friends. If only they will allow you to surmount the barrier between you and your new fortune by temporarily lending you the money for a ticket. You can pay them back handsomely after your return. But no one has the money to lend. You remember, though, that an old friend of yours works for an airline and you implore him with the same request. Again, he cannot afford to lend you the money, but he does offer a solution. The accounting system of the airline is such that if you wire the ticket payment within 24 hours of arrival at your destination, no one will ever know that it was not paid for prior to departure. In this way, you are able to claim your inheritance. The accounting procedures of quantum mechanics are quite similar. Just as Heisenberg showed that there is a trade-off between the precision of measurements of position and velocity, he also showed that there is a similar trade-off in the precision of energy measurements and how long one takes to do the measurement. Quantum mechanics asserts that you can't say that a particle has precisely such and such energy at precisely such and such moment in time. Ever-increasing precision of energy measurements require ever longer durations to carry them out. Roughly speaking, this means that the energy a particle has can wildly fluctuate so long as this fluctuation is over a short enough timescale. So just as the accounting system of the airline allows you to borrow the money for a plane ticket provided you pay it back quickly enough, quantum mechanics allows a particle to borrow energy so long as it can relinquish it within a time frame determined by Heisenberg's uncertainty principle. The mathematics of quantum mechanics shows that the greater the energy barrier, the lower the probability that this creative microscopic accounting will actually occur. But for microscopic particles facing a concrete slab, they can, and sometimes do, borrow enough energy to do what is impossible from the standpoint of classical physics: momentarily penetrate and tunnel through a region that they do not initially have enough energy to enter. As the objects we study become increasingly complicated, consisting of more and more particle constituents, such quantum tunneling can still occur, but it becomes very unlikely since all of the individual particles must be lucky enough to tunnel together. But the shocking episodes of George's disappearing cigar, of an ice cube passing right through the wall of a glass, and of George and Gracie's passing right through a wall of the bar, can happen. In a fantasy land such as the H-bar, in which we imagine that H is large, such quantum tunneling is commonplace. But the probability rules of quantum mechanics, and in particular, the actual smallness of H in the real world, show that if you walked into a solid wall every second, You would have to wait longer than the current age of the universe to have a good chance of passing through it on one of your attempts. With eternal patience and longevity, though, you could, sooner or later, emerge on the other side. The uncertainty principle captures the heart of quantum mechanics. Features that we normally think of as being so basic as to be beyond question, that objects have definite positions and speeds and that they have definite energies at definite moments, are now seen as mere artifacts of Planck's constant being so tiny on the scales of the everyday world. Of prime importance is that when this quantum realization is applied to the fabric of spacetime, it shows fatal imperfections in the stitches of gravity, and leads us to the third and primary conflict physics has faced during the past century. Chapter 5. The Need for a New Theory: General Relativity versus Quantum Mechanics. Our understanding of the physical universe has deepened profoundly during the past century. The theoretical tools of quantum mechanics and general relativity allow us to understand and make testable predictions about physical happenings from the atomic and subatomic realms all the way through phenomena occurring on the scales of galaxies, clusters of galaxies, and beyond to the structure of the whole universe itself. This is a monumental achievement. It is truly inspiring that beings confined to one planet, orbiting a run-of-the-mill star in the far edges of a fairly ordinary galaxy, have been able, through thought and experiment, to ascertain and comprehend some of the most mysterious characteristics of the physical universe. Nevertheless, physicists by their nature will not be satisfied until they feel that the deepest and most fundamental understanding of the universe has been unveiled. This is what Stephen Hawking has alluded to as a first step toward knowing the mind of God. There is ample evidence that quantum mechanics and general relativity do not provide this deepest level of understanding. Since their usual domains of applicability are so different, most situations require the use of quantum mechanics or general relativity, but not both. Under certain extreme conditions, however, where things are very massive and very small, near the central point of black holes or the whole universe at the moment of the Big Bang, to name two examples, we require both general relativity and quantum mechanics for proper understanding. But like the mixing of fire and gunpowder, when we try to combine quantum mechanics and general relativity, their union brings violent catastrophe. Well-formulated physical problems elicit nonsensical answers when the equations of both these theories are commingled. The nonsense often takes the form of a prediction that the quantum mechanical probability for some process is not 20% or 73% or 91%, but infinity. What in the world does a probability greater than 1 mean, let alone one that is infinite? We are forced to conclude that there is something seriously wrong. By closely examining the basic properties of general relativity and quantum mechanics, we can identify what that something is: the heart of quantum mechanics. When Heisenberg discovered the uncertainty principle, physics turned a sharp corner, never to retrace its steps. Probabilities, wave functions, interference, and quanta all involve radically new ways of seeing reality. Nevertheless, a die-hard classical physicist might still have hung on to a thread of hope that when all was said and done, these departures would add up to a framework not too distant from old ways of thinking. But the uncertainty principle cleanly and definitively undercut any attempt to cling to the past. The uncertainty principle tells us that the universe is a frenetic place when examined on smaller and smaller distances and shorter timescales. We saw some evidence of this in our attempt, described in the preceding chapter, to pinpoint the location of elementary particles such as electrons. By shining light of ever higher frequency on electrons, we measure their position with ever greater precision, but at a cost since our observations become ever more disruptive. High-frequency photons have a lot of energy and therefore give the electrons a sharp kick, significantly changing their velocities. Like the frenzy in a room full of children, all of whose momentary positions you know with great accuracy but over whose velocities, the speeds and directions in which they are moving, you have almost no control, this inability to know both the positions and velocities of elementary particles implies that the microscopic realm is intrinsically turbulent. Although this example conveys the basic relationship between uncertainty and frenzy, it actually reveals only part of the story. It might lead you to think, for instance, that uncertainty arises only when we clumsy observers of nature stumble onto the scene. This is not true. The example of an electron violently reacting to being confined in a small box by rattling around at high speed takes us a bit closer to the truth. Even without direct hits from an experimenter's disruptive photon, the electron's velocity severely and unpredictably changes from one moment to the next. But even this example does not fully reveal the stunning microscopic features of nature entailed by Heisenberg's discovery. Even in the most quiescent setting imaginable, such as an empty region of space, the uncertainty principle tells us that from a microscopic vantage point, there is a tremendous amount of activity. And this activity gets increasingly agitated on ever smaller distance and timescales. Quantum accounting is essential to understand this. We saw in the preceding chapter that just as you might temporarily borrow money to overcome an important financial obstacle, a particle such as an electron can temporarily borrow energy to overcome a literal physical barrier. This is true, but quantum mechanics forces us to take the analogy one important step further. Imagine someone who is a compulsive borrower and goes from friend to friend asking for money. The shorter the time for which a friend can lend him money, the larger the loan he seeks. Borrow and return, borrow and return. Over and over again, with unflagging intensity, he takes in money only to give it back in short order. Like stock prices on a wild roller coaster day on Wall Street, the amount of money the compulsive borrower possesses at any given moment goes through extreme fluctuations. But when all is said and done, an accounting of his finances shows that he is no better off than when he began. Heisenberg's uncertainty principle asserts that a similar frantic shifting back and forth of energy and momentum is occurring perpetually in the universe on microscopic distance and time intervals. Even in an empty region of space, inside an empty box for example, the uncertainty principle says that the energy and momentum are uncertain. They fluctuate between extremes that get larger as the size of the box, and the timescale over which it is examined gets smaller and smaller. It's as if the region of space inside the box is a compulsive borrower of energy and momentum, constantly extracting loans from the universe and subsequently paying them back. But what participates in these exchanges in, for instance, a quiet, empty region of space? Everything. Literally. Energy and momentum as well is the ultimate convertible currency. E equals m times c squared tells us that energy can be turned into matter and vice versa. Thus, if an energy fluctuation is big enough, it can momentarily cause, for instance, an electron and its antimatter companion, the positron, to erupt into existence, even if the region was initially empty. Since this energy must be quickly repaid, these particles will annihilate one another after an instant, relinquishing the energy borrowed in their creation. And the same is true for all of the other forms that energy and momentum can take. Other particle eruptions and annihilations, wild electromagnetic field oscillations, weak and strong force field fluctuations. Quantum mechanical uncertainty tells us the universe is a teeming, chaotic, frenzied arena on microscopic scales. As Feynman once jested, created and annihilated, created and annihilated. What a waste of time. Since the borrowing and repaying on average cancel each other out, an empty region of space looks calm and placid when examined with all but microscopic precision. The uncertainty principle, however, reveals that macroscopic averaging obscures a wealth of microscopic activity. As we will see shortly, this frenzy is the obstacle to merging general relativity and quantum mechanics. Quantum field theory. Over the course of the 1930s and 1940s, theoretical physicists, led by the likes of Paul Dirac, Wolfgang Pauli, Julian Schwinger, Freeman Dyson, Shinichiro Tominaga, and Feynman, to name a few, struggled relentlessly to find a mathematical formalism capable of dealing with this microscopic obstreperousness. They found that Schrödinger's quantum wave equation, mentioned in Chapter 4, was actually only an approximate description of microscopic physics, an approximation that works extremely well when one does not probe too deeply into the microscopic frenzy, either experimentally or theoretically, but that certainly fails if one does. The central piece of physics that Schrödinger ignored in his formulation of quantum mechanics is special relativity. In fact, Schrödinger did try to incorporate special relativity initially, but the quantum equation to which this led him made predictions that proved to be at odds with experimental measurements of hydrogen. This inspired Schrödinger to adopt the time-honored tradition in physics of divide and conquer. Rather than trying through one leap to incorporate all we know about the physical universe in developing a new theory, it is often far more profitable to take many small steps that sequentially include the newest discoveries from the forefront of research. Schrödinger sought and found a mathematical framework encompassing the experimentally discovered wave-particle duality, but he did not, at that early stage of understanding, incorporate special relativity. But physicists soon realized that special relativity was central to a proper quantum mechanical framework. This is because the microscopic frenzy requires that we recognize that energy can manifest itself in a huge variety of ways, a notion that comes from the special relativistic declaration E equals sign ms2. By ignoring special relativity, Schrödinger's approach ignored the malleability of matter, energy, and motion. Physicists as focus their initial path-breaking efforts to merge special relativity with quantum concepts on the electromagnetic force and its interactions with matter. Through a series of inspirational developments, they created quantum electrodynamics. This is an example of what has come to be called a relativistic quantum field theory, or a quantum field theory for short. It's quantum because all of the probabilistic and uncertainty issues are incorporated from the outset. It's a field theory because it merges the quantum principles into the previous classical notion of a force field, in this case, Maxwell's electromagnetic field. And finally, it's relativistic because special relativity is also incorporated from the outset. If you'd like a visual metaphor for a quantum field, you can pretty much invoke the image of a classical field, say as an ocean of invisible field lines permeating space. But you should refine this image in two ways. First, you should envision a quantum field as composed of particulate ingredients, such as photons for the electromagnetic field. Second, you should imagine energy in the form of particles' masses and their motion, endlessly shifting back and forth from one quantum field to another as they continually vibrate through space and time. Quantum electrodynamics is arguably the most precise theory of natural phenomena ever advanced. An illustration of its precision can be found in the work of Toichiro Kinoshita, a particle physicist from Cornell University who has, over the last 30 years, painstakingly used quantum electrodynamics to calculate certain detailed properties of electrons. Kinoshita's calculations fill thousands of pages and have ultimately required the most powerful computers in the world to complete. But the effort has been well worth it. The calculations yield predictions about electrons that have been experimentally verified to an accuracy of better than 1 part in a billion. This is an absolutely astonishing agreement between abstract theoretical calculation and the real world. Through quantum electrodynamics, physicists have been able to solidify the role of photons as the smallest possible bundles of light, and to reveal their interactions with electrically charged particles such as electrons, in a mathematically complete, predictive, and convincing framework. The success of quantum electrodynamics inspired other physicists in the 1960s and 1970s to try an analogous approach for developing a quantum mechanical understanding of the weak, the strong, and the gravitational forces. For the weak and the strong forces, this proved to be an immensely fruitful line of attack. In analogy with quantum electrodynamics, physicists were able to construct quantum field theories for the strong and the weak forces, called quantum chromodynamics and quantum electroweak theory. Quantum chromodynamics is a more colorful name than the more logical quantum strong dynamics, but it is just a name without any deeper meaning. On the other hand, the name electroweak does summarize an important milestone in our understanding of the forces of nature. Through their Nobel Prize-winning work, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that the weak and electromagnetic forces are naturally united by their quantum field theoretic description, even though their manifestations seem to be utterly distinct in the world around us. After all, weak force fields diminish to almost vanishing strength on all but subatomic distance scales, whereas electromagnetic fields, visible light, radio and TV signals, X-rays, have an indisputable macroscopic presence. Nevertheless, Glashow, Salam, and Weinberg showed, in essence, that at high enough energy and temperature, such as occurred a mere fraction of a second after the Big Bang, electromagnetic and weak force fields dissolve into one another, take on indistinguishable characteristics, and are more accurately called electroweak fields. When the temperature drops, as it has done steadily since the Big Bang, the electromagnetic and weak forces crystallize out in a different manner from their common high-temperature form, through a process known as symmetry breaking that we will describe later, and therefore appear to be distinct in the cold universe we currently inhabit. And so, if you are keeping score, by the 1970s, physicists had developed a sensible and successful quantum mechanical description of 3 of the 4 forces, strong, weak, electromagnetic, and had shown that 2 of the 3, weak and electromagnetic, actually share a common origin, the electroweak force. During the past 2 decades, physicists have subjected this quantum mechanical treatment of the 3 non-gravitational forces, as they act among themselves and the matter particles introduced in Chapter 1, to an enormous amount of experimental scrutiny. The theory has met all such challenges with aplomb. Once experimentalists measure some 19 parameters, the masses of the particles in Table 1.1, their force charges as recorded in the table in EndNote 1 to Chapter 1, the strengths of the 3 non-gravitational forces in Table 1.2, as well as a few other numbers we need not discuss. And theorists input these numbers into the quantum field theories of the matter particles and the strong, weak, and electromagnetic forces. The subsequent predictions of the theory regarding the microcosmos agree spectacularly with experimental results. This is true up to the energies capable of pulverizing matter into bits as small as a billionth of a meter, the current technological limit. For this reason, physicists call the theory of the 3 non-gravitational forces and the 3 families of matter particles the standard theory, or more often, the standard model of particle physics. Messenger particles. According to the standard model, just as the photon is the smallest constituent of an electromagnetic field, the strong and the weak force fields have smallest constituents as well. As we discussed briefly in Chapter 1, the smallest bundles of the strong force are known as gluons, and those of the weak force are known as weak-gauge bosons, or more precisely, the W and Z bosons. The Standard Model instructs us to think of these force particles as having no internal structure. In this framework, they are every bit as elementary as the particles in the 3 families of matter. The photons, gluons, and weak-gauge bosons provide the microscopic mechanism for transmitting the forces they constitute. For example, when one electrically charged particle repels another of like electric charge, you can think of it roughly in terms of each particle being surrounded by an electric field, a cloud or mist of electric essence, and the force each particle feels arises from the repulsion between their respective force fields. The more precise microscopic description of how they repel each other, though, is somewhat different. An electromagnetic field is composed of a swarm of photons. The interaction between 2 charged particles actually arises from their shooting photons back and forth between themselves. In rough analogy to the way in which you can affect a fellow ice skater's motion and your own by hurling a barrage of bowling balls at him or her, 2 electrically charged particles influence each other by exchanging the smallest bundles of light. An important failing of the ice skater analogy is that the exchange of bowling balls is always repulsive. It always drives the skaters apart. On the contrary, 2 oppositely charged particles also interact through the exchange of photons, although the resulting electromagnetic force is attractive. It's as if the photon is not so much the transmitter of the force per se, but rather the transmitter of a message of how the recipient must respond to the force in question. For like-charged particles, the photon carries the message "move apart," while for oppositely charged particles it carries the message "come together." For this reason, the photon is sometimes referred to as the messenger particle for the electromagnetic force. Similarly, the gluons and weak-gauge bosons are the messenger particles for the strong and weak nuclear forces. The strong force, which keeps quarks locked up inside of protons and neutrons, arises from individual quarks exchanging gluons. The gluons, so to speak, provide the glue that keeps these subatomic particles stuck together. The weak force, which is responsible for certain kinds of particle transmutations involved in radioactive decay, is mediated by the weak-gauge bosons. Gauge symmetry. You may have realized that the odd man out in our discussion of the quantum theory of the forces of nature is gravity. Given the successful approach physicists have used with the other three forces, you might suggest that physicists seek a quantum field theory of the gravitational force, a theory in which the smallest bundle of a gravitational force field, the graviton, would be its messenger particle. At first sight, as we now note, this suggestion would appear to be particularly apt because the quantum field theory of the three non-gravitational forces reveals that there is a tantalizing similarity between them and an aspect of the gravitational force we encountered in Chapter 3. Recall that the gravitational force allows us to declare that all observers, regardless of their state of motion, are on absolutely equal footing. Even those whom we would normally think of as accelerating may claim to be at rest, since they can attribute the force they feel to their being immersed in a gravitational field. In this sense, gravity enforces the symmetry. It ensures the equal validity of all possible observational points of view, all possible frames of reference. The similarity with the strong, weak, and electromagnetic forces is that they too are all connected with enforcing symmetries, albeit ones that are significantly more abstract than the one associated with gravity. To get a rough feel for these rather subtle symmetry principles, let's consider one important example. As we recorded in the table in EndNote 1 of Chapter 1, each quark comes in three colors, fancifully called red, green, and blue, although these are merely labels and have no relation to color in the usual visual sense, which determine how it responds to the strong force in much the same way that its electric charge determines how it responds to the electromagnetic force. All the data that have been collected establish that there is a symmetry among the quarks in the sense that we illustrate this in Figure 5.1 by zooming in and sequentially magnifying ever smaller regions of the spatial fabric. At first, as we zoom in, not much happens. As we see in the first three levels of magnification in Figure 5.1, the structure of space retains the same basic form. Reasoning from a purely classical standpoint, we would expect this placid and flat image of space to persist all the way to arbitrarily small length scales. But quantum mechanics changes this conclusion radically. Everything is subject to the quantum fluctuations inherent in the uncertainty principle, even the gravitational field. Although classical reasoning implies that empty space has zero gravitational field, quantum mechanics shows that on average it is zero, but that its actual value undulates up and down due to quantum fluctuations. Moreover, the uncertainty principle tells us that the size of the undulations of the gravitational field gets larger as we focus our attention on smaller regions of space. Quantum mechanics shows that nothing likes to be cornered. Narrowing the spatial focus leads to ever larger undulations. As gravitational fields are reflected by curvature, these quantum fluctuations manifest themselves as increasingly violent distortions of the surrounding space. We see the glimmers of such distortions emerging in the fourth level of magnification in Figure 5.1. By probing to even smaller distance scales as we do in the fifth level of Figure 5.1, we see that the random quantum mechanical undulations in the gravitational field correspond to such severe warpings of space that it no longer resembles a gently curving geometrical object, such as the rubber membrane analogy used in our discussion in Chapter 3. Rather, it takes on the frothing, turbulent, twisted form illustrated in the uppermost part of the figure. John Wheeler coined the term quantum foam to describe the frenzy revealed by such an ultramicroscopic examination of space and time. It describes an unfamiliar arena of the universe in which the conventional notions of left and right, back and forth, up and down, and even of before and after lose their meaning. It is on such short-distance scales that we encounter the fundamental incompatibility between general relativity and quantum mechanics. The notion of a smooth spatial geometry, the central principle of general relativity, is destroyed by the violent fluctuations of the quantum world on short-distance scales. On ultramicroscopic scales, the central feature of quantum mechanics, the uncertainty principle, is in direct conflict with the central feature of general relativity, the smooth geometrical model of space and of spacetime. In practice, this conflict rears its head in a very concrete manner. Calculations that merge the equations of general relativity and those of quantum mechanics typically yield one and the same ridiculous answer: infinity, Like a sharp rap on the wrist from an old-time school teacher, an infinite answer is nature's way of telling us that we are doing something that is quite wrong. The equations of general relativity cannot handle the roiling frenzy of quantum foam. Notice, however, that as we recede to more ordinary distances, following the sequence of drawings in Figure 5.1 in reverse, the random, violent small-scale undulations cancel each other out, in much the same way that, on average, our compulsive borrower's bank account shows no evidence of his compulsion. And the concept of a smooth geometry for the fabric of the universe once again becomes accurate. It's like what you experience when you look at a dot matrix picture. From far away, the dots that compose the picture blend together and create the impression of a smooth image, whose variations in lightness seamlessly and gently change from one area to another. When you inspect the picture on finer distance scales, you realize, however, that it markedly differs from its smooth, long-distance appearance. It is nothing but a collection of discrete dots, each quite separate from the others. But note that you become aware of the discrete nature of the picture only when you examine it on the smallest of scales. From far away, it looks smooth. Similarly, the fabric of spacetime appears to be smooth except when examined with ultra-microscopic precision. This is why general relativity works on large enough distance and time scales, the scales relevant for many typical astronomical applications, but is rendered inconsistent on short distance and time scales. The central tenet of a smooth and gently curving geometry is justified in the large but breaks down due to quantum fluctuations when pushed to the small. The basic principles of general relativity and quantum mechanics allow us to calculate the approximate distance scales below, which one would have to shrink in order for the pernicious phenomenon of Figure 5.1 to become apparent. The smallness of Planck's constant, which governs the strength of quantum effects, and the intrinsic weakness of the gravitational force team up to yield a result called the Planck length, which is small almost beyond imagination, a millionth of a billionth of a billionth of a billionth of a centimeter, Wem to the power of minus 33 centimeter. The fifth level in Figure 5.1 thus schematically depicts the ultra-microscopic, sub-Planck length landscape of the universe. To get a sense of scale, if we were to magnify an atom to the size of the known universe, the Planck length would barely expand to the height of an average tree. And so we see that the incompatibility between general relativity and quantum mechanics becomes apparent only in a rather esoteric realm of the universe. For this reason, you might well ask whether it's worth worrying about. In fact, the physics community does not speak with a unified voice when addressing this issue. There are those physicists who are willing to note the problem, but happily go about using quantum mechanics and general relativity for problems whose typical lengths far exceed the Planck length, as their research requires. There are other physicists, however, who are deeply unsettled by the fact that the two foundational pillars of physics as we know it are at their core fundamentally incompatible, regardless of the ultra-microscopic distances that must be probed to expose the problem. The incompatibility, they argue, points to an essential flaw in our understanding of the physical universe. This opinion rests on an unprovable but profoundly felt view that the universe, if understood at its deepest and most elementary level, can be described by a logically sound theory whose parts are harmoniously united, and surely regardless of how central this incompatibility is to their own research. Most physicists find it hard to believe that at rock bottom, our deepest theoretical understanding of the universe will be composed of a mathematically inconsistent patchwork of two powerful yet conflicting explanatory frameworks. Physicists have made numerous attempts at modifying either general relativity or quantum mechanics in some manner so as to avoid the conflict. But the attempts, although often bold and ingenious, have met with failure after failure. That is until the discovery of superstring theory. Part 3. The Cosmic Symphony. Chapter 6. Nothing but Music. The Essentials of Superstring Theory. Music has long since provided the metaphors of choice for those puzzling over questions of cosmic concern. From the ancient Pythagorean music of the spheres to the harmonies of nature that have guided inquiry through the ages, we have collectively sought the song of nature in the gentle wanderings of celestial bodies and the riotous fulminations of subatomic particles. With the discovery of superstring theory, musical metaphors take on a startling reality, for the theory suggests that the microscopic landscape is suffused with tiny strings whose vibrational patterns orchestrate the evolution of the cosmos. The winds of change, according to superstring theory, gust through an Aeolian universe. By contrast, the Standard Model views the elementary constituents of the universe as point-like ingredients with no internal structure. As powerful as this approach is, as we have mentioned, essentially every prediction about the micro-world made by the Standard Model has been verified down to about a billionth of a meter, the present-day technological limit. The Standard Model cannot be a complete or final theory because it does not include gravity. Moreover, attempts to incorporate gravity into its quantum mechanical framework have failed due to the violent fluctuations in the spatial fabric that appear at ultra-microscopic distances, that is, distances shorter than the Planck length. The unresolved conflict has impelled a search for an even deeper understanding of nature. In 1984, the physicists Michael Greene, then of Queen Mary College, and John Schwartz of the California Institute of Technology provided the first piece of convincing evidence that superstring theory, or string theory for short, might well provide this understanding. String theory offers a novel and profound modification to our theoretical description of the ultra-microscopic properties of the universe, a modification that physicists slowly realized alters Einstein's general relativity in just the right way to make it fully compatible with the laws of quantum mechanics. According to string theory, the elementary ingredients of the universe are not point particles. Rather, they are tiny, one-dimensional filaments somewhat like infinitely thin rubber bands vibrating to and fro. But don't let the name fool you. Unlike an ordinary piece of string, which is itself composed of molecules and atoms, the strings of string theory are purported to lie deeply within the heart of matter. The theory proposes that they are ultra-microscopic ingredients making up the particles out of which atoms themselves are made. The strings of string theory are so small, on average they are about as long as the Planck length, that they appear point-like even when examined with our most powerful equipment. Yet the simple replacement of point particles with strands of string as the fundamental ingredients of everything has far-reaching consequences. First and foremost, string theory appears to resolve the conflict between general relativity and quantum mechanics. As we shall see, the spatially extended nature of a string is the crucial new element allowing for a single harmonious framework incorporating both theories. Second, string theory provides a truly unified theory, since all matter and all forces are proposed to arise from one basic ingredient: oscillating strings. Finally, as discussed more fully in subsequent chapters, beyond these remarkable achievements, string theory once again radically changes our understanding of spacetime. A brief history of string theory. In 1968, a young theoretical physicist named Gabriele Veneziano was struggling to make sense of various experimentally observed properties of the strong nuclear force. Veneziano, then a research fellow at CERN, the European Accelerator Laboratory in Geneva, Switzerland, had worked on aspects of this problem for a number of years until one day he came upon a striking revelation. Much to his surprise, he realized that an esoteric formula concocted for purely mathematical pursuits by the renowned Swiss mathematician Leonhard Euler some 200 years earlier, the so-called Euler beta function, seemed to describe numerous properties of strongly interacting particles in one fell swoop. Veneziano's observation provided a powerful mathematical encapsulation of many features of the strong force, and it launched an intense flurry of research aimed at using Euler's beta function and various generalizations to describe the surfeit of data being collected at various atom smashers around the world. Nevertheless, there was a sense in which Veneziano's observation was incomplete. Like memorized formulae used by a student who does not understand their meaning or justification, Euler's beta function seemed to work, but no one knew why. It was a formula in search of an explanation. This changed in 1970 when the works of Yoichiro Nambu of the University of Chicago, Holger Nielsen of the Niels Bohr Institute, and Leonard Susskind of Stanford University revealed the hitherto unknown physics lurking behind Euler's formula. These physicists showed that if one modeled elementary particles as little, vibrating, one-dimensional strings, their nuclear interactions could be described exactly by Euler's function. If the pieces of string were small enough, they reasoned, they would still look like point particles, and hence could be consistent with experimental observations. Although this provided an intuitively simple and pleasing theory, it was not long before the string description of the strong force was shown to fail. During the early 1970s, high-energy experiments capable of probing the subatomic world more deeply showed that the string model made a number of predictions that were in direct conflict with observations. At the same time, the point-particle quantum field theory of quantum chromodynamics was being developed, and its overwhelming success in describing the strong force led to the dismissal of string theory. Most particle physicists thought that string theory had been relegated to the dustbin of science, but a few dedicated researchers kept at it. Schwartz, for instance, felt that the mathematical structure of string theory was so beautiful and had so many miraculous properties that it had to be pointing towards something deep. One of the problems physicists found with string theory was that it seemed to have a true embarrassment of riches. The theory contained configurations of vibrating string that had properties akin to those of gluons, substantiating its early claim of being a theory of the strong force. But beyond these, it contained additional messenger-like particles that did not appear to have any relevance to experimental observations of the strong force. In 1974, Schwartz and Jules Scherk of the École Normale Supérieure made a bold leap that transformed this apparent vice into a virtue. After studying the puzzling messenger-like patterns of string vibration, they realized that their properties matched perfectly those of the hypothesized messenger particle of the gravitational force, the graviton. Although these smallest bundles of the gravitational force have as yet never been seen, theorists can confidently predict certain basic features that they must possess, and Scherk and Schwartz found these properties to be realized exactly by certain vibrational patterns. Based on this, Scherk and Schwartz suggested that string theory had failed in its initial attempt because physicists had unduly constrained its scope. String theory is not just a theory of the strong force, they proclaimed. It is a quantum theory that includes gravity as well. The physics community did not receive this suggestion with unbridled enthusiasm. In fact, Schwartz recounts that our work was universally ignored. The path of progress was already littered with numerous failed attempts to unite gravity and quantum mechanics. String theory had been shown wrong in its initial effort to describe the strong force, and it seemed to many that it was senseless to try to use the theory to pursue an even grander goal. Even more devastating, subsequent studies during the late 1970s and early 1980s showed that string theory and quantum mechanics suffered from their own subtle conflicts. It appeared that the gravitational force had, once again, resisted incorporation into the microscopic description of the universe. Such was the case until 1984. In a landmark paper culminating more than a dozen years of intense research that had been largely ignored and often outright dismissed by most physicists, Greene and Schwartz established that the subtle quantum conflict afflicting string theory could be resolved. Moreover, they showed that the resulting theory had sufficient breadth to encompass all of the four forces and all of matter as well. As word of this result spread throughout the worldwide physics community, particle physicists by the hundreds dropped their research projects to launch a full-scale assault on what appeared to be the last theoretical battleground in the ancient quest to understand the deepest workings of the universe. I began graduate school at Oxford University in October 1984. Although I was excited to be learning about the likes of quantum field theory, gauge theory, and general relativity, there was a pervasive feeling among the older graduate students that there was little or no future for particle physics. The Standard Model was in place, and its remarkable success at predicting experimental outcomes indicated that its verification was merely a matter of time and details. Going beyond its limits to include gravity, and possibly to explain the experimental input on which it relies, the 19 numbers summarizing the elementary particle masses, their force charges, and the relative strengths of the forces, numbers that are known from experiment but are not understood theoretically, was so daunting a task that all but the most courageous physicists recoiled at the challenge. But 6 months later, the mood had swung completely around. The success of Greene and Schwartz finally trickled down even to first-year graduate students, and an electrifying sense of being on the inside of a profound moment in the history of physics displaced the previous ennui. A number of us consistently worked deep into the night to try to master the vast areas of theoretical physics and abstract mathematics that are required to understand string theory. The period from 1984 to 1986 has come to be known as the first superstring revolution. During those 3 years, more than 1,000 research papers on string theory were written by physicists from around the world. These works showed conclusively that numerous features of the Standard Model, features that had been painstakingly discovered over the course of decades of research, emerged naturally and simply from the grand structure of string theory. As Michael Greene has said, "The moment you encounter string theory and realize that almost all of the major developments in physics over the last 100 years emerge with significantly beyond our present capacity, each would be seen to be made of a single, tiny, oscillating loop of string. For reasons that will become clear, the length of a typical string loop is about the Planck length, about 100 billion times smaller than an atomic nucleus. It is no wonder that our present-day experiments are unable to resolve the microscopic, stringy nature of matter. Strings are minute even on the scales set by subatomic particles. We would need an accelerator to slam matter together with energies some billion times more powerful than any previously constructed in order to reveal directly that a string is not a point particle. We will describe shortly the stunning implications that follow from replacing point particles by strings, but let's first address a more basic question. What are strings made of? There are 2 possible answers to this question. First, strings are truly fundamental. They are atoms, uncuttable constituents in the truest sense of the ancient Greeks. As the absolute smallest constituents of anything and everything, they represent the end of the line, the last of the Russian Matryoshka dolls, in the numerous layers of substructure in the microscopic world. From this perspective, even though strings have spatial extent, the question of their composition is without any content. Were strings to be made of something smaller, they would not be fundamental. Instead, whatever strings were composed of would immediately displace them and lay claim to being an even more basic constituent of the universe. Using our linguistic analogy, paragraphs are made of sentences. Sentences are made of words, and words are made of letters. What makes up a letter? From a linguistic standpoint, that's the end of the line. Letters are letters. They are the fundamental building blocks of written language. There is no further substructure. Questioning their composition has no meaning. Similarly, a string is simply a string. As there is nothing more fundamental, it can't be described as being composed of any other substance. That's the first answer. The second answer is based on the simple fact that as yet we do not know if string theory is a correct or final theory of nature. If string theory is truly off the mark, then, well, we can forget strings and the irrelevant question of their composition. Although this is a possibility, research since the mid-1980s overwhelmingly points toward its being extremely unlikely. But history surely has taught us that every time our understanding of the universe deepens, we find yet smaller microscopic ingredients constituting a finer level of matter. And so another possibility, should strings fail to be the final theory, is that they are one more layer in the cosmic onion, a layer that becomes visible at the Planck length, although not the final layer. In this case, strings could be made up of yet smaller structures. String theorists have raised and continue to pursue this possibility. To date, there are intriguing hints in theoretical studies that strings may have further substructure, but there is as yet no definitive evidence. Only time and intense research will supply the final word on this question. Aside from a few speculations in chapters 12 and 15, for our discussion here, we approach strings in the manner proposed in the first answer. That is, we will take strings to be nature's most fundamental ingredient, unification through string theory. Besides its inability to incorporate the gravitational force, the Standard Model has another shortcoming. There is no explanation for the details of its construction. Why did nature select the particular list of particles and forces outlined in previous chapters and recorded in tables 1.1 and 1.2? Why do the 19 parameters that describe these ingredients quantitatively have the values that they do? You can't help feeling that their number and detailed properties seem so arbitrary. Is there a deeper understanding lurking behind these seemingly random ingredients? Or were the detailed physical properties of the universe chosen by happenstance? The Standard Model itself cannot possibly offer an explanation since it takes the list of particles and their properties as experimentally measured input. Just as the performance of the stock market cannot be used to determine the value of your portfolio without the input data of your initial investments, the Standard Model cannot be used to make any predictions without the input data of the fundamental particle properties. After experimental particle physicists fastidiously measure these data, theorists can then use the Standard Model to make testable predictions, such as what should happen when particular particles are slammed together in an accelerator. But the Standard Model can no more explain the fundamental particle properties of tables 1.1 and 1.2 than the Dow Jones average today can explain your initial investment in stocks 10 years ago. In fact, had experiments revealed a somewhat different particle content in the microscopic world, possibly interacting with somewhat different forces, these changes could have been fairly easily incorporated in the Standard Model by providing the theory with different input parameters. The structure of the Standard Model in this sense is too flexible to be able to explain the properties of the elementary particles, as it could have accommodated a range of possibilities. String theory is dramatically different. It is a unique and inflexible theoretical edifice. It requires no input beyond a single number, described below, that sets the benchmark scale for measurements. All properties of the microworld are within the realm of its explanatory power. To understand this, let's first think about more familiar strings, such as those on a violin. Each such string can undergo a huge variety, in fact infinite in number, of different vibrational patterns known as resonances, such as those shown in Figure 6.1. These are the wave patterns whose peaks and troughs are evenly spaced and fit perfectly between the string's two fixed endpoints. Our ears sense these different resonant vibrational patterns as different musical notes. The strings in string theory have similar properties. There are resonant vibrational patterns that the string can support by virtue of their evenly spaced peaks and troughs exactly fitting along its spatial extent. Some examples are given in Figure 6.2. Here's the central fact. Just as the different vibrational patterns of a violin string give rise to different musical notes, the different vibrational patterns of a fundamental string give rise to different masses and force charges. As this is a crucial point, let's say it again. According to string theory, the properties of an elementary particle, its mass and its various force charges, are determined by the precise resonant pattern of vibration that its internal string executes. It's easiest to understand this association for a particle's mass. The energy of a particular vibrational string pattern depends on its amplitude, the maximum displacement between peaks and troughs, and its wavelength, the separation between one peak and the next. The greater the amplitude and the shorter the wavelength, the greater the energy. This reflects what you would expect intuitively. More frantic vibrational patterns have more energy, while less frantic ones have less energy. We give a couple of examples in Figure 6.3. This is again familiar, as violin strings that are plucked more vigorously will vibrate more wildly, while those plucked more gingerly will vibrate more gently. Now, from special relativity, we know that energy and mass are two sides of the same coin. Greater energy means greater mass, and vice versa. Thus, according to string theory, the mass of an elementary particle is determined by the energy of the vibrational pattern of its internal string. Heavier particles have internal strings that vibrate more energetically, while lighter particles have internal strings that vibrate less energetically. Since the mass of a particle determines its gravitational properties, we see that there is a direct association between the pattern of string vibration and a particle's response to the gravitational force. Although the reasoning involved is somewhat more abstract, physicists have found that a similar alignment exists between other detailed aspects of a string's pattern of vibration and its properties vis-a-vis other forces. The electric charge, the weak charge, and the strong charge carried by a particular string, for instance, are determined by the precise way it vibrates. Moreover, exactly the same idea holds for the messenger particles themselves. Particles like photons, weak-gauge bosons, and gluons are yet other resonant patterns of string vibration, and of particular importance among the vibrational string patterns, one matches perfectly the properties of the graviton, ensuring that gravity is an integral part of string theory. So we see that, according to string theory, The observed properties of each elementary particle arise because its internal string undergoes a particular resonant vibrational pattern. This perspective differs sharply from that espoused by physicists before the discovery of string theory. In the earlier perspective, the differences among the fundamental particles were explained by saying that, in effect, each particle species was cut from a different fabric. Although each particle was viewed as elementary, the kind of stuff each embodied was thought to be different. Electron stuff, for example, had negative electric charge, while neutrino stuff had no electric charge. String theory alters this picture radically by declaring that the stuff of all matter and all forces is the same. Each elementary particle is composed of a single string. That is, each particle is a single string, and all strings are absolutely identical. Differences between the particles arise because their respective strings undergo different resonant vibrational patterns. What appear to be different elementary particles are actually different notes on a fundamental string. The universe, being composed of an enormous number of these vibrating strings, is akin to a cosmic symphony. This overview shows how string theory offers a truly wonderful unifying framework. Every particle of matter and every transmitter of force consists of a string whose pattern of vibration is its fingerprint. Because every physical event, process, or occurrence in the universe is, at its most elementary level, describable in terms of forces acting between these elementary material constituents, string theory provides the promise of a single, all-inclusive, unified description of the physical universe, a theory of everything, the music of string theory. Even though string theory does away with the previous concept of structureless elementary particles, old language dies hard, especially when it provides an accurate description of reality down to the most minute of distant scales. Following the common practice of the field, we shall therefore continue to refer to elementary particles, yet we will always mean what appear to be elementary particles but are actually tiny pieces of vibrating string. In the preceding section, we proposed that the masses and the force charges of such elementary particles are the result of the way in which their respective strings are vibrating. This leads us to the following realization. If we can work out precisely the allowed resonant vibrational patterns of fundamental strings, the notes, so to speak, that they can play, we should be able to explain the observed properties of the elementary particles. For the first time, therefore, string theory sets up a framework for explaining the properties of the particles observed in nature. At this stage, then, we should grab hold of a string and pluck it in all sorts of ways to determine the possible resonant patterns of vibration. If string theory is right, we should find that the possible patterns yield exactly the observed properties of the matter and force particles in tables 1.1 and 1.2. Of course, a string is too small to carry out this experiment literally as described. Rather, by using mathematical descriptions, we can theoretically pluck a string. In the mid-1980s, many string adherents believed that the mathematical analysis required for doing this was on the verge of being able to explain every detailed property of the universe on its most microscopic level. Some enthusiastic physicists declared that the TOE had finally been discovered. More than a decade of hindsight has shown that the euphoria generated by this belief was premature. String theory has the makings of a TOE, but a number of hurdles remain, preventing us from deducing the spectrum of string vibrations with the precision necessary to compare with experimental results. At the present time, therefore, we do not know if the fundamental characteristics of our universe, summarized in tables 1.1 and 1.2, can be explained by string theory. As we will discuss in Chapter 9, under certain assumptions that we will clearly state, string theory can give rise to a universe with properties that are in qualitative agreement with the known particle and force data, but extracting detailed numerical predictions from the theory is currently beyond our abilities. And so, although the framework of string theory, unlike that of the point-particle standard model, is capable of giving an explanation for why the particles and forces have the properties they do, we have not, as yet, been able to extract it. But remarkably, string theory is so rich and far-reaching that, even though we cannot yet determine its most detailed properties, we are able to gain insight into a wealth of the new physical phenomena that follow from the theory, as we will see in subsequent chapters. In the following chapters, we shall also discuss the status of the hurdles in some detail, but it is instructive first to understand them at a general level. Strings in the world around us come with a variety of tensions. The string laced through a pair of shoes, for example, is usually quite slack compared to the string stretched from one end of a violin to another. Both of these, in turn, are under far less tension than the steel strings of a piano. The one number that string theory requires in order to set its overall scale is the corresponding tension on its loops. How is this tension determined? Well, if we could pluck a fundamental string, we would learn about its stiffness, and in this way we could measure its tension much as is done to measure the tension of more familiar everyday strings. But since fundamental strings are so tiny, this approach cannot be carried out and a more indirect method is called for. In 1974, when Shirk and Schwartz proposed that one particular pattern of string vibration was the graviton particle, they were able to exploit such an indirect approach and thereby predict the tension on the strings of string theory. Their calculations revealed that the strength of the force transmitted by the proposed graviton pattern of string vibration is inversely proportional to the string's tension. And since the graviton is supposed to transmit the gravitational force, a force that is intrinsically quite feeble, they found that this implies a colossal tension of 1,000 billion 1039 tons, the so-called Planck tension. Fundamental strings are therefore extremely stiff compared with more familiar examples. This has three important consequences. Three consequences of stiff strings. First, whereas the ends of a violin or a piano string are pinned down, ensuring that they have a fixed length, no analogous constraining frame pins down the size of a fundamental string. Instead, the huge string tension causes the loops of string theory to contract to a minuscule size. Detailed calculation reveals that being under Planck tension translates into a typical string having Planck length 10 to the power of minus 33 centimeters, as previously mentioned. Second, because of the enormous tension, the typical energy of a vibrating loop in string theory is extremely high. To understand this, we note that the greater the tension a string is under, the harder it is to get it to vibrate. For instance, it's far easier to pluck a violin string and set it vibrating than it is to pluck a piano string. Two strings, therefore, that are under different tension and are vibrating in precisely the same way will not have the same energy. The string with higher tension will have more energy than the string with lower tension, since more energy must be exerted to set it in motion. This alerts us to the fact that the energy of a vibrating string is determined by two things: the precise manner in which it vibrates, more frantic patterns corresponding to higher energies, and the tension of the string, higher tension corresponding to higher energy. At first, this description might lead you to think that by taking on ever gentler vibrational patterns with ever smaller amplitudes and fewer peaks and troughs, a string can embody less and less energy. But, as we found in Chapter 4 in a different context, quantum mechanics tells us that this reasoning is not right. Like all vibrations or wave-like disturbances, quantum mechanics implies that they can exist only in discrete units. Roughly speaking, just as the money carried by a comrade in the warehouse is a whole number multiple of the monetary denomination with which he or she is entrusted, the energy embodied in a string vibrational pattern is a whole number multiple of a minimal energy denomination. In particular, this minimal energy denomination is proportional to the tension of the string, and it is also proportional to the number of peaks and troughs in the particular vibrational pattern, while the whole number multiple is determined by the amplitude of the vibrational pattern. The key point for the present discussion is this. Since the minimal energy denominations are proportional to the string's tension, and since this tension is enormous, the fundamental minimal energies are, on the usual scales of elementary particle physics, similarly huge. They are multiples of what is known as the Planck energy. To get a sense of scale, if we translate the Planck energy into a mass using Einstein's famous conversion formula E equals sine m(2), they correspond to masses that are on the order of 10 billion 1019 times that of a proton. This gargantuan mass, by elementary particle standards, is known as the Planck mass. It's about equal to the mass of a grain of dust or a collection of 1 million average bacteria. And so, the typical mass equivalent of a vibrating loop in string theory is generally some whole number, 1, 2, 3, 2, times the Planck mass. Physicists often express this by saying that the natural or typical energy scale and hence mass scale of string theory is the Planck scale. This raises a crucial question directly related to the goal of reproducing the particle properties in tables 1.1 and 1.2. If the natural energy scale of string theory is some 10 billion times that of a proton, how can it possibly account for the far lighter particles, electrons, quarks, photons, and so on, making up the world around us? The answer, once again, comes from quantum mechanics. The uncertainty principle ensures that nothing is ever perfectly at rest. All objects undergo quantum jitter, for if they didn't, we would know where they were and how fast they were moving with complete precision, in violation of Heisenberg's dictum. This holds true for the loops in string theory as well. No matter how placid a string appears, it will always experience some amount of quantum vibration. The remarkable thing, as originally worked out in the 1970s, is that there can be energy cancellations between these quantum jitters and the more intuitive kind of string vibrations discussed above and illustrated in figures 6.2 and 6.3. In effect, through the weirdness of quantum mechanics, the energy associated with the quantum jitters of a string is negative, and this reduces the overall energy content of a vibrating string by an amount that is roughly equal to Planck energy. This means that the lowest energy vibrational string patterns, whose energies we would naively expect to be about equal to the Planck energy, that is, 1 times the Planck energy, are largely cancelled, thereby yielding relatively low net energy vibrations, energies whose corresponding mass equivalents are in the neighborhood of the matter and force particle masses shown in tables 1.1 and 1.2. It is these lowest energy vibrational patterns, therefore, that should provide contact between the theoretical description of strings and the experimentally accessible world of particle physics. As an important example, Shirk and Schwartz found that for the vibrational pattern whose properties make it a candidate for the graviton messenger particle, the energy cancellations are perfect, resulting in a zero-mass gravitational force particle. This is precisely what is expected for the graviton. The gravitational force is transmitted at light speed, and only massless particles travel at this maximal velocity. But low-energy vibrational combinations are very much the exception rather than the rule. The more typical vibrating fundamental string corresponds to a particle whose mass is billions upon billions times greater than that of the proton. This tells us that the comparatively light fundamental particles of tables 1.1 and 1.2 should arise, in a sense, from the fine mist above the roaring ocean of energetic strings. Even a particle as heavy as the top quark, with a mass about 189 times that of the proton, can arise from a vibrating string only if the string's enormous characteristic Planck scale energy is cancelled by the jitters of quantum uncertainty to better than 1 part in 100 million billion. It's as if you were playing The Price is Right, and Bob Barker gives you $10 billion and challenges you to purchase products that will cost, cancel so to speak, all but 189 of the dollars, not a dollar more or less. Coming up with such an enormous yet precise expenditure, without being privy to the exact prices of the individual items, would severely tax the acumen of even the world's most expert shoppers. In string theory, where the currency is energy as opposed to money, approximate calculations have conclusively shown that analogous energy cancellations certainly can occur, but for reasons that will become increasingly clear in subsequent chapters, verifying the cancellations to such a high level of precision is generally beyond our theoretical ken at present. Even so, as indicated before, we shall see that many other properties of string theory that are less sensitive to these finest of details can be extracted and understood with confidence. This takes us to the third consequence of the enormous value of the string tension. Strings can execute an infinite number of different vibrational patterns. For instance, in Figure 6.2, we showed the beginnings of a never-ending sequence of possibilities characterized by an ever greater number of peaks and troughs. Doesn't this mean that there would have to be a corresponding never-ending sequence of elementary particles seemingly in conflict with the experimental situation summarized in tables 1.1 and 1.2? The answer is yes. If string theory is right, each of the infinitely many resonant patterns of string vibration should correspond to an elementary particle. An essential point, however, is that the high string tension ensures that all but a few of these vibrational patterns will correspond to extremely heavy particles, the few being the lowest energy vibrations that have near-perfect cancellations with quantum string jitters. And again, the term heavy here means many times heavier than the Planck mass. As our most powerful particle accelerators can reach energies only on the order of 1,000 times the proton mass, less than a millionth of a billionth of the Planck energy, we are very far from being able to search in the laboratory for any of these new particles predicted by string theory. There are more indirect approaches by which we could search for them, though. For instance, the energies involved at the birth of the universe would have been high enough to produce these particles copiously. In general, one would not expect them to survive to the present day, as such super-heavy particles are usually unstable, relinquishing their enormous mass by decaying into a cascade of ever lighter particles, ending with the familiar, relatively light particles in the world around us. However, it is possible that such a super-heavy vibrational string state, a relic from the Big Bang, did survive to the present. Finding such particles, as we discuss more fully in Chapter 9, would be a monumental discovery, to say the least. Gravity and quantum mechanics in string theory. The unified framework that string theory presents is compelling, but its real attraction is the ability to ameliorate the hostilities between the gravitational force and quantum mechanics. Recall that the problem in merging general relativity and quantum mechanics turns up when the central tenet of the former, that space and time constitute a smoothly curving geometrical structure, confronts the essential feature of the latter, that everything in the universe, including the fabric of space and time, undergoes quantum fluctuations that become increasingly turbulent when probed on smaller and smaller distance scales. On sub-Planck scale distances, the quantum undulations are so violent that they destroy the notion of a smoothly curving geometrical space. This means that general relativity breaks down. String theory softens the violent quantum undulations by smearing out the short-distance properties of space. There is a rough and a more precise answer to the question of what this really means and how it resolves the conflict. We discuss each in turn. The rough answer. Although it sounds unsophisticated, one way that we learn about the structure of an object is by hurling other things at it and observing the precise way in which they are deflected. We are able to see things, for example, because our eyes collect and our brains decode information carried by photons as they bounce off of objects being viewed. Particle accelerators are based on the same principle. They hurl bits of matter such as electrons and protons at each other as well as at other targets, and elaborate detectors analyze the resulting spray of debris to determine the architecture of the objects involved. As a general rule, the size of the probe particle that we use sets a lower limit to the length scale to which we are sensitive. To get a feel for what this important statement means, imagine that Slim and Jim decide to get some culture by enrolling in a drawing class. As the semester progresses, Jim becomes increasingly irritated by Slim's growing proficiency as an artist and challenges him to an unusual contest. He proposes that they each take a peach pit, secure it in a vise, and draw their most accurate still-life renditions. The unusual feature of Jim's challenge is that neither he nor Slim will be allowed to look at the peach pits. Instead, each is allowed to learn about the size, shape, and features of his peach pit only by shooting things, other than photons, at the pit and observing how they are deflected, as illustrated in Figure 6.4. Unbeknownst to Slim, Jim fills Slim's shooter with marbles, as in Figure 6.4a, but fills his own shooter with far smaller 5mm plastic pellets, as in Figure 6.4b. They both turn on their shooters, and the competition begins. After a while, the best drawing Slim can come up with is that in Figure 6.4a. By observing the trajectories of the deflected marbles, he was able to learn that the pit is a small, hard-surfaced mass, but that's all he could learn. Marbles are just too large to be sensitive to the finer corrugated structure of the peach pit. When Slim takes a look at Jim's drawing, Figure 6.4b, he is surprised to see that he has been outdone. A momentary glance at Jim's shooter, though, reveals the trick. The smaller probe particles used by Jim are fine enough to have their angle of deflection affected by some of the largest features adorning the pit's surface. And so, by shooting many 5mm pellets at the pit and observing their deflected trajectories, Jim was able to draw a more detailed image. Slim, not to be outdone, goes back to his shooter, fills it with even smaller probe particles, 0.5mm pellets, that are tiny enough to enter and hence be deflected by the finest corrugations on the pit's surface. By observing how these impinging probe particles are deflected, he is able to draw the winning rendition shown in Figure 6.4. C. The lesson taught by this little competition is clear. Useful probe particles cannot be substantially larger than the physical features being examined. Otherwise, they will be insensitive to the structures of interest. The same reasoning holds, of course, if one wants to probe the pit even more deeply to determine its atomic and subatomic structure. 0.5mm pellets will not provide any useful information. They are clearly too big to have any sensitivity to structure on atomic scales. This is why particle accelerators use protons or electrons as probes, since their small size makes them much better suited to the task. On subatomic scales, where quantum concepts replace classical reasoning, the most appropriate measure of a particle's probing sensitivity is its quantum wavelength, which indicates the window of uncertainty in its position. This fact reflects our discussion of Heisenberg's uncertainty principle in Chapter 4, in which we found that the margin of error incurred when using a point particle as a probe — we focused on photon probes, but the discussion applies to all other particles — is about equal to the probe particle's quantum wavelength. In somewhat looser language, the probing sensitivity of a point particle is smeared out by the jitteriness of quantum mechanics, in much the same way that the precision of a surgeon's scalpel is compromised if he or she has hands that shake. But recall that in Chapter 4 we also noted the important fact that a particle's quantum wavelength is inversely proportional to its momentum, which, roughly speaking, is its energy. And so, by increasing a point particle's energy, its quantum wavelength can be made shorter and shorter. Quantum smearing can be decreased further and further, and hence we can use it to probe ever finer physical structures. Intuitively, higher energy particles have greater penetrating power and are therefore able to probe more minute features. In this regard, the distinction between point particles and strands of string becomes manifest. Just as was the case for plastic pellets probing the surface features of a peach pit, the string's inherent spatial extent prevents it from probing the structure of anything substantially smaller than its own size. In this case, structures arising on length scales shorter than the Planck length. Somewhat more precisely, in 1988, David Gross, then of Princeton University, and his student Paul Mende showed that when quantum mechanics is taken into account, continually increasing the energy of a string does not continually increase its ability to probe finer structures, in direct contrast with what happens for a point particle. They found that when the energy of a string is increased, it is at first able to probe shorter scale structures, just like an energetic point particle. But when its energy is increased beyond the value required for probing structures on the scale of the Planck length, the additional energy does not sharpen the string probe. Rather, the energy causes the string to grow in size, thereby diminishing its short-distance sensitivity. In fact, although the size of a typical string is the Planck length, if we pumped enough energy into a string, an amount of energy beyond our wildest imaginings but one that would likely have been attained by the Big Bang, we could cause it to grow to a macroscopic size, a clumsy probe of the microcosmos indeed. It's as if a string, unlike a point particle, has two sources of smearing: quantum jitters, as for a point particle, and also its own inherent spatial extent. Increasing a string's energy decreases the smearing from the first source, but ultimately increases the smearing from the second. The upshot is that no matter how hard you try, the extended nature of a string prevents you from using it to probe phenomena on sub-Planck length distances. But the whole conflict between general relativity and quantum mechanics arises from the sub-Planck length properties of the spatial fabric. If the elementary constituent of the universe cannot probe sub-Planck scale distances, then neither it nor anything made from it can be affected by the supposedly disastrous short-distance quantum undulations. This is similar to what happens as we draw our hand across a highly polished granite surface. Although at a microscopic level the granite is discrete, grainy, and bumpy, our fingers are unable to detect these short-scale variations, and the surface feels perfectly smooth. Our stumpy, extended fingers smear out the microscopic discreteness. Similarly, since the string has spatial extent, it also has limits on its short-distance sensitivity. It cannot detect variations on sub-Planck distance scales. Like our fingers on granite, the string smears out the jittery ultra-microscopic fluctuations of the gravitational field. Although the resulting fluctuations are still substantial, this smearing smooths them out just enough to cure the incompatibility between general relativity and quantum mechanics. And, in particular, the pernicious infinities, discussed in the preceding chapter, that arise in the point-particle approach to forming a quantum theory of gravity are done away with by string theory. An essential difference between the granite analogy and our real concern with the spatial fabric is that there are ways in which the microscopic discreteness of the granite surface can be exposed. Finer, more precise probes than our fingers can be used. An electron microscope has the ability to resolve surface features to less than a millionth of a centimeter. This is sufficiently small to reveal the numerous surface imperfections. By contrast, in string theory, there is no way to expose the sub-Planck scale imperfections in the fabric of space. In a universe governed by the laws of string theory, the conventional notion that we can always dissect nature on ever smaller distances without limit is not true. There is a limit, and it comes into play before we encounter the devastating quantum foam of Figure 5.1. Therefore, in a sense that will be made more precise in later chapters, one can even say that the supposed tempestuous sub-Planckian quantum undulations do not exist. A positivist would say that something exists only if it can, at least in principle, be probed and measured. Since the string is supposed to be the most elementary object in the universe, and since it is too large to be affected by the violent sub-Planck length undulations of the spatial fabric, these fluctuations cannot be measured, and hence, according to string theory, do not actually arise. A sleight of hand. This discussion may leave you feeling dissatisfied. Instead of showing that string theory tames the sub-Planck length quantum undulations of space, we seem to have used the string's non-zero size to skirt the whole issue completely. Have we actually solved anything? We have. The following 2 points will serve to emphasize this. First, what the preceding argument implies is that the supposedly problematic sub-Planck length spatial fluctuations are an artifact of formulating general relativity and quantum mechanics in a point-particle framework. In a sense, therefore, the central conflict of contemporary theoretical physics has been a problem of our own making. Because we previously envisioned all matter particles and all force particles to be point-like objects with literally no spatial extent, we were obligated to consider properties of the universe on arbitrarily short-distance scales. And on the tiniest of distances we ran into seemingly insurmountable problems. String theory tells us that we encountered these problems only because we did not understand the true rules of the game. The new rules tell us that there is a limit to how finely we can probe the universe, and in a real sense, a limit to how finely our conventional notion of distance can even be applied to the ultra-microscopic structure of the cosmos. The supposed pernicious spatial fluctuations are now seen to have arisen in our theories because we were unaware of these limits and were thus led by a point-particle approach to grossly overstep the bounds of physical reality. Given the apparent simplicity of this solution for overcoming the problem between general relativity and quantum mechanics, you might wonder why it took so long for someone to suggest that the point-particle description is merely an idealization, and that in the real world, elementary particles do have some spatial extent. This takes us to our second point. Long ago, some of the greatest minds in theoretical physics, such as Pauli, Heisenberg, Dirac, and Feynman, did suggest that nature's constituents might not actually be points, but rather small, undulating blobs, or nuggets. They and others found, however, that it is very hard to construct a theory whose fundamental constituent is not a point particle that is nonetheless consistent with the most basic of physical principles such as conservation of quantum mechanical probability, so that physical objects do not suddenly vanish from the universe without a trace, and the impossibility of faster-than-light-speed transmission of information. From a variety of perspectives, their research showed time and again that one or both of these principles were violated when the point-particle paradigm was discarded. For a long time, therefore, it seemed impossible to find a sensible quantum theory based on anything but point particles. The truly impressive feature of string theory is that more than 20 years of exacting research has shown that although certain features are unfamiliar, string theory does respect all of the requisite properties inherent in any sensible physical theory. And furthermore, through its graviton pattern of vibration, string theory is a quantum theory containing gravity. The more precise answer. The rough answer captures the essence of why string theory prevails where previous point-particle theories failed. And so, if you like, you can go on to the next section without losing the logical flow of our discussion. But having developed the essential ideas of special relativity in Chapter 2, we already have the necessary tools for describing more accurately how string theory calms the violent quantum jitters. In the more precise answer, we rely upon the same core idea as in the rough answer, but we express it directly at the level of strings. We do this by comparing in some detail point-particle and string probes. We will see how the extended nature of the string smears out the information that would be obtainable by point-particle probes, and therefore again how it happily does away with the ultra-short-distance behavior responsible for the central dilemma of contemporary physics. We first consider the way in which point particles would interact if they were actually to exist, and hence how they could be used as physical probes. The most basic interaction is between two point particles moving on a collision course so that their trajectories will intersect, as in Figure 6.5. If these particles were billiard balls, they would collide, and each would be deflected onto a new trajectory. Point-particle quantum field theory shows that essentially the same thing happens when elementary particles collide. They scatter off one another and continue on deflected trajectories. But the details are a little different. For concreteness and simplicity, imagine that one of the two particles is an electron, and the other is its antiparticle, the positron. When matter and antimatter collide, they can annihilate in a flash of pure energy, producing, for example, a photon. To distinguish the ensuing trajectory of the photon from the previous trajectories of the electron and positron, we follow a traditional physics convention and draw it with a wiggly line. The photon will typically travel for a bit and then release the energy derived from the initial electron-positron pair by producing another electron-positron pair with trajectories as indicated on the far right of Figure 6.6. In the end, two particles are fired at each other. They interact through the electromagnetic force, and finally they emerge on deflected trajectories, a sequence of events that bears some similarity to our description of colliding billiard balls. We are concerned with the details of the interaction, specifically the point where the initial electron and positron annihilate and produce the photon. The central fact, as will become apparent, is that there is an unambiguous, completely identifiable time and place where this happens. It is marked in Figure 6.6. How does this description change if, when we closely examine the objects we thought were zero-dimensional points, they turn out to be one-dimensional strings? The basic process of interaction is the same, but now the objects on a collision course are oscillating loops, as shown in Figure 6.7. If these loops are vibrating in just the right resonance patterns, they will correspond to an electron and a positron on collision course, collide and again annihilate each other in a flash. The flash, a photon, is itself a string in a particular vibrational pattern. Thus, the two incoming strings interact by merging together and producing a third string as shown in Figure 6.7. Just as in our point-particle description, this string travels a bit and then releases the energy derived from the two initial strings by dissociating into two strings that travel onward. Again, from any but the most microscopic perspective, this will look just like the point-particle interaction of Figure 6.6. There is, however, a crucial difference between the two descriptions. We emphasize that the point-particle interaction occurs at an identifiable point in space and time, a location that all observers can agree on. As we shall now see, this is not true for interactions between strings. We will show this by comparing how George and Gracie, two observers in relative motion as in Chapter 2, would describe the interaction. We will see that they do not agree on where and when the two strings touch for the first time. To do so, imagine that we view the interaction between two strings with a camera whose shutter is kept open so that the whole history of the process is captured on one piece of film. We show the result, known as a string world sheet. By slicing the world sheet into parallel pieces, much as one slices a loaf of bread, the moment-by-moment history of the string interaction can be recovered. We show an example of this slicing in Figure 6.8. Specifically, in Figure 6.8a, we show George, intently focused on the two incoming strings together with an attached plane that slices through all events in space that occur at the same time, according to his perspective. As we have done often in previous chapters, we have suppressed one spatial dimension in this diagram for visual clarity. In reality, of course, there is a three-dimensional array of events that occur at the same time according to any observer. Figures 6.8b and 6.8c give a couple of snapshots at subsequent times, subsequent slices of the world sheet, showing how George sees the two strings approach each other. Of central importance, in Figure 6.8c, we show the instant in time, according to George, when the two strings first touch and merge together, producing the third string. Let's now do the same for Gracie. As discussed in Chapter 2, the relative motion of George and Gracie implies that they do not agree on what events occur at the same time. From Gracie's perspective, the events in space that occur simultaneously lie on a different plane, as shown in Figure 6.9. That is, from Gracie's perspective, the world sheet of Figure 6.7, C, must be sliced into pieces at a different angle in order to reveal the moment-by-moment progression of the interaction. In Figures 6.9, B, and 6.9, C, we show subsequent moments in time, now according to Gracie, including the moment when she sees the two incoming strings touch and produce the third string. By comparing Figures 6.8c and 6.9 wards as C, as we do in Figure 6.10, we see that George and Gracie do not agree on when and where the two initial strings first touch, where they interact. The string, being an extended object, ensures that there is no unambiguous location in space or moment in time when the strings first interact. Rather, it depends upon the state of motion of the observer. If we apply exactly the same reasoning to the interaction of point particles, as summarized in Figure 6.11, we recover the conclusion stated earlier. There is a definite point in space and moment in time when the point particles interact. Point particles cram all of their interaction into a definite point. When the force involved in an interaction is the gravitational force, that is, when the messenger particle involved in the interaction is the graviton instead of the photon. This complete packing of the force's punch into a single point leads to disastrous results, such as the infinite answers we alluded to earlier. Strings, by contrast, smear out the place where interactions occur. Because different observers perceive that the interaction takes place at various locations along the left part of the surface of Figure 6.10, in a real sense. This means that the interaction location is smeared out among all of them. This spreads out the force's punch, and, in the case of the gravitational force, this smearing significantly dilutes its ultramicroscopic properties, so much so that calculations yield well-behaved finite answers in place of the previous infinities. This is a more precise version of the smearing encountered in the rough answer of the last section. And once again, this smearing results in a smoothing of the ultra-microscopic jitteriness of space as sub-Planck length distances are blurred together. Like viewing the world through glasses that are too weak or too strong. Fine sub-Planckian details that would be accessible to a point-particle probe are smeared together by string theory and rendered harmless. And unlike the case with poor eyesight, if string theory is the ultimate description of the universe, there is no corrective lens to bring the supposed sub-Planck scale fluctuations into sharp focus. the incompatibility of general relativity and quantum mechanics, which would become apparent only on sub-Planck scale distances, is avoided in a universe that has a lower limit on the distances that can be accessed, or even said to exist in the conventional sense. Such is the universe described by string theory, in which we see that the laws of the large and the small can be harmoniously merged together, as the supposed catastrophe arising on ultra-microscopic distances is summarily done away with. Beyond strings, strings are special for two reasons. First, even though they are spatially extended, they can be described consistently in the framework of quantum mechanics. Second, among the resonant vibrational patterns there is one that has the exact properties of the graviton, thus ensuring that the gravitational force is an intrinsic part of its structure. But just as string theory shows that the conventional notion of zero-dimensional point particles appears to be a mathematical idealization that is not realized in the real world, might it also be the case that an infinitely thin, one-dimensional strand is similarly a mathematical idealization? Might it actually be the case that strings have some thickness, like the surface of a two-dimensional bicycle tire inner tube, or, even more realistically, like a thin, three-dimensional donut? The seemingly insurmountable difficulties found by Heisenberg, Dirac, and others in their attempts to construct a quantum theory of three-dimensional nuggets have repeatedly stymied researchers following this natural chain of reasoning. Quite unexpectedly, though, during the mid-1990s, string theorists realized, through indirect and rather shrewd reasoning, that such higher-dimensional fundamental objects actually do play an important and subtle role in string theory itself. Researchers have gradually realized that string theory is not a theory that contains only strings. A crucial observation, central to the second superstring revolution initiated by Witten and others in 1995, is that string theory actually includes ingredients with a variety of different dimensions. Two-dimensional frisbee-like constituents, three-dimensional blob-like constituents, and even more exotic possibilities to boot. These most recent realizations will be taken up in chapters 12 and 13. For now, we continue to follow the path of history and further explore the striking new properties of a universe built out of one-dimensional strings instead of zero-dimensional point particles. Chapter 7. The Super in Superstrings. When the success of Eddington's 1919 expedition to measure Einstein's prediction of the bending of starlight by the sun had been established, the Dutch physicist Hendrik Lorentz sent Einstein a telegram informing him of the good news. As word of the telegram's confirmation of general relativity spread, a student asked Einstein about what he would have thought if Eddington's experiment had not found the predicted bending of starlight. Einstein replied, "Then I would have been sorry for the dear Lord, for the theory is correct." Of course, had experiments truly failed to confirm Einstein's predictions, the theory would not be correct, and general relativity would not have become a pillar of modern physics. But what Einstein meant is that general relativity describes gravity with such a deep inner elegance, with such simple yet powerful ideas, that he found it hard to imagine that nature could pass it by. General relativity, in Einstein's view, was almost too beautiful to be wrong. Aesthetic judgments do not arbitrate scientific discourse, however. Ultimately, theories are judged by how they fare when faced with cold, hard, experimental facts. But this last remark is subject to an immensely important qualification. While a theory is being constructed, its incomplete state of development often prevents its detailed experimental consequences from being assessed. Nevertheless, physicists must make choices and exercise judgments about the research direction in which to take their partially completed theory. Some of these decisions are dictated by internal logical consistency. We certainly require that any sensible theory avoid logical absurdities. Other decisions are guided by a sense of the qualitative experimental implications of one theoretical construct relative to another. We are generally not interested in a theory if it has no capacity to resemble anything we encounter in the world around us. But it is certainly the case that some decisions made by theoretical physicists are founded upon an aesthetic sense, a sense of which theories have an elegance and beauty of structure on par with the world we experience. Of course, nothing ensures that this strategy leads to truth. Maybe, deep down, the universe has a less elegant structure than our experiences have led us to believe. Or maybe we will find that our current aesthetic criteria need significant refining when applied in ever less familiar contexts. Nevertheless, especially as we enter an era in which our theories describe realms of the universe that are increasingly difficult to probe experimentally, physicists do rely on such an aesthetic to help them steer clear of blind alleys and dead-end roads that they might otherwise pursue. So far, this approach has provided a powerful and insightful guide. In physics, as in art, symmetry is a key part of aesthetics. But unlike the case in art, symmetry in physics has a very concrete and precise meaning. In fact, by diligently following this precise notion of symmetry to its mathematical conclusion, physicists during the last few decades have found theories in which matter particles and messenger particles are far more closely intertwined than anyone previously thought possible. Such theories, which unite not only the forces of nature but also the material constituents, have the greatest possible symmetry, and for this reason have been called supersymmetric. Superstring theory, as we shall see, is both the progenitor and the pinnacle example of a supersymmetric framework, the nature of physical law. Imagine a universe in which the laws of physics are as ephemeral as the tastes of fashion changing from year to year, from week to week, or even from moment to moment. In such a world, assuming that the changes do not disrupt basic life processes, you would never experience a dull moment, to say the least. The simplest acts would be an adventure, since random variations would prevent you or anyone else from using past experience to predict anything about future outcomes. Such a universe is a physicist's nightmare. Physicists, and most everyone else as well, rely crucially upon the stability of the universe. The laws that are true today were true yesterday and will still be true tomorrow, even if we have not been clever enough to have figured them all out. After all, what meaning can we give to the term law if it can abruptly change? This does not mean that the universe is static. The universe certainly changes in innumerable ways from each moment to the next. Rather, it means that the laws governing such evolution are fixed and unchanging. You might ask whether we really know this to be true. In fact, we don't. But our success in describing numerous features of the universe, from a brief moment after the Big Bang right through to the present, assures us that if the laws are changing, they must be doing so very slowly. The simplest assumption that is consistent with all that we know is that the laws are fixed. Now, imagine a universe in which the laws of physics are as parochial as local culture, changing unpredictably from place to place and defiantly resisting any outside influence to conform. Like the Adventures of Gulliver, travels in such a world would expose you to an enormously rich array of unpredictable experiences. But from a physicist's perspective, this is yet another nightmare. It's hard enough, for instance, to live with the fact that laws that are valid in one country or even one state may not be valid in another. But imagine what things would be like if the laws of nature were as varied. In such a world, experiments carried out in one locale would have no bearing on the physical laws relevant somewhere else. Instead, physicists would have to redo experiments over and over again in different locations to probe the local laws of nature that hold in each. Thankfully, everything we know points toward the laws of physics being the same everywhere. All experiments the world over converge on the same set of underlying physical explanations. Moreover, our ability to explain a vast number of astrophysical observations of far-flung regions of the cosmos using one fixed set of physical principles leads us to believe that the same laws do hold true everywhere. Having never traveled to the opposite end of the universe, we can't definitively rule out the possibility that a whole new kind of physics prevails elsewhere, but everything points to the contrary. Again, this does not mean that the universe looks the same or has the same detailed properties in different locations. An astronaut jumping on a pogo stick on the moon can do all sorts of things that are impossible to do on Earth. But we recognize that the difference arises because the moon is far less massive than the Earth. It does not mean that the law of gravity is somehow changing from place to place. Newton's, or more precisely Einstein's, law of gravity is the same on Earth as it is on the moon. The difference in the astronaut's experience is one of change in environmental detail, not variation of physical law. Physicists describe these two properties of physical laws, that they do not depend on when or where you use them, as symmetries of nature. By this usage, physicists mean that nature treats every moment in time and every location in space identically, symmetrically, by ensuring that the same fundamental laws are in operation. Much in the same manner that they affect art and music, such symmetries are deeply satisfying. They highlight an order and a coherence in the workings of nature. The elegance of rich, complex, and diverse phenomena emerging from a simple set of universal laws is at least part of what physicists mean when they invoke the term beautiful. In our discussions of the special and general theories of relativity, we came upon yet other symmetries of nature. Recall that the principle of relativity, which lies at the heart of special relativity, tells us that all physical laws must be the same, regardless of the constant velocity relative motion that individual observers might experience. This is a symmetry because it means that nature treats all such observers identically, symmetrically. Each such observer is justified in considering himself or herself to be at rest. Again, it's not that observers in relative motion will make identical observations. As we have seen earlier, there are all sorts of stunning differences in their observations. Instead, like the disparate experiences of the pogo stick enthusiast on the Earth and on the Moon, the differences in observations reflect environmental details. The observers are in relative motion, even though their observations are governed by identical laws. Through the equivalence principle of general relativity, Einstein significantly extended this symmetry by showing that the laws of physics are actually identical for all observers, even if they are undergoing complicated accelerated motion. Recall that Einstein accomplished this by realizing that an accelerated observer is also perfectly justified in declaring himself or herself to be at rest, and in claiming that the force he or she feels is due to a gravitational field. Once gravity is included in the framework, all possible observational vantage points are on a completely equal footing. Beyond the intrinsic aesthetic appeal of this egalitarian treatment of all motion, we have seen that these symmetry principles played a pivotal role in the stunning conclusions regarding gravity that Einstein found. Are there any other symmetry principles having to do with space, time, and motion that the laws of nature should respect? If you think about this, you might come up with one more possibility. The laws of physics should not care about the angle from which you make your observations. For instance, if you perform some experiment and then decide to rotate all of your equipment and do the experiment again, the same laws should apply. This is known as rotational symmetry, and it means that the laws of physics treat all possible orientations on equal footing. It is a symmetry principle that is on par with the previous ones discussed. Are there others? Have we overlooked any symmetries? You might suggest the gauge symmetries associated with the non-gravitational forces, as discussed in Chapter 5. These are certainly symmetries of nature, but they are of a more abstract sort. Our focus here is on symmetries that have a direct link to space, time, or motion. With this stipulation, it's now likely that you can't think of any other possibilities. In fact, in 1967, physicists Sidney Coleman and Geoffrey Mandela were able to prove that no other symmetries associated with space, time, or motion could be combined with those just discussed and result in a theory bearing any resemblance to our world. Subsequently, though, close examination of this theorem, based on insights of a number of physicists, revealed precisely one subtle loophole. The Coleman-Mandela result did not exploit fully symmetries sensitive to something known as spin. Spin. An elementary particle, such as an electron, can orbit an atomic nucleus in somewhat the same way that the Earth orbits the Sun. But, in the traditional point-particle description of an electron, it would appear that there is no analog of the Earth's spinning around on its axis. When any object spins, points on the axis of rotation itself, like the central point of a spinning frisbee, do not move. If something is truly point-like, though, it has no other points that lie off of any purported spin axis, and so it would appear that there simply is no notion of a point object spinning. Many years ago, such reasoning fell prey to yet another quantum mechanical surprise. In 1925, the Dutch physicists George Uhlenbeck and Samuel Goudsmit realized that a wealth of puzzling data having to do with properties of light emitted and absorbed by atoms could be explained if electrons were assumed to have very particular magnetic properties. Some 100 years earlier, the Frenchman André-Marie Ampère had shown that magnetism arises from the motion of electric charge. Uhlenbeck and Goudsmit followed this lead and found that only one specific sort of electron motion could give rise to the magnetic properties suggested by the data: rotational motion, that is, spin. And so, contrary to classical expectations, Uhlenbeck and Goudsmit proclaimed that, somewhat like the Earth, electrons both revolve and rotate. Did Uhlenbeck and Goudsmit literally mean that the electron is spinning? Yes and no. What their work really showed is that there's a quantum mechanical notion of spin that is somewhat akin to the usual image but inherently quantum mechanical in nature. It's one of those properties of the microscopic world that brushes up against classical ideas but injects an experimentally verified quantum twist. For instance, picture a spinning skater. As she pulls her arms in, she spins more quickly. As she stretches out her arms, she spins more slowly. And sooner or later, depending on how vigorously she threw herself into the spin, she will slow down and stop. Not so for the kind of spin revealed by Uhlenbeck and Goudsmit. According to their work and subsequent studies, every electron in the universe always and forever spins at one fixed and never-changing rate. The spin of an electron is not a transitory state of motion as for more familiar objects that, for some reason or other, happen to be spinning. Instead, the spin of an electron is an intrinsic property much like its mass or its electric charge. If an electron were not spinning, it would not be an electron. Although early work focused on the electron, physicists have subsequently shown that these ideas about spin apply equally well to all of the matter particles that fill out the three families of Table 1.1. This is true down to the last detail. All of the matter particles, and their antimatter partners as well, have spin equal to that of the electron. In the language of the trade, physicists say that matter particles all have spin 1/2, where the value 1/2 is, roughly speaking, a quantum mechanical measure of how quickly electrons rotate. Moreover, physicists have shown that the non-gravitational force carriers, photons, weak-gauge bosons, and gluons, also possess an intrinsic spinning characteristic that turns out to be twice that of the matter particles. They all have spin 1. What about gravity? Well, even before string theory, physicists were able to determine what spin the hypothesized graviton must have to be the transmitter of the gravitational force. The answer: twice the spin of photons, weak-gauge bosons, and gluons, i.e. spin 2. In the context of string theory, spin, just like mass and force charges, is associated with the pattern of vibration that a string executes. As with point particles, it's a bit misleading to think of the spin carried by a string as arising from its spinning literally around in space, but this image does give a loose picture to have in mind. By the way, we can now clarify an important issue we encountered earlier. In 1974, when Shirk and Schwarz proclaimed that string theory should be thought of as a quantum theory incorporating the gravitational force, they did so because they had found that strings necessarily have a vibrational pattern in their repertoire that is massless and has spin 2, the hallmark features of the graviton. Where there is a graviton, there is also gravity. With this background on the concept of spin, let's now turn to the role it plays in revealing the loophole in the Coleman-Mandela result concerning the possible symmetries of nature mentioned in the preceding section: supersymmetry and superpartners. As we have emphasized, the concept of spin, although superficially akin to the image of a spinning top, differs in substantial ways that are rooted in quantum mechanics. Its discovery in 1925 revealed that there is another kind of rotational motion that simply would not exist in a purely classical universe. This suggests the following question: just as ordinary rotational motion allows for the symmetry principle of rotational invariance, physics treats all spatial orientations on an equal footing, could it be that the more subtle rotational motion associated with spin leads to another possible symmetry of the laws of nature? By 1971 or so, physicists showed that the answer to this question was yes. Although the full story is quite involved, the basic idea is that when spin is considered, there is precisely one more symmetry of the laws of nature that is mathematically possible. It is known as supersymmetry. Supersymmetry cannot be associated with a simple and intuitive change in observational vantage point, Shifts in time, in spatial location, in angular orientation, and in velocity of motion exhaust these possibilities. But just as spin is like rotational motion, with a quantum mechanical twist, supersymmetry can be associated with a change in observational vantage point in a quantum mechanical extension of space and time. These quotes are especially important, as the last sentence is only meant to give a rough sense of where supersymmetry fits into the larger framework of symmetry principles. 5.2. Nevertheless, although understanding the origin of supersymmetry is rather subtle, we will focus on one of its primary implications. Should the laws of nature incorporate its principles? And this is far easier to grasp. In the early 1970s, physicists realized that if the universe is supersymmetric, the particles of nature must come in pairs whose respective spins differ by half a unit. Such pairs of particles, regardless of whether they are thought of as point-like, as in the Standard Model, or as tiny vibrating loops, are called superpartners. Since matter particles have spin 1/2, while some of the messenger particles have spin 1, supersymmetry appears to result in a pairing, a partnering, of matter and force particles. As such, it seems like a wonderful unifying concept. The problem comes in the details. By the mid-1970s, when physicists sought to incorporate supersymmetry into the Standard Model, they found that none of the known particles, those of tables 1.1 and 1.2, could be superpartners of one another. Instead, detailed theoretical analysis showed that if the universe incorporates supersymmetry, then every known particle must have an as-yet undiscovered superpartner particle, whose spin is half a unit less than its known counterpart. For instance, there should be a spin-0 partner of the electron. This hypothetical particle has been named the selectron, a contraction of supersymmetric electron. The same should also be true for the other matter particles with, for example, the hypothetical spin-0 superpartners of neutrinos and quarks being called sneutrinos and squarks. Similarly, the force particles should have spin 1/2 superpartners. For photons, there should be photinos. For the gluons, there should be gluinos. For the W and Z bosons, there should be winos and xenos. On closer inspection, then, supersymmetry seems to be a terribly uneconomical feature. It requires a whole slew of additional particles that wind up doubling the list of fundamental ingredients. Since none of the superpartner particles has ever been detected, you would be justified to take Rabi's remark from Chapter 1 regarding the discovery of the muon one step further, declare that nobody ordered supersymmetry, and summarily reject this symmetry principle. For 3 reasons, however, many physicists believe strongly that such an out-of-hand dismissal of supersymmetry would be studied this question and found a surprising answer. The quantum cloud of particle eruptions and annihilations amplifies the strengths of the strong and weak forces. This implies that as we examine them on the shorter distances, we penetrate more of this seething cloud, and hence are subject to less of its amplification. And so, the strengths of these forces get weaker when they are probed on shorter distances. Georgi, Quinn, and Weinberg took this realization and ran with it to a remarkable end. They showed that when these effects of the quantum frenzy are carefully accounted for, the net result is that the strengths of all 3 non-gravitational forces are driven together. Whereas the strengths of these forces are very different on scales accessible to current technology, Georgi, Quinn, and Weinberg argued that this difference is actually due to the different effect that the haze of microscopic quantum activity has on each force. Their calculations showed that if this haze is penetrated by examining the forces not on everyday scales, but as they act on distances of about 1/100th of a billionth of a billionth of a billionth, 10^29 of a centimeter, a mere factor of 10,000 larger than the Planck length, the 3 non-gravitational force strengths appear to become equal. Although far removed from the realm of common experience, the high energy necessary to be sensitive to such small distances was characteristic of the roiling, hot, early universe when it was about 1,000th of a trillionth of a trillionth of a trillionth, 10^39 of a second old, when its temperature was on the order of 1028 Kelvin mentioned earlier. In somewhat the same way that a collection of disparate ingredients, pieces of metal, wood, rocks, minerals, and so on, all melt together and become a uniform, homogeneous plasma when heated to sufficiently high temperature, these theoretical works suggested that the strong, weak, and electromagnetic forces all merge into one grand force at such immense temperatures. This is shown schematically in Figure 7.1. Although we do not have the technology to probe such minute distance scales or to produce such scorching temperatures, since 1974 experimentalists have significantly refined the measured strengths of the three non-gravitational forces under everyday conditions. These data, the starting points for the three forces strength curves in Figure 7.1, are the input data for the quantum mechanical extrapolations of Gorgy, Quinn, and Weinberg. In 199.1, Ugo Amaldi of CERN, Wim de Boer, and Hermann Furstenau of the University of Karlsruhe, Germany, recalculated the Gorgy, Quinn, and Weinberg extrapolations, making use of these experimental refinements, and showed two significant things. First, the strengths of the three non-gravitational forces almost agree, but not quite at tiny distance scales equivalently high energy, high temperature, as shown in Figure 7.2. Second, this tiny but undeniable discrepancy in their strengths vanishes if supersymmetry is incorporated. The reason is that the new superpartner particles required by supersymmetry contribute additional quantum fluctuations, and these fluctuations are just right to nudge the strengths of the forces to converge with one another. To many physicists, it is extremely difficult to believe that nature would choose the forces so that they almost, but not quite, have strengths that microscopically unify, microscopically become equal. It's like putting together a jigsaw puzzle in which the final piece is slightly misshapen and won't cleanly fit into its appointed position. Supersymmetry deftly refines its shape so that all pieces firmly lock into place. Another aspect of this latter realization is that it provides a possible answer to the question, why haven't we discovered any of the superpartner particles? The calculations that lead to the convergence of the force strengths, as well as other considerations studied by a number of physicists, indicate that the superpartner particles must be a good deal heavier than the known particles. Although no definitive predictions can be made, studies show that the superpartner particles might be 1,000 times as massive as a proton, if not heavier. As even our state-of-the-art accelerators cannot quite reach such energies, this provides an explanation for why these particles have not, as yet, been discovered. In Chapter 9, we will return to a discussion of the experimental prospects for determining in the near future whether supersymmetry truly is a property of our world. Of course, the reasons we have given for believing in, or at least not yet rejecting, supersymmetry are far from airtight. We have described how supersymmetry elevates our theories to their most symmetric form, but you might suggest that the universe does not care about attaining the most symmetric form that is mathematically possible. We have noted the important technical point that supersymmetry relieves us from the delicate task of tuning numerical parameters in the standard model to avoid subtle quantum problems. But you might argue that the true theory describing nature may very well walk the fine edge between self-consistency and self-destruction. We have discussed how supersymmetry modifies the intrinsic strengths of the three non-gravitational forces at tiny distances in just the right way, for them to merge together into a grand unified force. But you might argue, again, that nothing in the design of nature dictates that these force strengths must exactly match on microscopic scales. And finally, you might suggest that a simpler explanation for why the superpartner particles have never been found is that our universe is not supersymmetric, and therefore the superpartners do not exist. No one can refute any of these responses. But the case for supersymmetry is strengthened immensely when we consider its role in string theory. Supersymmetry in string theory. The original string theory that emerged from Veneziano's work in the late 1960s incorporated all of the symmetries discussed at the beginning of this chapter, but it did not incorporate supersymmetry, which had not yet been discovered. This first theory based on the string concept was, more precisely, called the bosonic string theory. The name bosonic indicates that all of the vibrational patterns of the bosonic string have spins that are a whole number. There are no fermionic patterns, that is, no patterns with spins differing from a whole number by a half unit. This led to two problems. First, if string theory was to describe all forces and all matter, it would somehow have to incorporate fermionic vibrational patterns, since the known matter particles all have spin. Bafu? Second, and far more troubling, was the realization that there was one pattern of vibration in bosonic string theory, whose mass, more precisely, whose mass squared, was negative, a so-called tachyon. Even before string theory, physicists had studied the possibility that our world might have tachyon particles, in addition to the familiar particles that all have positive masses, but their efforts showed that it is difficult, if not impossible, for such a theory to be logically sensible. Similarly, in the context of bosonic string theory, physicists tried all sorts of fancy footwork to make sense of the bizarre prediction of a tachyon vibrational pattern, but to no avail. These features made it increasingly clear that although it was an interesting theory, the bosonic string was missing something essential. In 1971, Pierre Ramond of the University of Florida took up the challenge of modifying the bosonic string theory to include fermionic patterns of vibration. Through his work and subsequent results of Schwartz and André Neveu, a new version of string theory began to emerge. And much to everyone's surprise, the bosonic and the fermionic patterns of vibration of this new theory appeared to come in pairs. For each bosonic pattern, there was a fermionic pattern, and vice versa. By 1977, insights of Ferdinando Gliozzi of the University of Turin, Schurk, and David Olive of Imperial College put this pairing into the proper light. The new string theory incorporated supersymmetry, and the observed pairing of bosonic and fermionic vibrational patterns reflected this highly symmetric character. Supersymmetric string theory, superstring theory that is, had been born. Moreover, the work of Gliozzi, Schurk, and Olive had one other crucial result. They showed that the troublesome tachyon vibration of the bosonic string does not afflict the superstring. Slowly, the pieces of the string puzzle were falling into place. Nevertheless, the major initial impact of the work of Ramond, and also of Neveu and Schwartz, was not actually in string theory. By 1973, the physicists Julian Wess and Bruno Zumino realized that supersymmetry, the new symmetry emerging from the reformulation of string theory, was applicable even to theories based on point particles. They rapidly made important strides toward incorporating supersymmetry into the framework of point-particle quantum field theory. And since at the time, quantum field theory was the central rage of the mainstream particle physics community, with string theory increasingly becoming a subject on the fringe, the insights of Wess and Zumino launched a tremendous amount of subsequent research on what has come to be called supersymmetric quantum field theory. The supersymmetric standard model, discussed in the preceding section, is one of the crowning theoretical achievements of these pursuits. We now see that through historical twists and turns, even this point-particle theory owes a great debt to string theory. With the resurgence of superstring theory in the mid-1980s, supersymmetry has re-emerged in the context of its original discovery. And in this framework, the case for supersymmetry goes well beyond that presented in the preceding section. String theory is the only way we know of to merge general relativity and quantum mechanics. But it's only the supersymmetric version of string theory that avoids the pernicious tachyon problem and that has fermionic vibrational patterns that can account for the matter particles constituting the world around us. Supersymmetry, therefore, comes hand in hand with the string theory's proposal for a quantum theory of gravity, as well as with its grand claim of uniting all forces and all of matter. If string theory is right, physicists expect that so is supersymmetry. Until the mid-1990s, however, one particularly troublesome aspect plagued supersymmetric string theory: a super embarrassment of riches. If someone tells you that they have solved the mystery of Amelia Earhart's fate, you might be skeptical at first, but if they have a well-documented, thoroughly pondered explanation, you would probably hear them out, and who knows, you might even be convinced. But what if, in the next breath, they tell you that they actually have a second explanation as well? You listen patiently, and are surprised to find the alternate explanation to be as well documented and thought through as the first. And after finishing the second explanation, you are presented with a third, a fourth, and even a fifth explanation, each different from the others and yet equally convincing. No doubt, by the end of the experience, you would feel no closer to Amelia Earhart's true fate than you did at the outset. In the arena of fundamental explanations, more is definitely less. By 1985, string theory, notwithstanding the justified excitement it was engendering, was starting to sound like our overzealous Earhart expert. The reason is that by 1985, physicists realized that supersymmetry, by then a central element in the structure of string theory, could actually be incorporated into string theory in not one but 5 different ways. Each method results in a pairing of bosonic and fermionic vibrational patterns, but the details of this pairing, as well as numerous other properties of the resulting theories, differ substantially. Although their names are not all that important, it's worth recording that these 5 supersymmetric string theories are called the Type 1 theory, the Type 2A theory, the Type 2B theory, the heterotic Type O or 32 theory, pronounced O32, and the heterotic type E8XE8 theory, pronounced E8 times E8. All the features of string theory that we have discussed to this point are valid for each of these theories. They differ only in the finer details. Having 5 different versions of what is supposedly the TOE, possibly the ultimate unified theory, was quite an embarrassment for string theorists, just as there is only one true explanation for whatever happened to Amelia Earhart. Regardless of whether we will ever find it, we expect the same to be true regarding the deepest, most fundamental understanding of how the world works. We live in one universe. We expect one explanation. One suggestion for resolving this problem might be that although there are 5 different superstring theories, 4 might be ruled out simply by experiment, leaving one true and relevant explanatory framework. But even if this were the case, we would still be left with the nagging question of why the other theories exist in the first place. In the wry words of Witten, if one of the 5 theories describes our universe, who lives in the other 4 worlds? A physicist's dream is that the search for the ultimate answers will lead to a single, unique, absolutely inevitable conclusion. Ideally, the final theory, whether string theory or something else, should be the way it is because there simply is no other possibility. If we were to discover that there is only one logically sound theory incorporating the basic ingredients of relativity and quantum mechanics, many feel that we would have reached the deepest understanding of why the universe has the properties it does. In short, this would be unified theory paradise. As we will see in Chapter 12, recent research has taken superstring theory one giant step closer to this unified utopia by showing that the 5 different theories are, remarkably, actually 5 different ways of describing one and the same overarching theory. Superstring theory has the uniqueness pedigree. Things seem to be falling into place, but as we will discuss in the next chapter, unification through string theory does require one more significant departure from conventional wisdom. Chapter 8. More dimensions than meet the eye. Einstein resolved 2 of the major scientific conflicts of the past 100 years through special and then general relativity. Although the initial problems that motivated his work did not portend the outcome, each of these resolutions completely transformed our understanding of space and time. String theory resolves the 3rd major scientific conflict of the past century, and in a manner that even Einstein would likely have found remarkable, it requires that we subject our conceptions of space and time to yet another radical revision. String theory so thoroughly shakes the foundations of modern physics that even the generally accepted number of dimensions in our universe, something so basic that you might think it beyond questioning, is dramatically and convincingly overthrown. The illusion of the familiar. Experience informs intuition. But it does more than that. Experience sets the frame within which we analyze and interpret what we perceive. You would no doubt expect, for instance, that the wild child raised by a pack of wolves would interpret the world from a perspective that differs substantially from your own. Even less extreme comparisons, such as those between people raised in very different cultural traditions, serve to underscore the degree to which our experiences determine our interpretive mindset. Yet there are certain things that we all experience, and it is often the beliefs and expectations that follow from these universal experiences that can be the hardest to identify and the most difficult to challenge. A simple but profound example is the following. If you were to get up from reading this book, you could move in our 3 independent directions, that is, through 3 independent spatial dimensions. Absolutely any path you follow, regardless of how complicated, results from some combination of motion through what we might call the left-right dimension, the back-forth dimension, and the up-down dimension. Every time you take a step, you implicitly make three separate choices that determine how you move through these three dimensions. An equivalent statement, as encountered in our discussion of special relativity, is that any location in the universe can be fully specified by giving three pieces of data, where it is relative to these three spatial dimensions. In familiar language, you can specify a city address, say, by giving a street, location in the left-right dimension, a cross street or an avenue, location in the back-fourth dimension, and a floor number, location in the up-down dimension. And from a more modern perspective, we have seen that Einstein's work encourages us to think about time as another dimension, the future-past dimension, giving us a total of 4 dimensions, 3 space dimensions and 1 time dimension. You specify events in the universe by telling where and when they occur. This feature of the universe is so basic, so consistent, and so thoroughly pervasive that it really does seem beyond questioning. In 1919, however, a little-known Polish mathematician named Theodor Kaluza from the University of Königsberg had the temerity to challenge the obvious. He suggested that the universe might not actually have 3 spatial dimensions. It might have more. Sometimes silly-sounding suggestions are plain silly. Sometimes they rock the foundations of physics. Although it took quite some time to percolate, Kaluza's suggestion has revolutionized our formulation of physical law. We are still feeling the aftershocks of his astonishingly prescient insight. Kaluza's idea and Klein's refinement. The suggestion that our universe might have more than 3 spatial dimensions may well sound fatuous, bizarre, or mystical. In reality, though, it is concrete and thoroughly plausible. To see this, it's easiest to shift our sights temporarily from the whole universe and think about a more familiar object, such as a long, thin garden hose. Imagine that a few hundred feet of garden hose is stretched across a canyon, and you view it from, say, a quarter of a mile away, as in Figure 8.1a. From this distance, you will easily perceive the long, unfurled, horizontal extent of the hose, but unless you have uncanny eyesight, the thickness of the hose will be difficult to discern. From your distant vantage point, you would think that if an ant were constrained to live on the hose, it would have only one dimension in which to walk, the left-right dimension along the hose's length. If someone asked you to specify where the ant was at a given moment, you would need to give only one piece of data: the distance of the ant from the left, or the right, end of the hose. The upshot is that from a quarter of a mile away, a long piece of garden hose appears to be a one-dimensional object. In reality, we know that the hose does have thickness. You might have trouble resolving this from a quarter mile, but by using a pair of binoculars, you can zoom in on the hose and observe its girth directly, as shown in Figure 8.1b. From this magnified perspective, you see that a little ant living on the hose actually has 2 independent directions in which it can walk: along the left-right dimension spanning the length of the hose as already identified, and along the clockwise-counterclockwise dimension around the circular part of the hose. You now realize that to specify where the tiny ant is at any given instant, you must actually give 2 pieces of data: where the ant is along the length of the hose, and where the ant is along its circular girth. This reflects the fact the surface of the garden hose is 2-dimensional. Nonetheless, there is a clear difference between these 2 dimensions. The direction along the length of the hose is long, extended, and easily visible. The direction circling around the thickness of the hose is short, curled up, and harder to see. To become aware of the circular dimension, you have to examine the hose with significantly greater precision. This example underscores a subtle and important feature of spatial dimensions. They come in 2 varieties. They can be large, extended, and therefore directly manifest, or they can be small, curled up, and much more difficult to detect. Of course, in this example, you did not have to exert a great deal of effort to reveal the curled-up dimension encircling the thickness of the hose. You merely had to use a pair of binoculars. However, if you had a very thin garden hose, as thin as a hair or a capillary, detecting its curled-up dimension would be more difficult. In a paper he sent to Einstein in 1919, Kaluza made an astounding suggestion. He proposed that the spatial fabric of the universe might possess more than the three dimensions of common experience. The motivation for this radical thesis, as we will discuss shortly, was Kaluza's realization that it provided an elegant and compelling framework for weaving together Einstein's general relativity and Maxwell's electromagnetic theory into a single, unified conceptual framework. But, more immediately, how can this proposal be squared with the apparent fact that we see precisely three spatial dimensions? The answer, implicit in Kaluza's work and subsequently made explicit and refined by the Swedish mathematician Oskar Klein in 1926, is that the spatial fabric of our universe may have both extended and curled-up dimensions. That is, just like the horizontal extent of the garden hose, our universe has dimensions that are large, extended, and easily visible, the three spatial dimensions of common experience. But like the circular girth of a garden hose, the universe may also have additional spatial dimensions that are tightly curled up into a tiny space, a space so tiny that it has so far eluded detection by even our most refined experimental equipment. To gain a clearer image of this remarkable proposal, let's reconsider the garden hose for a moment. Imagine that the hose is painted with closely spaced black circles along its girth. From far away, as before, the garden hose looks like a thin, one-dimensional line, but if you zoom in with binoculars, you can detect the curled-up dimension even more easily after our paint job, and you see the image illustrated in Figure 8.2. This figure emphasizes that the surface of the garden hose is two-dimensional, with one large, extended dimension and one small, circular dimension. Kaluza and Klein propose that our spatial universe is similar, but that it has three large, extended spatial dimensions and one small circular dimension, for a total of four spatial dimensions. It is difficult to draw something with that many dimensions, so for visualization purposes we must settle for an illustration incorporating two large dimensions and one small circular dimension. We illustrate this in Figure 8.3, in which we magnify the fabric of space in much the same way that we zoomed in on the surface of the garden hose. The lowest image in the figure shows the apparent structure of space, the ordinary world around us, on familiar distance scales such as meters. These distances are represented by the largest set of grid lines. In the subsequent images, we zoom in on the fabric of space by focusing our attention on ever smaller regions, which we sequentially magnify in order to make them easily visible. At first, as we examine the fabric of space on shorter distance scales, not much happens. It appears to retain the same basic form as it has on larger scales, as we see in the first three levels of magnification. However, as we continue on our journey toward the most microscopic examination of space, the fourth level of magnification in Figure 8.3, a new, curled-up, circular dimension becomes apparent, much like the circular loops of thread making up the pile of a tightly woven piece of carpet. Kaluza and Klein suggested that the extracircular dimension exists at every point in the extended dimensions, just as the circular girth of the garden hose exists at every point along its unfurled, horizontal extent. For visual clarity, we have drawn only an illustrative sample of the circular dimension at regularly spaced points in the extended dimensions. We show a close-up of the Kaluza-Klein vision of the microscopic structure of the spatial fabric in Figure 8.4. The similarity with the garden hose is manifest, although there are some important differences. The universe has three large extended space dimensions, only two of which we have actually drawn, compared with the garden hose's one, and, more important, we are now describing the spatial fabric of the universe itself, not just an object, like the garden hose that exists within the universe. But the basic idea is the same. Like the circular girth of the garden hose, if the additional curled-up, circular dimension of the universe is extremely small, it is much harder to detect than the manifest, large, extended dimensions. In fact, if its size is small enough, it will be beyond detection by even our most powerful magnifying instruments, And of utmost importance, the circular dimension is not merely a circular bump within the familiar extended dimensions as the illustration might lead you to believe. Rather, the circular dimension is a new dimension, one that exists at every point in the familiar extended dimensions just as each of the up-down, left-right, and back-forth dimensions exists at every point as well. It is a new and independent direction in which an ant, if it were small enough, could move. To specify the spatial location of such a microscopic ant, we would need to say where it is in the three familiar extended dimensions, represented by the grid, and also where it is in the circular dimension. We would need 4 pieces of spatial information. If we add in time, we get a total of 5 pieces of spacetime information, 1 more than we normally would expect. And so, rather surprisingly, we see that although we are aware of only 3 extended spatial dimensions, Kaluza's and Klein's reasoning shows that this does not preclude the existence of additional curled-up dimensions, at least if they are very small. The universe may very well have more dimensions than meet the eye. How small is small? Cutting-edge equipment can detect structures as small as a billionth of a meter. So long as an extra dimension is curled up to a size less than this tiny distance, it is too small for us to detect. In 1926, Klein combined Kaluza's initial suggestion with some ideas from the emerging field of quantum mechanics. His calculations indicated that the additional circular dimension might be as small as the Planck length, far shorter than experimental accessibility. Since then, physicists have called the possibility of extra tiny space dimensions Kaluza-Klein theory. Comings and goings on a garden hose. The tangible example of the garden hose and the illustration in Figure 8.3 are meant to give you some sense of how it is possible that our universe has extra spatial dimensions. But even for researchers in the field, it is quite difficult to visualize a universe with more than 3 spatial dimensions. For this reason, physicists often hone their intuition about these extra dimensions by contemplating what life would be like if we lived in an imaginary, lower-dimensional universe, following the lead of Edwin Abbott's enchanting 1884 classic popularization Flatland, in which we slowly realize that the universe has more dimensions than those of which we are directly aware. Let's try this by imagining a 2-dimensional universe shaped like our garden hose. Doing so requires that you relinquish an outsider's perspective that views the garden hose as an object in our universe. Rather, you must leave the world as we know it and enter a new garden hose universe in which the surface of a very long garden hose, you can think of it as being infinitely long, is all there is as far as spatial extent. Imagine that you are a tiny ant living your life on its surface. Let's start by making things even a little more extreme. Imagine that the length of the circular dimension of the garden hose universe is very short, so short that neither you nor any of your fellow hose dwellers are even aware of its existence. Instead, you and everyone else living in the hose universe take one basic fact of life to be so evident as to be beyond questioning. The universe has one spatial dimension. If the garden hose universe had produced its own ant Einstein, Jose dwellers would say that the universe has one spatial and one time dimension. In fact, this feature is so self-evident that Jose dwellers have named their home Lineland, directly emphasizing its having one spatial dimension. Life in Lineland is very different from life as we know it. For example, the body with which you are familiar cannot fit in Lineland. No matter how much effort you may put into body reshaping, one thing you can't get around is that you definitely have length, width, and breadth, spatial extent in 3 dimensions. In Lineland, there is no room for such an extravagant design. Remember, although your mental image of Lineland may still be tied to a long, thread-like object existing in our space, you really need to think of Lineland as a universe. All there is. As an inhabitant of Lineland, you must fit within its spatial extent. Try to imagine it. Even if you take on an ant's body, you still will not fit. You must squeeze your ant body to look more like a worm, and then further squeeze it until you have no thickness at all. To fit in Lineland, you must be a being that has only length. Imagine further that you have an eye on each end of your body. Unlike your human eyes, which can swivel around to look in all the 3 dimensions, your eyes as a line being are forever locked into position. each staring off into the one-dimensional distance. This is not an anatomical limitation of your new body. Instead, you and all other line beings recognize that since lineland has but one dimension, there simply isn't another direction in which your eyes can look. Forward and backward exhaust the extent of lineland. We can try to go further in imagining life in lineland, but we quickly realize that there's not much more to it. For instance, if another line being is on one or the other side of you, picture how it will appear. You will see one of her eyes, the one facing you. But unlike human eyes, hers will be a single dot. Eyes in lineland have no features and display no emotion. There's just no room for these familiar characteristics. Moreover, you will be forever stuck with this dot-like image of your neighbor's eye. If you wanted to pass her and explore the realm of lineland on the other side of her body, you would be in for a great disappointment. You can't pass by her. She is fully blocking the road, and there is no space in lineland to go around her. The order of line beings as they are sprinkled along the extent of lineland is fixed and unchanging. What drudgery! A few thousand years after a Religious epiphany in lineland, a line being named Kaluza K Line offers some hope for the downtrodden line dwellers, either from divine inspiration or from the sheer exasperation of years of staring at his neighbor's dot eye. He suggests that lineland may not be one-dimensional after all. What if he theorizes lineland is actually two-dimensional, with the second space dimension being a very small, circular direction that has, as yet, evaded direct detection because of its tiny spatial extent? He goes on to paint a picture of a vastly new life if only this curled-up space direction would expand in size, something that is at least possible according to the recent work of his colleague Einstein. Kaluza K. Line describes a universe that amazes you and your comrades and fills everyone with hope. A universe in which line beings can move freely past one another by making use of the second dimension, the end of spatial enslavement. We realize that Kaluza K. Line is describing life in a thickened garden hose universe. In fact, if the circular dimension were to grow, inflating lineland into the garden hose universe, your life would change in profound ways. Take your body, for example. As a line being, anything between your two eyes constitutes the interior of your body. Your eyes, therefore, play the same role for your line body as skin plays for an ordinary human body. They constitute the barrier between the inside of your body and the outside world. A doctor in lineland can access the interior of your line body only by puncturing its surface. In other words, surgery in lineland takes place through the eyes. But now imagine what happens if lineland does, a la Kaluza K line, have a secret curled-up dimension, and if this dimension expands to an observably large size. Now, one line being can view your body at an angle and thereby directly see into its interior, as we illustrate in Figure 8.5. Using this second dimension, a doctor can operate on your body by reaching directly inside your exposed interior. Weird! In time, line beings, no doubt, would develop a skin-like cover to shield the newly exposed interior of their bodies from contact with the outside world. And moreover, they would undoubtedly evolve into beings with length as well as breadth. Flat beings sliding along the two-dimensional garden hose universe as illustrated in Figure 8.6. If the circular dimension were to grow very large indeed, this two-dimensional universe would be closely akin to Abbott's Flatland, an imaginary, two-dimensional world Abbott suffused with a rich cultural heritage and even a satirical caste system based upon one's geometrical shape. Whereas it's hard to imagine anything interesting happening in lineland, there's just not enough room. Life on a garden hose becomes replete with possibilities. The evolution from 1 to 2 observably large space dimensions is dramatic. And now the refrain. Why stop there? The two-dimensional universe might itself have a curled-up dimension and therefore secretly be three-dimensional. We can illustrate this with Figure 8.4 Kamya, so long as we recognize that we are now imagining that there are only two extended space dimensions, whereas when we first introduced this figure, we were imagining the flat grid to represent three extended dimensions. If the circular dimension should expand, a two-dimensional being would find itself in a vastly new world in which movement is not limited just to left, right, and back, forth along the extended dimensions. Now, a being can also move in a third dimension, the up-down direction along the circle. In fact, if the circular dimension were to grow to a large enough size, this could be our three-dimensional universe. We do not know at present whether any of our three spatial dimensions extends outward forever, or in fact curls back on itself in the shape of a giant circle, beyond the range of our most powerful telescopes. If the circular dimension in Figure 8.4 got big enough, billions of light-years in extent, the figure could very well be a drawing of our world, but the refrain replays. Why stop there? This takes us to Kaluza's and Klein's vision, that our three-dimensional universe might have a previously unanticipated curled-up fourth spatial dimension. If this striking possibility, or its generalization to numerous curled-up dimensions, to be discussed shortly, is true, and if these curled-up dimensions were themselves to expand to a macroscopic size, the lower dimensional examples discussed make it clear that life as we know it would change immensely. Surprisingly, though, even if they should always stay curled up and small, the existence of extra curled-up dimensions has profound implications. Unification in higher dimensions. Although Kaluza's 1919 suggestion that our universe might have more spatial dimensions than those of which we are directly aware was a remarkable possibility in its own right, something else really made it compelling. Einstein had formulated general relativity in the familiar setting of a universe with three spatial dimensions and one time dimension. The mathematical formalism of his theory, however, could be extended fairly directly to write down analogous equations for a universe with additional space dimensions. Under the modest assumption of one extra space dimension, Kaluza carried out the mathematical analysis and explicitly derived the new equations. He found that in the revised formulation, the equations pertaining to the three ordinary dimensions were essentially identical to Einstein's. But because he included an extra space dimension, not surprisingly, Kaluza found extra equations beyond those Einstein originally derived. After studying the extra equations associated with the new dimension, Kaluza realized that something amazing was going on. The extra equations were none other than those Maxwell had written down in the 1880s for describing the electromagnetic force. By adding another space dimension, Kaluza had united Einstein's theory of gravity with Maxwell's theory of light. Before Kaluza's suggestion, gravity and electromagnetism were thought of as two unrelated forces. Nothing had even hinted that there might be a relation between them. By having the bold creativity to imagine that our universe has an additional space dimension, Kaluza suggested that there was a deep connection indeed. His theory argued that both gravity and electromagnetism are associated with ripples in the fabric of space. Gravity is carried by ripples in the familiar three space dimensions, while electromagnetism is carried by ripples involving the new, curled-up dimension. Kaluza sent his paper to Einstein, and at first Einstein was quite intrigued. On April 21, 1919, Einstein wrote back to Kaluza and told him that it had never occurred to him that unification might be achieved through a five-dimensional, four space and one time, cylinder world. He added, "At first glance, I like your idea enormously." About a week later, though, Einstein wrote Kaluza again, this time with some skepticism. "I have read through your paper and find it really interesting. Nowhere so far can I see an impossibility. On the other hand, I have to admit that the arguments brought forward so far do not appear convincing enough." But then, on October 14, 1921, more than 2 years later, Einstein wrote to Kaluza again, having had time to digest Kaluza's novel approach more fully. "I am having second thoughts about having restrained you from publishing your idea on a unification of gravitation and electricity 2 years ago. If you wish, I shall present your paper to the Academy after all." Belatedly, Kaluza had received the master's stamp of approval. Although it was a beautiful idea, subsequent detailed study of Kaluza's proposal, augmented by Klein's contributions, showed that it was in serious conflict with experimental data. The simplest attempts to incorporate the electron into the theory predicted relations between its mass and its charge that were vastly different from their measured values. because there did not seem to be any obvious way of getting around this problem. Many of the physicists who had taken notice of Kaluza's idea lost interest. Einstein and others continued now and then to dabble with the possibility of extra curled-up dimensions, but it quickly came to be an enterprise on the outskirts of theoretical physics. In a real sense, Kaluza's idea was way ahead of its time. The 1920s marked the start of a bull market for theoretical and experimental physics concerned with understanding the basic laws of the microworld. Theorists had their hands full as they sought to develop the structure of quantum mechanics and quantum field theory. Experimentalists had the detailed properties of the atom as well as numerous other elementary material constituents to discover. Theory guided experiment and experiment refined theory as physicists pushed forward for half a century, ultimately to reveal the Standard Model. It is no wonder that speculations on extra dimensions took a distant back seat during these productive and heady times. With physicists exploring powerful quantum methods, the implications of which gave rise to experimentally testable predictions, there was little interest in the mere possibility that the universe might be a vastly different place on length scales far too small to be probed by even the most powerful of instruments. But sooner or later, bull markets lose steam. By the late 1960s and early 1970s, the theoretical structure of the Standard Model was in place. By the late 1970s and early 1980s, many of its predictions had been verified experimentally, and most particle physicists concluded that it was just a matter of time before the rest were confirmed as well. Although a few important details remained unresolved, many felt that the major questions concerning the strong, weak, and electromagnetic forces had been answered. The time was finally ripe to return to the grandest question of all, the enigmatic conflict between general relativity and quantum mechanics. The success in formulating a quantum theory of three of nature's forces emboldened physicists to try to bring the fourth, gravity, into the fold. Having pursued numerous ideas that all ultimately failed, the mindset of the community became more open to comparatively radical approaches. After being left for dead in the late 1920s, Kaluza-Klein theory was resuscitated. Modern Kaluza-Klein theory. The understanding of physics had significantly changed and substantially deepened in the 6 decades since Kaluza's original proposal. Quantum mechanics had been fully formulated and experimentally verified. The strong and the weak forces, unknown in the 1920s, had been discovered and were largely understood. Some physicists suggested that Kaluza's original proposal had failed because he was unaware of these other forces, and had therefore been too conservative in his revamping of space. More forces meant the need for even more dimensions. It was argued that a single new circular dimension, although able to show hints of a connection between general relativity and electromagnetism, was just not enough. By the mid-1970s, an intense research effort was underway focusing on higher dimensional theories with numerous curled-up spatial directions. Figure 8.7 illustrates an example with 2 extra dimensions that are curled up into the surface of a ball, that is, a sphere. As in the case of the single circular dimension, these extra dimensions are tacked onto every point of the familiar extended dimensions. For visual clarity, we again have drawn only an illustrative sample of the spherical dimensions at regularly spaced grid points in the extended dimensions. Beyond proposing a different number of extra dimensions, one can also imagine other shapes for the extra dimensions. For instance, in Figure 8.8 we illustrate a possibility in which there are again 2 extra dimensions, now in the shape of a hollow donut, that is, a torus. Although they are beyond our ability to draw, more complicated possibilities can be imagined in which there are 3, 4, 5, essentially any number of extra spatial dimensions, curled up into a wide spectrum of exotic shapes. The essential requirement, again, is that all of these dimensions have a spatial extent smaller than the smallest length scales we can probe, since no experiment has yet revealed their existence. The most promising of the higher dimensional proposals were those that also incorporated supersymmetry. Physicists hoped that the partial canceling of the most severe quantum fluctuations, arising from the pairing of superpartner particles, would help to soften the hostilities between gravity and quantum mechanics. They coined the name higher dimensional supergravity to describe those theories encompassing gravity, extra dimensions, and supersymmetry. As had been the case with Kaluza's original attempt, various versions of higher dimensional supergravity looked quite promising at first. The new equations resulting from the extra dimensions were strikingly reminiscent of those used in the description of electromagnetism and the strong and the weak forces. But detailed scrutiny showed that the old conundrums persisted. Most importantly, the pernicious short-distance quantum undulations of space were lessened by supersymmetry, but not sufficiently to yield a sensible theory. Physicists also found it difficult to find a single, sensible, higher-dimensional theory incorporating all features of forces and matter. It gradually became clear that bits and pieces of a unified theory were surfacing, but that a crucial element capable of tying them all together in a quantum mechanically consistent manner was missing. In 1984, this missing piece, string theory, dramatically entered the story and took center stage. More dimensions and string theory. By now, you should be convinced that our universe may have additional curled-up spatial dimensions. Certainly, so long as they are small enough, nothing rules them out. But extra dimensions may strike you as an artifice. Our inability to probe distances smaller than a billionth of a meter permits not only extra tiny dimensions, but all manner of whimsical possibilities as well in a microscopic civilization populated by even tinier green people. While the former certainly seems more rationally motivated than the latter, the act of postulating either of these experimentally untested and at present untestable possibilities might seem equally arbitrary. Such was the case until string theory. Here is a theory that resolves the central dilemma confronting contemporary physics, the incompatibility between quantum mechanics and general relativity, and that unifies our understanding of all of nature's fundamental material constituents and forces. But to accomplish these feats, it turns out that string theory requires that the universe have extra space dimensions. Here's why. One of the main insights of quantum mechanics is that our predictive power is fundamentally limited to asserting that such and such outcome will occur with such and such probability. Although Einstein felt that this was a distasteful feature of our modern understanding, and you may agree, it certainly appears to be fact. Let's accept it. Now, we all know that probabilities are always numbers between 0 and 1. Equivalently, when expressed as percentages, probabilities are numbers between 0 and 100. Physicists have found that a key signal that a quantum mechanical theory has gone haywire is that particular calculations yield probabilities that are not within this acceptable range. For instance, we mentioned earlier that a sign of the grinding incompatibility between general relativity and quantum mechanics in a point-particle framework is that calculations result in infinite probabilities. As we have discussed, string theory cures these infinities. But what we have not as yet mentioned is that a residual, somewhat more subtle problem still remains. In the early days of string theory, physicists found that certain calculations yielded negative probabilities, which are also outside of the acceptable range. So, at first sight, string theory appeared to be awash in its own quantum mechanical hot water. With stubborn determination, physicists sought and found the cause of this unacceptable feature. The explanation begins with a simple observation. If a string is constrained to lie on a two-dimensional surface, such as the surface of a table or a garden hose, the number of independent directions in which it can vibrate is reduced to 2, the left-right and back-forth dimensions along the surface. Any vibrational pattern that remains on the surface involves some combination of vibrations in these two directions. Correspondingly, we see that this also means that a string in flatland, the garden hose universe, or in any other two-dimensional universe, is also constrained to vibrate in a total of 2 independent spatial directions. If, however, the string is allowed to leave the surface, the number of independent vibrational directions increases to 3, since the string then can also oscillate in the up-down direction. Equivalently, in a universe with 3 spatial dimensions, a string can vibrate in 3 independent directions. Although it gets harder to envision, the pattern continues. In a universe with ever more spatial dimensions, there are ever more independent directions in which it can vibrate. We emphasize this fact of string vibrations because physicists found that the troublesome calculations were highly sensitive to the number of independent directions in which a string can vibrate. The negative probabilities arose from a mismatch between what the theory required and what reality seemed to impose. The calculations showed that if strings could vibrate in 9 independent spatial directions, all of the negative probabilities would cancel out. Well, that's great in theory, but so what? If string theory is meant to describe our world with 3 spatial dimensions, we still seem to be in trouble. But are we? Taking a more than half-century-old lead, we see that Kaluza and Klein provide a loophole. Since strings are so small, not only can they vibrate in large, extended dimensions, they can also vibrate in ones that are tiny and curled up. And so we can meet the 9 space dimension requirement of string theory in our universe by assuming, a la Kaluza and Klein, that in addition to our familiar 3 extended spatial dimensions, there are 6 other curled-up spatial dimensions. In this manner, string theory, which appeared to be on the brink of elimination from the realm of physical relevance, is saved. Moreover, rather than just postulating the existence of extra dimensions, as had been done by Kaluza, Klein, and their followers, string theory requires them. For string theory to make sense, the universe should have 9 space dimensions and 1 time dimension, for a total of 10 dimensions. In this way, Kaluza's 1919 proposal finds its most convincing and powerful forum. Some questions. This raises a number of questions. First, why does string theory require the particular number of 9 space dimensions to avoid nonsensical probability values? This is probably the hardest question in string theory to answer without appealing to mathematical formalism. A straightforward string theory calculation reveals this answer, but no one has an intuitive, non-technical explanation for the particular number that emerges. The physicist Ernest Rutherford once said, in essence, that if you can't explain a result in simple, non-technical terms, then you don't really understand it. He wasn't saying that this means your result is wrong. Rather, he was saying that it means you do not fully understand its origin, meaning, or implications. Perhaps this is true regarding the extra-dimensional character of string theory. In fact, let's take this opportunity to brace, parenthetically, for a central aspect of the second superstring revolution that we will discuss in Chapter 12. The calculation underlying the conclusion that there are 10 space-time dimensions, 9 space and 1 time, turns out to be approximate. In the mid-1990s, Witten, based on his own insights and previous work by Michael Duff from Texas AANDM University and Chris Hall and Paul Townsend from Cambridge University, gave convincing evidence that the approximate calculation actually misses 1 space dimension. String theory, he argued to most string theorists' amazement, actually requires 10 space dimensions and 1 time dimension for a total of 11 dimensions. We will ignore this important result until Chapter 12, as it will have little direct bearing on the material we develop before then. Second, if the equations of string theory, or more precisely the approximate equations guiding our pre-Chapter 12 discussion, show that the universe has 9 space dimensions and 1 time dimension, why is it that 3 space and 1 time dimensions are large and extended while all of the others are tiny and curled up? Why aren't they all extended or all curled up, or some other possibility in between? At present, no one knows the answer to this question. If string theory is right, we should eventually be able to extract the answer. But as yet, our understanding of the theory is not refined enough to reach this goal. That's not to say that there haven't been valiant attempts to explain it. For instance, from a cosmological perspective, we can imagine that all of the dimensions start out being tightly curled up, and then, in a big bang-like explosion, 3 spatial dimensions and 1 time dimension unfurl and expand to their present large extent, while the other spatial dimensions remain small. Rough arguments have been put forward as to why only 3 space dimensions grow large, as we will discuss in Chapter 14. But it's fair to say that these explanations are only in the formative stages. In what follows, we will assume that all but 3 space dimensions are curled up, in accordance with what we see around us. A primary goal of modern research is to establish that this assumption emerges from the theory itself. Third, given the requirement of numerous extra dimensions, is it possible that some are additional time dimensions as opposed to additional space dimensions? If you think about this for a moment, you will see that it's a truly bizarre possibility. We all have a visceral understanding of what it means for the universe to have multiple space dimensions, since we live in a world in which we constantly deal with a plurality. 3. But what would it mean to have multiple times? Would one align with time as we presently experience it psychologically, while the other would somehow be different? It gets even stranger when you think about a curled-up time dimension. For instance, if a tiny ant walks around an extra space dimension that is curled up like a circle, it will find itself often as we like. But if a curled-up dimension is a time dimension, traversing it means returning, after a temporal lapse, to a prior instant in time. This, of course, is well beyond the realm of our experience. Time, as we know it, is a dimension we can traverse in only one direction with absolute inevitability, never being able to return to an instant after it has passed. Of course, it might be that curled-up time dimensions have vastly different properties from the familiar, vast time dimension that we imagine reaching back to the creation of the universe and forward to the present moment. But in contrast to extra spatial dimensions, new and previously unknown time dimensions would clearly require an even more monumental restructuring of our intuition. Some theorists have been exploring the possibility of incorporating extra time dimensions into string theory, but as yet the situation is inconclusive. In our discussion of string theory, we will stick to the more conventional approach in which all of the curled-up dimensions are space dimensions. But the intriguing possibility of new time dimensions could well play a role in future developments. The physical implications of extra dimensions. Years of research, dating Hack to Kaluza's original paper, have shown that even though any extra dimensions that physicists propose must be smaller than we or our equipment can directly see, since we haven't seen them, they do have important indirect effects on the physics that we observe. In string theory, this connection between the microscopic properties of space and the physics we observe is particularly transparent. To understand this, you need to recall that masses and charges of particles in string theory are determined by the possible resonant vibrational string patterns. Picture a tiny string as it moves and oscillates, and you will realize that the resonant patterns are influenced by its spatial surroundings. Think, for example, of ocean waves. Out in the grand expanse of the open ocean, isolated wave patterns are relatively free to form and travel this way or that. This is much like the vibrational patterns of a string as it moves through large, extended spatial dimensions. As in Chapter 6, such a string is equally free to oscillate in any of the extended directions at any moment. But if an ocean wave passes through a more cramped spatial environment, the detailed form of its wave motion will surely be affected by, for example, the depth of the water, the placement and shape of the rocks encountered, the canals through which the water is channeled, and so on. Or think of an organ pipe or a French horn. The sounds that each of these instruments can produce are a direct consequence of the resonant patterns of vibrating air streams in their interior. These are determined by the precise size and shape of the spatial surroundings within the instrument through which the air streams are channeled. Curled-up spatial dimensions have a similar impact on the possible vibrational patterns of a string. Since tiny strings vibrate through all of the spatial dimensions, the precise way in which the extra dimensions are twisted up and curled back on each other strongly influences and tightly constrains the possible resonant vibrational patterns. These patterns, largely determined by the extra-dimensional geometry, constitute the array of possible particle properties observed in the familiar extended dimensions. This means that extra-dimensional geometry determines fundamental physical attributes like particle masses and charges that we observe in the usual three large space dimensions of common experience. This is such a deep and important point that we say it once again, with feeling. According to string theory, the universe is made up of tiny strings whose resonant patterns of vibration are the microscopic origin of particle masses and force charges. String theory also requires extra space dimensions that must be curled up to a very small size to be consistent with our never having seen them. But a tiny string can probe a tiny space. As a string moves about, oscillating as it travels, the geometrical form of the extra dimensions plays a critical role in determining resonant patterns of vibration. Because the patterns of string vibrations appear to us as the masses and charges of the elementary particles, we conclude that these fundamental properties of the universe are determined, in large measure, by the geometrical size and shape of the extra dimensions. That's one of the most far-reaching insights of string theory. Since the extra dimensions so profoundly influence basic physical properties of the universe, we should now seek, with unbridled vigor, an understanding of what these curled-up dimensions look like. What do the curled-up dimensions look like? The extra spatial dimensions of string theory cannot be crumpled up any which way. The equations that emerge from the theory severely restrict the geometrical form that they can take. In 1984, Philip Candelas of the University of Texas at Austin, Gary Horowitz and Andrew Strominger of the University of California at Santa Barbara, and Edward Witten showed that a particular class of six-dimensional geometrical shapes can meet these conditions. They are known as Calabi-Yau spaces, or Calabi-Yau shapes, in honor of two mathematicians, Eugenio Calabi from the University of Pennsylvania and Xingtong Yao from Harvard University, whose research in a related context but prior to string theory plays a central role in understanding these spaces. Although the mathematics describing Calabi-Yau spaces is intricate and subtle, we can get an idea of what they look like with a picture. In Figure 8.9, we show an example of a Calabi-Yau space. As you view this figure, you must bear in mind that the image has built-in limitations. We are trying to represent a six-dimensional shape on a two-dimensional piece of paper, and this introduces significant distortions. Nevertheless, the image does convey the rough idea of what a Calabi-Yau space looks like. The shape in Figure 8.9 is but one of many tens of thousands of examples of Calabi-Yau shapes that meet the stringent requirements for the extra dimensions that emerge from string theory. Although belonging to a club with tens of thousands of members might not sound very exclusive, you must compare it with the infinite number of shapes that are mathematically possible. By this measure, Calabi-Yau spaces are rare indeed. To put it all together, you should now imagine replacing each of the spheres in Figure 8.7, which represented two curled-up dimensions, with a Calabi-Yau space. That is, at every point in the three familiar extended dimensions, string theory claims that there are six hitherto unanticipated dimensions, tightly curled up into one of these rather complicated-looking shapes, as illustrated in Figure 8.10. These dimensions are an integral and ubiquitous part of the spatial fabric. They exist everywhere. For instance, if you sweep your hand in a large arc, you are moving not only through the three extended dimensions, but also through these curled-up dimensions. Of course, because the curled-up dimensions are so small, as you move your hand, you circumnavigate them an enormous number of times, repeatedly returning to your starting point. Their tiny extent means that there is not much room for a large object like your hand to move. It all averages out so that after sweeping your arm, you're completely unaware of the journey you took through the curled-up Calabi-Yau dimensions. This is a stunning feature of string theory, but if you're practically minded, you are bound to bring the discussion back to an essential and concrete issue. Now that we have a better sense of what the extra dimensions look like, what are the physical properties that emerge from strings that vibrate through them? And how do these properties compare with experimental observations? This is string theory's $64,000 question. Chapter 9. The Smoking Gun. Experimental Signatures. Nothing would please string theorists more than to proudly present the world with a list of details, the mass of the electron or the existence of three families of particles, for which there is currently no explanation. In this chapter, we will discuss how far string theorists have gone toward reaching these goals. Ironically, we will see that although string theory has the potential to be the most predictive theory that physicists have ever studied, a theory that has the capacity to explain the most fundamental of nature's properties, physicists have not as yet been able to make predictions with the precision necessary to confront experimental data. Like a child who receives his or her dream gift for Christmas but can't quite get it to work because a few pages of the instructions are missing, today's physicists are in possession of what may well be the holy grail of modern science, but they can't unleash its full predictive power until they succeed in writing the full instruction manual. Nevertheless, as we discuss in this chapter, with a bit of luck, one central feature of string theory could receive experimental verification within the next decade. And with a good deal more luck, indirect fingerprints of the theory could be confirmed at any moment. Crossfire. Is string theory right? We don't know if you share the belief that the laws of physics should not be fragmented into those that govern the large and those that govern the small. And if you also believe that we should not rest until we have a theory whose range of applicability is limitless, string theory is the only game in town. You might well argue, though, that this highlights only physicists' lack of imagination rather than some fundamental uniqueness of string theory. Perhaps. You might further argue that, like the man searching for his lost keys solely under a streetlight, physicists are huddled around string theory merely because the vagaries of scientific energy mountaintop to experimentalists working at a lower base camp. This is a prime goal of present-day research in string theory. No stones have as yet been dislodged from the summit to be sent hurtling down, but, as we now discuss, a few tantalizing and promising pebbles certainly have. The road to experiment. Without monumental technological breakthroughs, we will never be able to focus on the tiny length scales necessary to see a string directly. Physicists can probe down to a billionth of a meter with accelerators that are roughly a few miles in size. Probing smaller distances requires higher energies, and this means larger machines capable of focusing that energy on a single particle. As the Planck length is some 17 orders of magnitude smaller than what we can currently access, using today's technology, we would need an accelerator the size of the galaxy to see individual strings. In fact, Shmuel Nusanov of Tel Aviv University has shown that this rough estimate based on straightforward scaling is likely to be overly optimistic. His more careful study indicates that we would require an accelerator the size of the whole universe. The energy required to probe matter at the Planck length is roughly equal to 1,000 kilowatt-hours. The energy needed to run an average air conditioner for about 100 hours. And so, it's not particularly outlandish. The seemingly insurmountable technological challenge is to focus all of this energy on a single particle, that is, on a single string. As the U.S. Congress ultimately canceled funding for the superconducting supercollider, an accelerator a mere 54 miles in circumference, don't hold your breath while waiting for the money for a Planck probing accelerator. If we are going to test string theory experimentally, it will have to be in an indirect manner. We will have to determine physical implications of string theory that can be observed on length scales that are far larger than the size of a string itself. In their groundbreaking paper, Candelas, Horowitz, Strominger, and Witten took the first steps toward this goal. They not only found that the extra dimensions in string theory must be curled up into a Calabi-Yau shape, but they also worked out some of the implications this has on the possible patterns of string vibrations. One central result they found highlights the amazingly unexpected solutions string theory offers to long-standing particle physics problems. Recall that the elementary particles that the physicists have found fall into three families of identical organization, with the particles in each successive family being increasingly massive. The puzzling question for which there was no insight prior to string theory is, why families and why three? Here is string theory's proposal. A typical Calabi-Yau shape contains holes that are analogous to those found at the center of a phonograph record, or a donut, or a multi-downut, as shown in Figure 9.1. In the higher dimensional Calabi-Yau context, there are actually a variety of different types of holes that can arise, holes which themselves can have a variety of dimensions, multidimensional holes. But Figure 9.1 conveys the basic idea, articles recorded in Table 1.1. String theorists believe that a similar story will one day also explain the properties of the messenger particles of the fundamental forces, listed in Table 1.2. That is, as strings twist and vibrate while meandering through the extended and curled-up dimensions, a small subset of their vast oscillatory repertoire consists of vibrations with spin equal to 1 or 2. These are the candidate force-carrying string vibrational states. Regardless of the shape of the Calabi-Yau space, there is always one vibrational pattern that is massless and has spin 2. We identify this pattern as the graviton. The precise list of spin 1 messenger particles, their number, the strength of the force they convey, the gauge symmetries they respect, though it does depend crucially on the precise geometrical form of the curled-up dimensions. And so, once again, we come to realize that string theory provides a framework for explaining the observed messenger particle content of our universe. That is, for explaining the properties of the fundamental forces, but that without knowing exactly which Calabi-Yau shape the extra dimensions are curled into, we cannot make any definitive predictions or postdictions, beyond Witten's remark regarding the postdiction of gravity. Why can't we figure out which is the right Calabi-Yau shape? Most string theorists blame this on the inadequacy of the theoretical tools currently being used to analyze string theory. As we shall discuss in some detail in Chapter 12, the mathematical framework of string theory is so complicated that physicists have been able to perform only approximate calculations through a formalism known as perturbation theory. In this approximation scheme, each possible Calabi-Yau shape appears to be on equal footing with every other. None is fundamentally singled out by the equations. And since the physical consequences of string theory depend sensitively on the precise form of the curled-up dimensions, without the ability to select one Calabi-Yau space from the many, no definitive experimentally testable conclusions can be drawn. A driving force behind present-day research is to develop theoretical methods that transcend the approximate approach in the hope that, among other benefits, we will be led to a unique Calabi-Yau shape for the extra dimensions. We will discuss progress along these lines in Chapter 13, Exhausting Possibilities. So you might ask, even though we can't as yet figure out which Calabi-Yau shape string theory selects, does any choice yield physical properties that agree with what we observe? In other words, if we were to work out the corresponding physical properties associated with each and every Calabi-Yau shape and collect them in a giant catalog, would we find any that match reality? This is an important question, but for two main reasons, it is also a hard one to answer fully. A sensible start is to focus only on those Calabi-Yau shapes that yield three families. This cuts down the list of viable choices considerably, although many still remain. In fact, notice that we can deform a multi-handled donut from one shape to a slew of others. An infinite variety, in fact, without changing the number of holes it contains. In Figure 9.2, we illustrate one such deformation of the bottom shape from Figure 9.1. In much the same way, we can start with a three-holed Calabi-Yau space and smoothly deform its shape without changing the number of holes, again through what amounts to an infinite sequence of shapes. When we mentioned earlier that there were tens of thousands of Calabi-Yau shapes, we were already grouping together all those shapes that can be changed into one another by such smooth deformations, and we were counting the whole group as one Calabi-Yau space. The problem is that the detailed physical properties of string vibrations, their masses and their response to forces, are very much affected by such detailed changes in shape. But once again, we have no means of selecting one possibility over any other. And no matter how many graduate students physics professors might set to work, it's just not possible to figure out the physics corresponding to an infinite list of different shapes. This realization has led string theorists to examine the physics resulting from a sample of possible Calabi-Yau shapes. Even here, however, life is not completely smooth sailing. The approximate equations that string theorists currently use are not powerful enough to work out the resulting physics fully for any given choice of Calabi-Yau shape. They can take us a long way toward understanding, in the sense of a ballpark estimate, the properties of the string vibrations that we hope will align with the particles we observe. But precise and definitive physical conclusions, such as the mass of the electron or the strength of the weak force, require equations that are far more exact than the present approximate framework. Recall from Chapter 6, and the Price is Right example, that the natural energy scale of string theory is the Planck energy, and it is only through extremely delicate cancellations that string theory yields vibrational patterns with masses in the vicinity of those of the known matter and force particles. Delicate cancellations require precise calculations because even small errors have a profound impact on accuracy. As we will discuss in Chapter 12, during the mid-1990s, physicists have made significant progress toward transcending the present approximate equations, although there is still far to go. So where do we stand? Well, even with the stumbling block of having no fundamental criteria by which to select one Calabi-Yau shape over any other, as well as not having all the theoretical tools necessary to extract the observable consequences of such a choice fully, we can still ask whether any of the choices in the Calabi-Yau catalog gives rise to a world that is in even rough agreement with observation. The answer to this question is quite encouraging. Although most of the entries in the Calabi-Yau catalog yield observable consequences significantly different from our world, different numbers of particle families, different number and types of fundamental forces, among other substantial deviations. A few entries in the catalog yield physics that is qualitatively close to what we actually observe. That is, there are examples of Calabi-Yau spaces that, when chosen for the curled-up dimensions required by string theory, give rise to string vibrations that are closely akin to the particles of the standard model. And, of prime importance, string theory successfully stitches the gravitational force into this quantum mechanical framework. With our present level of understanding, this situation is the best we could have hoped for. If many of the Calabi-Yau shapes were in rough agreement with experiment, the link between a specific choice and the physics we observe would be less compelling. Many choices could fit the bill, and hence none would appear to be singled out, even from an experimental perspective. On the other hand, if none of the Calabi-Yau shapes came even remotely close to yielding observed physical properties, it would seem that string theory, although a beautiful theoretical framework, could have no relevance for our universe. Finding a small number of Calabi-Yau shapes that, with our present, fairly coarse ability to determine detailed physical implications, appear to be well within the ballpark of acceptability is an extremely encouraging outcome. Explaining the elementary matter and force particle properties would be among the greatest, if not the greatest, of scientific achievements. Nevertheless, you might ask whether there are any string-theoretic predictions, as opposed to postdictions, that experimental physicists could attempt to confirm, either now or in the foreseeable future. There are. Superparticles. The theoretical hurdles currently preventing us from extracting detailed string predictions force us to search for generic, rather than specific aspects of a universe consisting of strings. Generic in this context refers to characteristics that are so fundamental to string theory that they are fairly insensitive to, if not completely independent of, those detailed properties of the theory that are now beyond our theoretical purview. Such characteristics can be discussed with confidence, even with an incomplete understanding of the full theory. In subsequent chapters, we shall return to other examples, but for now we focus on 1. Supersymmetry. As we have discussed, a fundamental property of string theory is that it is highly symmetric, incorporating not only intuitive symmetry principles but respecting as well the maximal mathematical extension of these principles, supersymmetry. This means, as discussed in Chapter 7, the patterns of string vibrations come in pairs, superpartner pairs, differing from each other by a half unit of spin. If string theory is right, then some of the string vibrations will correspond to the known elementary particles. And due to the supersymmetric pairing, string theory makes the prediction that each such known particle will have a superpartner. We can determine the force charges that each of these superpartner particles should carry, but we do not currently have the ability to predict their masses. Even so, the prediction that superpartners exist is a generic feature of string theory. It is a property of string theory that is true, independent of those aspects of the theory we haven't yet figured out. No superpartners of the known elementary particles have ever been observed. This might mean that they do not exist and that string theory is wrong. But many particle physicists feel that it means that the superpartners are very heavy and are thus beyond our current capacity to observe experimentally. Physicists are now constructing a mammoth accelerator in Geneva, Switzerland called the Large Hadron Collider. Hopes run high that this machine will be powerful enough to find the superpartner particles. The accelerator should be ready for operation before 2010, and shortly thereafter, supersymmetry may be confirmed experimentally. As Schwartz has said, supersymmetry ought to be discovered before too long, and when that happens, it's going to be dramatic. You should bear in mind two things, though. Even if superpartner particles are found, this fact alone will not establish that string theory is correct. As we have seen, although supersymmetry was discovered by studying string theory, It has also been successfully incorporated into point-particle theories and is therefore not unique to its stringy origins. Conversely, even if superpartner particles are not found by the Large Hadron Collider, this fact alone will not rule out string theory, since it might be that the superpartners are so heavy that they are beyond the reach of this machine as well. Having said this, if in fact the superpartner particles are found, it will most definitely be strong and exciting circumstantial evidence for string theory. Fractionally charged particles. Another experimental signature of string theory, having to do with electric charge, is somewhat less generic than superpartner particles but equally dramatic. The elementary particles of the Standard Model have a very limited assortment of electric charges. The quarks and antiquarks have electric charges of 1/3 or 2/3, and their negatives, while the other particles have electric charges of 0, 1, or -1. Combinations of these particles account for all known matter in the universe. In string theory, however, it is possible for there to be resonant vibrational patterns corresponding to particles of significantly different electric charges. For instance, the electric charge of a particle can take on exotic fractional values such as 1/5, 1/11, 1/13, or 1/53, among a variety of other possibilities. These unusual charges can arise if the curled-up dimensions have a certain geometrical property. Holes, with the peculiar property that strings encircling them can disentangle themselves only by wrapping around a specified number of times. The details are not particularly important, but it turns out that the number of windings required to get disentangled manifests itself in the allowed patterns of vibration by determining the denominator of the fractional charges. Some Calabi-Yau shapes have this geometrical property, while others do not, and for this reason, the possibility of unusual electric charge fractions is not as generic as the existence of superpartner particles. On the other hand, whereas the prediction of superpartners is not a unique property of string theory, decades of experience have shown that there is no compelling reason for such exotic electric charge fractions to exist in any point-particle theory. They can be forced into a point-particle theory, but doing so would be as natural as the proverbial bull in a china shop. Their possible emergence from simple geometrical properties that the extra dimensions can have makes these unusual electric charges a natural experimental signature for string theory. As with the situation with superpartners, no such exotically charged particles have ever been observed, and our understanding of string theory does not allow for a definitive prediction of their masses should the extra dimensions have the correct properties to generate them. One explanation for not seeing them again is that if they do exist, their masses must be beyond our present technological means. In fact, it is likely that their masses would be on the order of the Planck mass. But should a future experiment come across such exotic electric charges, it would constitute very strong evidence for string theory. Some longer shots. There are yet other ways in which evidence for string theory might be found. For example, Witten has pointed out the long-shot possibility that astronomers might one day see a direct signature of string theory in the data they collect from observing the heavens. As encountered in Chapter 6, the size of a string is typically the Planck length, but strings that are more energetic can grow substantially larger. The energy of the Big Bang, in fact, would have been high enough to produce a few macroscopically large strings that, through cosmic expansion, might have grown to astronomical scales. We can imagine that now or sometime in the future, a string of this sort might sweep across the night sky, leaving an unmistakable and measurable imprint on data collected by astronomers, such as a small shift in the cosmic microwave background temperature. See Chapter 14. As Witten says, although somewhat fanciful, this is my favorite scenario for confirming string theory, as nothing would settle the issue quite as dramatically as seeing a string in a telescope. Closer to Earth, there are other possible experimental signatures of string theory that have been put forward. Here are 5 examples. First, in Table 1.1, we noted that we do not know if neutrinos are just very light, or if in fact they are exactly massless. According to the Standard Model, they are massless, but not for any particularly deep reason. A challenge to string theory is to provide a compelling explanation of present and future neutrino data, especially if experiments ultimately show that neutrinos do have a tiny but non-zero mass. Second, there are certain hypothetical processes that are forbidden by the Standard Model but that may be allowed by string theory. Among these are the possible disintegration of the proton. Don't worry, such disintegration, if true, would happen very slowly, and the possible transmutations and decays of various combinations of quarks in violation of certain long-established properties of point-particle quantum field theory. These kinds of processes are especially interesting because their absence from conventional theory makes them sensitive signals of physics that cannot be accounted for without invoking new theoretical principles. If observed, any one of these processes would provide fertile ground for string theory to offer an explanation. Third, for certain choices of the Calabi-Yau shape, there are particular patterns of string vibration that can effectively contribute new, tiny, long-range force fields. Should the effects of any such new forces be discovered, they might well reflect some of the new physics of string theory. Fourth, as we note in the next chapter, astronomers have collected evidence that our galaxy and possibly the whole of the universe is immersed in a bath of dark matter, the identity of which has yet to be determined. Through its many possible patterns of resonant vibration, string theory suggests a number of candidates for the dark matter. The verdict on these candidates must await future experimental results establishing the detailed properties of the dark matter. And finally, a fifth possible means of connecting string theory to observations involves the cosmological constant. Remember, as discussed in Chapter 3, this is the modification Einstein temporarily imposed on his original equations of general relativity to ensure a static universe. Although the subsequent discovery that the universe is expanding led Einstein to retract the modification, physicists have since realized that there is no explanation for why the cosmological constant should be zero. In fact, the cosmological constant can be interpreted as a kind of overall energy stored in the vacuum of space, and hence its value should be theoretically calculable and experimentally measurable. But, to date, such calculations and measurements lead to a colossal mismatch. Observations show that the cosmological constant is either zero, as Einstein ultimately suggested, or quite small. Calculations indicate that quantum mechanical fluctuations in the vacuum of empty space tend to generate a non-zero cosmological constant whose value is some 120 orders of magnitude, a 1 followed by 120 zeros, larger than experiment allows. This presents a wonderful challenge and opportunity for string theorists. Can calculations in string theory improve on this mismatch and explain why the cosmological constant is zero? Or if experiments do ultimately establish that its value is small but non-zero, can string theory provide an explanation? Should string theorists be able to rise to this challenge, as yet they have not, it would provide a compelling piece of evidence in support of the theory. An appraisal. The history of physics is filled with ideas that when first presented seemed completely untestable, but, through various unforeseen developments, were ultimately brought within the realm of experimental verifiability. The notion that matter is made of atoms, Pauli's hypothesis that there are ghostly neutrino particles, and the possibility that the heavens are dotted with neutron stars and black holes are three prominent ideas of precisely this sort. Ideas that we now embrace fully, but that, at their inception, seemed more like musings of science fiction than aspects of science fact. The motivation for introducing string theory is at least as compelling as any of these three ideas. In fact, string theory has been hailed as the most important and exciting development in theoretical physics since the discovery of quantum mechanics. This comparison is particularly apt because the history of quantum mechanics teaches us that revolutions in physics can easily take many decades to reach maturity. And compared to today's string theorists, the physicists working out quantum mechanics had a great advantage. Quantum mechanics, even when only partially formulated, could make direct contact with experimental results. Even so, it took close to 30 years for the logical structure of quantum mechanics to be worked out, and about another 20 years to incorporate special relativity fully into the theory. We are now incorporating general relativity, a far more challenging task and, moreover, one that makes contact with experiment much more difficult. Unlike those who worked out quantum theory, today's string theorists do not have the shining light of nature, through detailed experimental results, to guide them from one step to the next. This means that it's conceivable that one or more generations of physicists will devote their lives to the investigation and development of string theory without getting a shred of experimental feedback. The substantial number of physicists the world over who are vigorously pursuing string theory know that they are taking a risk, that a lifetime of effort might result in an inconclusive outcome. Undoubtedly, significant theoretical progress will continue, but will it be sufficient to overcome present hurdles and yield definitive, experimentally testable predictions? Will the indirect tests we have discussed above result in a true smoking gun for string theory? These questions are of central concern to all string theorists, but they are also questions about which nothing can really be said. Only the passage of time will reveal the answers. The beautiful simplicity of string theory, the way in which it tames the conflict between gravity and quantum mechanics, its ability to unify all of nature's ingredients, and its potential of limitless predictive power, all serve to provide rich inspiration that makes the risk worth taking. These lofty considerations have been continually reinforced by the ability of string theory to uncover remarkably new physical characteristics of a string-based universe, characteristics that reveal a subtle and deep coherence in the workings of nature. In the language introduced above, many of these are generic features that, regardless of currently unknown details, will be basic properties of a universe built of strings. Of these, the most astonishing have had a profound effect on our ever-evolving understanding of space and time.